Introduction of Smithsonian Institution, United States National Museum, Bulletin 240, Contributions from the Museum of History and Technology, Papers 34 through 44 on Science and Technology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Smithsonian Institution, United States National Museum, Bulletin 240, Contributions from the Museum of History and Technology, Papers 34 through 44 on Science and Technology by Museum of History and Technology, United States. Washington, D.C., 1966. Publications of the United States National Museum. The scholarly and scientific publications of the United States National Museum include two series, Proceedings of the United States National Museum and United States National Museum Bulletin. In these series, the museum publishes original articles and monographs dealing with the collections and work of its constituent museums, the Museum of Natural History and the Museum of History and Technology, setting forth newly acquired facts in the fields of anthropology, biology, history, geology, and technology. Copies of each publication are distributed to libraries, to cultural and scientific organizations, and to specialists and others interested in the different subjects. The proceedings, begun in 1878, are intended for the publication in separate form of shorter papers from the Museum of Natural History. These are gathered in volumes, octavo in size, with the publication date of each paper recorded in the table of contents of the volume. In the Bulletin series, the first of which was issued in 1875, appear longer, separate publications consisting of monographs, occasionally in several parts, and volumes in which are collected works on related subjects. Bulletins are either octavo or quarto in size, depending upon the needs of the presentation. Since 1902, papers relating to the botanical collections of the Museum of Natural History have been published in the Bulletin series under the heading Contributions from the United States National Herbarium, and since 1959, in bulletins titled Contributions from the Museum of History and Technology have been gathered shorter papers relating to the collections and research of that museum. The present collection of contributions, papers 34 through 44, comprises Bulletin 240. Each of these papers has been previously published in separate form. The year of publication is shown on the last page of each paper. Frank A. Taylor, Director, United States National Museum. End of Section 0. Section 1 of Smithsonian Institution, United States National Museum. Bulletin 240, Contributions from the Museum of History and Technology, Papers 34 through 44 on Science and Technology, by the Museum of History and Technology, United States. This LibriVox recording is in the public domain. Contributions from the Museum of History and Technology, Paper 34, the 1893 Duryea Automobile in the Museum of History and Technology, by Don H. Burgable. Part 1. During the last decade of the 19th century, a number of American engineers and mechanics were working diligently to develop a practical, self-propelled vehicle employing an internal combustion engine as the motive force. Among these men were Charles and Frank Duryea, who began work on this type of vehicle about 1892. This carriage was operated on the streets of Springfield, Massachusetts in 1893, where its trials were noted in the newspapers. Now preserved in the Museum of History and Technology, it is a prized exhibit in the collection of early automobiles. It is the purpose of this paper to present some of the facts discovered during the restoration of this vehicle, to show the problems that faced its builders, and to describe their solutions. An attempt also has been made to correlate all this information with reports of the now almost legendary day-to-day experiences of the Duryeas as published by the brothers in various booklets and as related by Frank Duryea during 2 interviews recorded on tape in 1956 and 1957 while he was visiting the Smithsonian. The author, Don H. Berkable, is on the staff of the Museum of History and Technology in the Smithsonian Institution's United States National Museum. Of the numerous American automotive pioneers, perhaps among the best known are Charles and Frank Duryea, beginning their work of automobile building in Springfield, Massachusetts, and after much rebuilding, they constructed their first successful vehicle in 1892 and 1893. No sooner was this finished than Frank, working alone, began work on a second vehicle having a 2-cylinder engine. With this automobile, sufficient capital was attracted in 1895 to form the Duryea Motor Wagon Company, in which both brothers were among the stockholders and directors. A short time after the formation of the company, this second automobile was entered by the company in the Chicago Times-Herald automobile race on Thanksgiving Day, November 28, 1895, where Frank Duryea won a victory over the other 5 contestants, 2 electric automobiles, and 3 Benz machines imported from Germany. In the year following this victory, Frank, as engineer in charge of design and construction, completed the plans begun earlier for a more powerful automobile. During 1896, the company turned out 13 identical automobiles, the first example of mass production in American automotive history. Even while these cars were under construction, Frank was planning a lighter vehicle, one of which was completed in October of 1896. This machine was driven to another victory by Frank Duryea on November 14, 1896, when he competed once again with the European-built cars in the Liberty Day Run from London to Brighton. The decision to race and demonstrate their autos abroad was the result of the company's desire to interest foreign capital. Yet Frank later felt they might better have used their time and money by concentrating on building cars and selling them to the local market. Subsequently, in the fall of 1898, Frank arranged for the sale of his and Charles' interest in the company, and thereafter the brothers pursued separate careers. Frank, in 1901, entered into a contract with the J. Stevens Arms and Tool Company of Chicopee Falls, Massachusetts, which built automobiles under his supervision. This association led, in 1904, to the formation of the Stevens-Duryea Company, of which Irving Page was president and Frank Duryea was vice president and chief engineer. This company produced, during its 10-year existence, a number of popular and well-known models. Among them, a light 6, known as the Model U, in 1907, a larger 4-cylinder called the Model X in 1908, and a larger 6, the Model Y, in 1909. In 1914, when Stevens withdrew from the company, Frank obtained control. The following year, he sold the plants and machinery, liquidated the company, and, due to ill health, retired. Charles, in the meantime, located in Reading, Pennsylvania, where he built autos under the name of the Duryea Power Company. Here, and later in Philadelphia under the name of the Duryea Motor Corporation and other corporate names, he continued for a number of years to build automobiles, vacuum cleaners, and other mechanical devices. Until the time of his death in 1938, he practiced as a consulting engineer. Early automotive experience. Born in 1861 near Canton, Illinois, Charles E. Duryea had learned the trade of a mechanic following his graduation from high school, and subsequently turned his interests to bicycle repair. He and his brother James Frank, 8 years younger, eventually left Illinois and moved to Washington, D.C., where they were employed in the bicycle shop of H.S. Owen, one of that city's leading bicycle dealers and importers. While in Washington, Charles became a regular reader of the Patent Office Gazette, an act which undoubtedly influenced his later work with automobiles. A short time later, probably in 1889, Charles contracted with a firm in Rockaway, New Jersey, to construct bicycles for him, but their failure to make delivery as promised caused him to go to Chicopee, Massachusetts, where he contracted with the Ames Manufacturing Company to do his work. Moving there in 1890, he obtained for his brother a position as toolmaker with the Ames Company. Thus, Frank Duryea, as he was later known, also became located in Chicopee, a northern suburb of Springfield. During the summer of 1891, Charles found the bicycle business left him some spare time, and the gasoline-powered carriages he had read of earlier came constantly into his mind in these periods of idleness. He and Frank studied several books on gasoline engines, among them one by an English writer, title and author unknown. This described the Otto four-stroke cycle, as now used. Some engineers, however, were concerned because this engine, on the completion of the exhaust stroke, had not entirely evacuated all of the products of combustion. The Atkinson engine, patented in 1887, was one of the attempts to solve this, as well as several other problems, thus creating a more efficient cycle. This engine was designed so that the exhaust stroke carried the piston all the way to the head of the engine, while the compression stroke only moved the piston far enough to sufficiently compress the mixture. The unusual linkage necessary to create these unequal strokes in the Atkinson engine made it seem impractical for a carriage engine, where compactness was desired. Going to Hartford, Connecticut, possibly on business relating to his bicycle work, Charles visited the Hartford Machine Screw Company, where the Daimler-type engine was being produced, but after examining it, he felt it was too heavy and clumsy for his purpose. Also in Hartford, he talked over the problem of a satisfactory engine with C.E. Hawley, an employee of the Pope Manufacturing Company, makers of the Columbia bicycle. Hawley, searching for a way to construct an engine that would perform in a manner similar to the Atkinson, yet would have the lightness and compactness necessary for a carriage engine, suggested an idea that Charles believed had some merit. This idea, involving the use of what the Duryeas later called a free piston, was eventually to be incorporated in their first engine. Construction begins. Back in Chicopee again, Charles began planning his first horseless carriage. Frank later stated that they leaned heavily on the Benz patents in their work, but while the later engine and transmission show evidence of this, only the Benz manner of placing the engine and the flywheel seemed to have been employed in the original Duryea plan. Charles reversed the engine so that the flywheel was to the front rather than to the rear, as in the Benz patent, but made use of Benz's vertical crankshaft so that the flywheel rotated in a horizontal plane. Previously, most engines had used vertical flywheels. Benz, believing that this practice would cause difficulty in steering a propelled carriage, explained his reason for changing this feature in his U.S. Patent 385087 issued June 26, 1888. In motors hitherto used, the flywheels have been attached to a horizontal shaft or axle and have thus been made to revolve in a vertical plane, since the horizontal shaft is best adapted to the transmission of power. If, however, in this case we should use a heavy rotating mass, corresponding to the power employed and revolving rapidly in a vertical plane, the power to manage the vehicle or boat would become very much lessened, as the flywheel continues to revolve in its plane. I therefore so designed the apparatus that its crankshaft X has a vertical position and its flywheel Y revolves in a horizontal plane. By this means, the vehicle is not only easily controlled, but also the greatest safety is attained against capsizing. To the Duryea plan, Benz may also have contributed the idea for positioning the countershaft, though its location is sufficiently obvious that Charles may have had no need for copying Benz. Charles wisely deferred from Benz by placing the flywheel forward, thus eliminating the need for the long driving belt of the Benz carriage. Yet he did reject the bevel gears used by Benz, which might well have been retained, as Frank was later to prove by designing a workable transmission that incorporated such bevel gears. The initial plan, as conceived by Charles, also included the details of the axles, the steering gear, countershaft with its friction drum, the two-piece angle iron frame upon which the countershaft bearings were mounted, and the free piston engine with its ignition tube, since hot tube ignition was to be employed. No provision was made, however, for a burner to heat the tube, nor had a carburetor been designed, though it had been decided not to use a surface tank carburetor. The plans called for no muffler or starting arrangement. Many engines of that period were started simply by turning the flywheel with the hands, and Charles felt this method was sufficient for his carriage. The Ames plant customarily had a summer shutdown during August. Thus, during August of 1891, Charles and Frank had access to a nearly empty plant in which they could carry on experiments and make up working drawings of the proposed vehicle. It cannot now be conclusively stated whether any parts were made for the car during August or the remainder of the year. It is more likely that the brothers attempted to complete a set of drawings. Frank Harrington, chief draftsman at Ames, may have helped out at this time. From Charles's statement of April 14, 1937, it is learned that he did prepare drawings during 1892. The first contemporary record of any work on vehicles is a bill, dated January 21, 1892, for a drawing made by George W. Howard and Company. This drawing was made in the fall of 1891 by Charles A. Bartlett, a member of the Howard firm and a neighbor of Charles Duryea, according to a statement by Charles in the Automobile Trade Journal of January 10, 1925. He was then also of the opinion that this drawing may not have had anything to do with the carriage they were about to assemble, but a notation found by Charles at a later date has led him to believe that it possibly concerned a business-type vehicle he had discussed with an unidentified Mr. Snow. By early 1892, Charles needed capital to finance his venture, an old carriage to attach his inventions to, a place to work, and a mechanic to do the work. On March 26th, he stopped by the Smith Carriage Company and looked over a selection of used buggies and phaetons. He finally decided on a rather well-used ladies' phaeton, which he purchased for $70. The leather dash was in so deplorable a state it would have to be recovered before the carriage went onto the road, and the leather fenders it once possessed had previously been removed. Yet the upholstery appeared to be in satisfactory condition, and the candle lamps were intact. 2 days later, Charles was able to interest Irwin F. Markham of Springfield sufficiently to obtain his financial aid in the project. A contract was drawn up between the two men, which stated that Mr. Markham was to put up $1,000, for which he received a 5/10 share of the venture. When the $1,000 had been used, he then had the option to continue his aid until the project had been carried to a successful climax and retain his half share, or to refuse further funds and relinquish 4 of his 5/10 interest in the business. Had he eventually chosen the latter, Charles would obviously have to seek assistance elsewhere. That same day, March 28th, Charles found working space and machinery available at John W. Russell and Sons Company in Springfield. The Russells had recently completed a large government order of shells for the famous dynamite guns later used on board the cruiser Vesuvius in the Spanish-American War, and this left an entire second floor, approximately 35 by 85 feet, virtually unoccupied, according to an affidavit of William J. Russell of April 30th, 1926. Now ready to begin the actual work, Charles hired his brother Frank to start construction. Frank started about the 1st of April, receiving a raise of about 10% over the salary he had received at Ames. Before the vehicle was complete, a number of other men performed work on some of the parts, among them William Dietz, who had been hired by Charles primarily to work on bicycles in the same area, but who occasionally assisted on the carriage. Russell Company records show time charged against Charles Duryea by 6 other Russell employees: W. J. Russell, P. Colgan, C. E. Merrick, T. Shea, L. J. Parmalee, and A. A. Poisson. It is Frank Duryea's remembrance that he started work on Monday, April 4th. He first removed the body, with its springs, and placed it on a pair of wooden horses where it remained until the summer of the following year. The next step was to remove the rear axle and take it to a blacksmith shop where the old axle spindles were cut off and welded to a new drop center axle. Following this, the front axle spindles were removed, the ends of the axle slotted, and a webbed C-shaped piece carrying the kingpin bearings was fitted into each slot, braced from underneath by short brackets, which were riveted and brazed in place. The old spindles were then welded to the center of offset kingpins, which in turn were mounted in the bearings in a manner similar to that in which the frame of the Columbia high-wheeled bicycle was mounted on its fork. Arms welded to the lower end of the kingpins were connected by tie rods to an arm on the lower end of the vertical steering column located on the center of the axle. While work on the running gear advanced, some progress was made in the construction of the engine. Patterns for the castings were fabricated, most of them by Charles Marshall on Taylor Street, and castings were poured. The body or main casting of the engine resembled a length of cast-iron pipe. It had no bosses or lugs cast on, nor any water jacket, for they thought the engine would be kept cool merely by being placed in the open air. The front end of the engine was secured to the vehicle by 4 bolts, which passed through the halves of the bearings and onto 4 projections on the opened end of the engine. As the crankshaft of this engine was retained in constructing the present engine, it is logical to assume that the bearings were the same also. The head was cast as a thick disc, with both intake and exhaust valves located therein, and was bolted onto the flanged head end of the engine. Inside the cylinder was the strange arrangement previously suggested by C.E. Hawley. To the connecting rod was attached a rather ordinary ringed piston, over which was fitted a free ringless piston, machined to fit closely the cylinder bore. This floating piston could move freely, a distance equal to the compression space. The intention was that on the intake stroke, suction would open the intake valve, which had no positive opening arrangement, and draw in the mixture, which was then compressed as in a regular Otto engine. Fired by the hot tube ignition system, the force of the explosion would drive both pistons down, forcing the outer one tight against the head of the smaller one, and at the end of the stroke, the longer wall of the outer piston would strike an arm projecting into the cylinder near the opened end, moving forward the exhaust valve rod to which the arm was attached, thus pushing open the valve in the head. On the exhaust stroke, the unrestrained outer piston moved all the way to the head, expelling all of the products of combustion and pushing the exhaust valve shut again. With a bore of 4 inches or less, this engine, Charles believed, should develop about 3 horsepower and run at a speed between 350 to 400 revolutions per minute. As no ignition system had yet been provided, they prepared a 4.5-inch length of 1/4-inch iron pipe, closed at one end, and screwed the open end into the head. Heating this tube with an alcohol burner would cause ignition of the mixture when a portion of it was forced into the heated tube toward the end of the compression stroke. No attempt was made at this time to use the electrical make and break circuit used in their second engine, as the free piston would have wrecked the igniter parts on the exhaust stroke, and the push rod, located on the end of the piston, would have prevented the piston from closing the exhaust valve. After keying the flywheel to the lower end of the crankshaft, Charles and Frank decided to make an attempt to run the engine. Carrying it into a back room, probably during July or August 1892, they blocked it up on horses. A carburetor had not yet been constructed, so they attempted to start the engine by spinning the flywheel by hand, at the same time spraying gasoline through the intake valve with a perfume atomizer previously purchased at a drugstore at the Massasoit House. Repeated efforts of the 2 men to start the engine resulted in failure. In the belief that the defects, whatever they might be, could be remedied after the engine was installed, the Duryeas went ahead and mounted the engine in the carriage. To do this, they shortened the original reach of the carriage, allowing the engine itself to become the rear continuation of the reach. The four ears on the front, or open end of the engine, were bolted to the centrally located frame, with the bearing blocks in between. This frame, the same one now in the vehicle, was constructed of two pieces of angle iron riveted and brazed together. Greater rigidity was obtained by a number of half-inch iron rods running from the frame to both front and rear axles. Because of the absence of any mounting brackets on the engine casting itself, a wooden block with a trowel on top to receive the body of the engine was fitted between the engine and the axle, while two U-shaped rods secured it with clip bars and nuts underneath. Beneath the flywheel was mounted the friction transmission of Charles's design. This consisted of a large drum, perhaps 12 inches in diameter, equal in length to the diameter of the flywheel, and keyed to a shaft directly under the center of the crankshaft and parallel to the axles. The diameter of the drum estimated by examination of existing features. In view of the four projections of the frame extending downward and just in front of the jackshaft position, it is likely that these supported the four jackshaft bearings. Being a bicycle manufacturer, Charles saw the need for a differential or balance gear. Accordingly, he purchased from the Pope Manufacturing Company a very light unit of the type formerly used on Columbia tricycles, and installed it somewhere on the jackshaft. A small sprocket on each end of the shaft carried a chain from the larger sprockets clamped to the spokes of each rear wheel. The lower surface of the flywheel had been machined so as to form a friction disc, with a 1/4 inch depression, 3 inches in diameter, turned in the center. The drum was positioned so that its upper surface was 1/4 inch below the face of the flywheel. Hanging loosely around the drum was an endless belt, 1 1/2 inches wide, first made of rather soft rubber packing material. The belt lay on the drum surface between the fingers of a shipper fork. While it lay under the 3-inch depression in the center of the flywheel, the belt and the drum were at rest, but when it was moved away from that depression, the belt wedged itself tightly between the drum and the flywheel. The resulting friction caused the drum to turn and setting the vehicle into motion. The farther the belt was moved toward the outer edge of the wheel, the faster the drum and the vehicle moved. In September of 1892, Charles, who had contracted with a Peoria, Illinois firm to have bicycle parts manufactured, decided to move to that city. Departing on the 22nd of September, he did not return to Springfield for over 2 years, and thus was not able to participate in the completion and testing of the carriage. At the time of his departure, several units on the carriage were incomplete. A carburetor had not been built, nor had a satisfactory burner or belt-shifting device. Charles had experimented with various shifting levers just before leaving Springfield. However, as he reported later, he did not succeed in designing a workable mechanism. Frank Duryea, now left to finish the work unassisted, continued the experiments with the belt shifter. He finally worked out a fork mounted on a carriage that was supported by 2 rods, each of which slid in 2 bearings. Although the short distance between the 2 bearings caused the shifter carriage to bind occasionally, the device was thought to be sufficient and was installed in front of the frame, connected to a system of cables, arms, and rods, possibly similar to the present cam bar shifter. The shipper fork carriage was moved from side to side by raising or lowering the tiller. Turning now to an efficient burner for heating the ignition tube, Frank started with an ordinary wick-type kerosene lamp with a small metal tank. Wishing to use gasoline in the lamp, he found it necessary to fabricate a number of burner units before he found a type that gave him a clean blue flame. He then found the flame to be very sensitive to drafts and easily extinguished, and devised a small shield or chimney to afford it some protection. Early in October, while still working with the burner, Frank developed a severe headache. He felt the fumes of the lamp had probably caused it, and went to his room in the home of Mr. and Mrs. Patrick on Front Street in Chicopee. After he noticed no improvement, a doctor's examination showed he had typhoid fever, and on October 5th he was admitted to the Springfield Hospital. Here he remained for 1 month, being discharged on November 5th. Returning to his room, he was informed that because of the fear that he might be a typhoid carrier, the Patricks preferred him to find other lodgings. He readily accepted the invitation of Mr. and Mrs. D.H. Nesbitt of Chicopee to take a room with them. After several weeks recuperating in their home, he left Springfield to visit his mother in Wyoming, Illinois. After a restful visit at home, Frank Duryea returned to Springfield and finished the work on his burner. Now, only the lack of a carburetor prevented a trial of the vehicle. He recalls that he studied several gasoline engine catalogs, and one of them, a Fairbanks catalog he believes, he saw a design that seemed to suit his needs. He decided to simplify the construction and operation of his carburetor and had a small bronze casting made to form the body of it. Inside was a gasoline chamber with two tapped openings, one to receive a pipe from the 2-gallon gasoline tank mounted above the engine, the other taking a pipe to the overflow tank underneath the engine, thus maintaining the gasoline level without the use of a float valve. This latter tank had a hand pump on one end, so that the overflow gasoline could at times be pumped again into the main tank. Gasoline passed from the carburetor chamber, through a needle valve, adjusted by a knob on top, then through a tiny tube that entered the pipe leading to the intake valve. It is not certain whether this intake pipe was at first fitted with the choke arrangement later used with the second engine. Frank, hoping at last to be rewarded for his efforts by the sound of explosions from the engine, was ready to give the carriage an indoor trial. Standing astraddle of the reach and facing to the rear, he spun the flywheel with both hands, taking care not to get his hands caught between the wheel and the frame. His efforts were in vain, and there was a complete failure to obtain ignition. He then made a new ignition tube, nearly twice as long as the original 4.5-inch tube, and turned down its wall as thin as he thought safety allowed. The thinner wall did not conduct the heat off so rapidly, and thus kept the tube hot enough to permit ignition. After this slight change, he was able to get a few occasional explosions, but he does not now believe that the engine ever operated continuously. Each explosion was accompanied by a loud knock, due undoubtedly to the movement of the free piston. Had the engine operated continuously, it is likely that the action of the free piston would have shortly wrecked the engine. Further efforts appeared unwarranted until alterations could be made. The two pistons were first pinned together into a single unit which was probably ringless, since it is believed the walls of the outer piston were too thin to admit rings. Because the piston no longer struck the exhaust valve, a short rod had to be screwed onto the piston head. This pushed the valve shut at the completion of the exhaust stroke. The remaining problem, the opening of the exhaust valve, was solved by screwing a device to the side of the cylinder which operated from the sidewise motion of the connecting rod. This device shifted a small spacer between the piston and the striker arm of the exhaust valve rod, permitting the piston to push open the exhaust valve. On alternating strokes, the spacer shifted back out of the cylinder. Therefore, no contact was made between piston and striker arm. Sometime in February 1892, the altered engine was successfully started. At last, the transmission could be tested. Will Russell had come upstairs to watch the trial, and according to a statement by him, given April 30th, 1926, Frank, standing to the right of the engine and behind the rear axle, reached forward and, with the combination tiller-belt shifter, moved the belt into driving position. The carriage started forward, but as it approached the wall of the building, Frank discovered that he could not get the belt back into the neutral position. In desperation, he grasped the rear axle with both hands and was dragged a short distance, attempting to stop the machine before it struck the wall. He had, however, sufficiently retarded it so that no damage was done. This short trial demonstrated some of the weaknesses in the friction transmission. Since the speed of the surface of the flywheel, in feet per second, increased in proportion to the distance of the point of contact from the center, the outer edge of the belt attempted to run faster than the inner edge. This conflict of forces not only put an undue load on the motor, causing a great loss of power, but it also created a tendency for the belt to work towards the outer edge of the flywheel. Conversely, when the operator desired to return the belt to neutral, it strongly resisted any efforts to slide it toward the center of the wheel, as Frank had learned from the wall-bumping incident. Furthermore, the rubber belt on the friction drum had worn so badly that it had to be replaced at least once during the brief experiments. At this point, Frank and Markham felt that the carriage was anything but satisfactory. While they were trying to decide what steps should be taken next, Frank added one last improvement to the engine. Fearing that the uncooled cylinder might suffer damage from the excessive heat, he constructed a copper water jacket in two halves, drew them together around the cylinder with clamping rings, and soldered the seams. Asbestos packing sealed the end joints where the jacket contacted the cylinder. Thinking back, Frank does not recall that he ever used a water tank with this engine, though he does remember adding water through the upper jacket opening. The engine was run only for a few brief periods following this addition. Obviously, this collection of patchwork could not fulfill their needs for an engine. First, it would be next to impossible to start if the body was placed on the running gear, as the flywheel then would be practically inaccessible. The absence of rings on the piston caused a further loss of power to the already overloaded engine. The flywheel was too light. The absence of any form of governor left the operator with no control over the engine speed. Ignition was poor, partly owing to the hot tube arrangement, and partly to the excessive distance between the engine and the carburetor. Frank wrote his brother Charles on February 6th that, in his opinion, the mixing chamber was so far from the engine that the gasoline could not be drawn into the cylinder as liquid, and it was too cold to vaporize and go in as gas. Thus he had difficulty in getting the engine started. When it did start, the explosions were unmuffled. Less important to him than these defects, however, was the awkward and unsightly wooden engine mount. End of Section 1. Section 1, Part 2 of Smithsonian Institution, United States National Museum, Bulletin 240, Contributions from the Museum of History and Technology, Papers 34 through 44 on Science and Technology, by the Museum of History and Technology, United States. This LibriVox recording is in the public domain. Contributions from the Museum of History and Technology, Paper 34. The 1893 Duryea Automobile in the Museum of History and Technology by Don H. Burgable. Part 2. Description of the automobile. Sometime in the early part of March, Frank convinced Markham that he could construct a new and practical engine, using only previously tried mechanical principles. Drawing up new plans for this engine, he took them to Charles Marshall, who began to work on the patterns for the new engine castings. After the patterns had been delivered to the foundry, Frank left Springfield for a short vacation in Groton, Connecticut, where he visited with his fiancée. On May 17, 1893, several weeks after his return to Springfield, they were married. The engine castings were undoubtedly received from the foundry prior to Frank Duryea's marriage, and the work of machining and assembling the parts went on through the spring and summer. This engine, still on the carriage in the Museum of History and Technology, is cased with a water jacket and has bases on top to support the front and rear bearings of the starting crankshaft, and a base with port on the upper right side where the exhaust valve housing was to be bolted. On the underside are two flanges, forming a base for seating the engine on the axle. A separate combustion chamber is cast and bolted to the head. Inside this chamber are located the igniter parts of Frank's electric ignition system. The fixed part, an insulated electrode, is screwed into the right side of the chamber and is connected with the ignition switch outside, to which one of the ignition wires is attached. A breaker arm inside is pinned to a small shaft extending through the top of the chamber. Around the breaker arm shaft is a small coil spring, originally a spiral spring, according to the letter of Charles Duryea shown in Figure 17. anchored below to a thin brass finger extending toward the right side of the car, and above to a nut screwed tightly onto the shaft. This nut is also the terminal for the other ignition wire. The action of the spring keeps the breaker arm and the electrode in constant contact until the push rod on the end of the piston strikes the arm and separates the two parts. Breaking contact then produces the ignition spark. Since the mechanism would spark at the end of both the exhaust and compression strokes, the battery current is conserved by a contact strip on the underside of the larger exhaust valve gear, by means of which the flow of current is cut off during the greater part of the cycle. On the left side of the combustion chamber is bolted the housing containing the tiny intake valve. A comparatively weak spring seats this valve in order that the suction created by the piston can easily pull it open. Clamped onto the valve housing is the intake pipe, enclosing the choke and carrying the carburetor on its forward side. The choke consists of two discs, which block the pipe, each with 4 holes at the edges and one in the center. Turning one disc by means of a small handle outside, so that the 4 outer holes cannot coincide with those on the inner disc, decreases the flow of air and causes all air to rush through the center hole, where the tiny carburetor tube passes through. The present carburetor was transferred over from the first engine. When Frank later installed the engine on the carriage, he noticed the close proximity of the intake pipe to the open end of the muffler. Believing that the fumes might choke the engine, he attached a long sheet metal tube to the intake pipe so that fresh air would be drawn in from a point further forward on the vehicle. Moving to the right side of the engine brings the exhaust valve assembly into view. This valve is contained in a casting bolted over the exhaust port in the side of the cylinder, and from the casting, a pipe leads to the muffler underneath. The valve is pushed open by a rod connecting to a crank which is pinned to the lower end of a shaft carrying an iron gear on top. The gear is in mesh with a fiber gear, keyed to the upper end of the crankshaft, with half the number of teeth. This ratio permits the opening of the exhaust valve on every other revolution. The crankshaft of the first engine was retained for the new engine, thus giving the two engines the same stroke of 5 3/8 inches, but the bore was increased slightly to 4 3/8 inches. With this larger bore, and with the engine speed increased to 500 RPM, Frank rated this engine at 4 horsepower. A heavier flywheel, with a governor resting in the upper recess, was pressed onto the crankshaft. As the operator of the vehicle had no control over the carburetor once he climbed into the seat, this governor was necessary to maintain regular engine speed. Its function was to move a slide on the exhaust valve unit, to prevent the valve from closing. Thus, the engine, with the suction broken, could not draw a charge on the next revolution. During the recent restoration of this carriage, it was found that while most parts are still intact, nearly all of the governor parts are missing. A description of them must therefore be based on the recollections of Frank Duryea along with certain evidences seen on the engine. Just on top of the flywheel, and surrounding the crankshaft, rest 2 rings, 3 7/8 inches in diameter. Into the opposing surfaces of these rings are cut a series of small inclined planes, appurtenant to each other. On the outer circumference of the upper ring, 2 pins pass through a pair of lugs mounted in the flywheel, causing the ring to rotate with the flywheel, yet permitting vertical movement. Underneath, the other ring is allowed to turn slightly when, by means of 2 connecting links, the arms of the governor push against them. These 2 arms, each constructed like a right angle and pivoted at the apex, are arranged directly opposite each other far out in the flywheel recess. As a weight on one angle of the arm presses outward by centrifugal force against the spring, the other angle presses inward against the connecting link mentioned above. The turning of the lower set of the inclined planes against the fixed set above raises the upper ring, and the fork resting on it. The upward movement of this fork, which is a continuation of an arm pivoted to a bracket midway between the crankshaft and the slide carrying the exhaust valve stop, causes the other end of the arm to drop, pulling the slide down with it. In this manner, the closing of the exhaust valve is blocked, preventing the intake of the next charge, and therefore the engine misses one or more explosions until it slows to its normal speed. A starting shaft is mounted above the engine casting by a cast iron bracket on either end. The front end of the shaft has a bevel gear, which is held by a coil spring behind the front bracket, just out of contact with a bevel gear pressed into the upper end of the crankshaft. The short rear portion of the shaft is a tube which slides over the main shaft, fitting the removable hand crank to the squared end of the hollow shaft, and turning the crank clockwise will advance the forward section of shaft through the medium of a pair of inclined collars. With the bevel gears now engaged, the engine may be cranked. When the ignition begins, the inclined collars slide back down each other's surfaces. The shaft is again shortened, and its bevel gear springs free of the one on the crankshaft. While Frank worked on his engine, he realized that certain parts of the old running gear would need to be altered or replaced. In view of the heavier and more powerful engine, he felt the old wheels, probably having compressed band hubs, were inadequate. He procured a set of new, heavier wheels with Warner-type cast-iron reinforced hubs. The angle iron frame, apparently sturdy enough to carry the added weight, was retained, but it was decided to install a heavier rear axle. The front axle assembly was at first allowed to remain unchanged, as was the steering apparatus. A short time later, when the engine and friction transmission were bolted in place on the running gear, Frank saw that the rigidity of the framework had an undesirable effect. When the vehicle passed over any unevenness in the shop floor, the framework was distorted and caused the jackshaft bearings to bind tightly enough on the shaft to prevent its being turned by hand. In order to provide the three-point suspension necessary to eliminate this distortion, Frank attached the forward parts of the framework to an extra wooden spring bar, installing between this bar and the front axle a vertical fifth wheel, of the type ordinarily used in a horizontal position in any light carriage. Frank next calculated that with the faster-running engine, the speed of the vehicle would be about 15 miles an hour, too much for the heavily loaded wheels. As he intended to make use of the original transmission, he decided to decrease the speed by increasing the size of the friction drum. He accomplished this by sliding a heavy fiber tube over the original drum, bringing its diameter to approximately 14 inches. The original shipper fork carriage was improved by separating the original bearings to a greater distance and eliminating one of the two bearings on one end. This permitted a smooth and free operation of the small sliding carriage. In August of 1893, possibly as a result of indoor experiments, Frank discovered that the chains running from the small five-tooth jackshaft sprockets to the large bronze wheel sprockets were tight at some times and loose at others. This caused considerable unnecessary noise. The difficulty, apparently, was the result of the sprockets being cast and not machined. The pattern maker had said he believed he could make the pattern accurately enough so that no machining of the castings would be necessary. Nice castings were produced, but these sprockets were the reason why an unusual construction was put on the crankshaft, meaning jackshaft, explained Frank Duryea during an interview at the National Museum on November 9, 1956. Elaborating further, in reply to the queries of E.A. Battison of the museum's Division of Engineering, Duryea told of the problem and the solution, when he explained that the sprockets had places where the shrinkage was not even. The hot metal, contracting as it cooled, did not seem to contract uniformly, creating slightly unequal distances between teeth. This resulted in the chain hanging quite loose in some places, and in others the tightness prevented adjustment. He contacted Will Russell, foreman of the Russell shop, where the automobile was made, and Russell showed him a device built by George Warwick, who had made the Warwick bicycle. It was an internal cut gear, according to Duryea's description, with sprocket teeth on its periphery. With sprockets outside and normal teeth inside, the wheels were about 6 inches in diameter externally. These little internal gear sprockets were hung on double-shrouded pinions, secured to each end of the jackshaft. A solid disc, or housing, fitted against both ends of the pinion to prevent the internal gear from working off sideways. Duryea explained the function of these unique little parts. As soon as tension came on that ring gear that we talked about, it not only tightened the chain hanging on the sprocket on the upper side, but it tightened it on both sides. The sprocket rocks right out, both sides of the chain are tight. This feature is one rarely encountered elsewhere, and Duryea, later in the interview, said, "To tell you the truth, I think I was just a little bit ashamed about the thing because I had to pull it off. I didn't like the looks of it after I got it on." Two small tanks, each with a capacity of approximately 2 gallons, were mounted over the engine in the positions they still occupy, the one on the left for gasoline, the other for water. The small fitting under the gasoline tank had a thumbscrew shutoff and a glass sight feed tube leading to the carburetor. The water tank, an inch longer than the gasoline tank, communicates with the water jacket of the engine through 2 pieces of half-inch pipe entering the jacket from above and below. The overflow tank, holding just over 1 gallon, is suspended between the rear axle and the flywheel. A number of mufflers were constructed for the engine. The first experimental one was built of wood, being a box of 6 by 6 by 15 inches with a hole for the exhaust pipe in one end and a series of small holes in the opposite end. Inside, Frank arranged metal plates which were somewhat shorter than the depth of the box. Every other one was attached to the bottom of the box. The intermediate plates were fastened to the top. This contrivance muffled the sound considerably, but as might be expected, soon began to smoke. There can be little doubt that it was replaced before any of the outdoor trials began. Another type consisted of a cylindrical metal shell, perhaps 6 inches in diameter and 10 or 12 inches long. Here a series of perforated baffle plates were inserted, with alternating solid plates having parts of their external edges cut away. 2 bolts running the length of the muffler held on the cast iron heads in a manner quite similar to the Model T Ford mufflers of later years. Though partially satisfactory, Frank, in a November 6, 1957 interview, complained that it made a metallic sound. Perhaps this was the muffler he used from September to November of 1893. On August 28th, Frank wrote to Charles saying the carriage was almost ready for the road, and that he hoped to take it out for a test on the coming Saturday, off somewhere where no one will see us. There is no evidence showing whether the amount of remaining work permitted the proposed trial on September 2nd. The body was finally replaced on the running gear, at which time it was found necessary to raise the seat cushion several inches by the insertion of a framework made of old crating boards. This allowed sufficient room between the seat and the frame to suspend the batteries and coil. 6 No. 2 Samson batteries were contained in this space, 3 on each side, in rows parallel to the side of the vehicle. The Samson battery consisted of a glass jar containing a solution of ammonia salts and water, with a carbon rod in the center, housing a zinc rod. It is difficult to understand why they used Samson batteries rather than dry cells. Perhaps they were concerned with the mounting cost of the machine and were making use of parts already on hand. A coil, possibly from an old gaslight igniter system, accompanied the Samson batteries under the seat. The original coil is now missing. The iron dash frame, previously recovered and provided with a rain apron to be pulled up over the knees in the event of heavy rain, blew in under the carriage top, was bolted back in place. Frank and Mr. Markham gave the carriage a quick painting. Later, Frank admitted the machine never had a good job of painting. Before the motor wagon actually got onto the road, a reporter on the Springfield Evening Union got some statistics on it, and an item appeared on September 16th giving the first public notice of the machine. Toward the latter part of the following week, Frank was ready to give the product of his labors its first road trial. On September 21st, the completed carriage was rolled onto the elevator at Russell's shop. Seeing that the running gear was too long for the elevator, they raised the front of the machine, resting the entire weight of 750 pounds on the rear wheels. Once outside the building, they pushed it into an area between the Russell and Stacy buildings. After dark, so no one will see, Mr. Bemis, Mr. Markham's son-in-law, brought a horse, and they pulled the phaeton out to his barn on Spruce Street. There, on Spruce and Florence Streets, the first tests were made. The next day, Frank wrote his brother, saying, "Have tried it, the carriage, finally and thoroughly, and quit trying until some changes are made. Belt transmission very bad. Engine all right." He did admit the engine seemed to be well loaded most of the time. He also had an idea in mind to replace the poor transmission, explaining the plan to Charles. The 3 gears on secondary shaft have friction clutches. The 2 bevel gears on same shaft are controlled by a clutch which frees one and clutches the other at will. This provides a reverse. The Springfield Evening Union of September 22nd carried a notice of the trial. This report, too, commented on the faulty transmission and the plan already in Frank's mind for the new transmission. The friction belt allowed of the speed being steadily increased or diminished at the will of the driver and caused no sudden forward motion of the carriage. But while this arrangement has many advantages, it uses up the power so that the 2 horsepower furnished by the motor, somewhat less than the rating Frank gave the engine, was reduced to less than 3/4 horsepower on reaching the main shaft. This would not be sufficient to propel the carriage up steep grades, but would be sufficient to run the carriage on level road. The inventors will do away with this belt in favor of a clamp gear and will make the drum wheel smaller. By this means there will be very little power lost in transmission to the shaft, and by a patented arrangement the carriage may be started gradually, but the speed must be increased by shifting the clamp gear to a succession of gears on the driving wheel of the motor. The speed of the carriage will be fixed permanently according to the size of the gear that the smaller one is shifted to. The test of the machine with the gear arrangement will be made soon. In October, Frank decided on another vacation and went to Chicago to see the Columbian Exposition. Charles had come up from Peoria to see the fair, and the two talked over the progress on their motor wagon and discussed the transmission problem. They gave particular attention to everything related to engines and motor carriages, and Frank recalls seeing a Daimler quadricycle that impressed him with its performance. Just what decisions the two might have made there are unknown, yet it is likely that they agreed to give the old transmission one more chance to prove itself. Returning to Springfield, probably in the first week of November, Frank gave the friction drive its final test, this time substituting a leather belt for the rubber one first used. Mr. Markham, though intensely interested in the experiments, apparently was dubious concerning the safety of the carriage. It had no brakes, and fearing failure of the transmission on a downgrade, he was reluctant to ride in the machine. On November 9, he asked Will Bemis to try it for him. The following day, the Springfield Morning Union gave a description of the run. Residents in the vicinity of Florence Street flocked to the windows yesterday afternoon, astonished to see gliding by in the roadway a common-top carriage with no shafts and no horse attached. The vehicle is operated by gasoline and is the invention of Irwin Markham and J.F. Duryea. It has been previously described in the Union, and the trial yesterday was simply to ascertain the practical value of a leather friction surface which has been substituted for the rubber one previously used. The vehicle, which was operated by Mr. Bemis, started from the corner of Hancock Avenue and Spruce Street, and went up the avenue, up Hancock Street, and started down Florence Street, working finely. But when about halfway down the latter street, it stopped short, refusing to move. Investigation showed that the bearing had been worn smooth by the friction, and a little water sprinkled upon it put it in running condition again. The rest of the trip was made down Florence and down Spruce Street, to the residence of the inventors. They hope to have the vehicle in good working condition soon. The same evening, the late edition ran a brief paragraph stating that the test was made to determine the value of a leather friction surface for propelling the wagon that had been substituted in place of the rubber surface used in the former test. Bemis, according to Frank Duryea's recollection, was not impressed with the performance of the machine, saying, "The thing is absolutely useless." And for a time it appeared that further support from Markham would not be forthcoming. Frank, believing eventual success to be near, drew up plans showing his geared transmission, and with these managed to gain Markham's partial support. Money for material and use of the shop was to continue, but Frank was to complete the work on his own time. Now, receiving no salary, Frank worked hurriedly on the transmission throughout late November and December and the first 2 weeks of January, first discarding the old friction drum and shaft and the ship-afore carriage. He bolted a rawhide bevel gear to the lower surface of the flywheel. This turns 2 bevel gears in opposite directions on a countershaft directly underneath, approximately in the position of the old jackshaft. The right bevel gear is secured to the main countershaft on which 2 clutches are mounted, one on each side of the crankshaft. On a sleeve turning freely around the countershaft is mounted the reverse bevel gear and clutch. 3 free-running clutch drums, the right one carrying the high-speed gear, the 2 on the left carrying the combination low-speed and reverse gear between them, complete the countershaft assembly. The clutch assemblies are of Frank Duryea's design, having internal arms, expanding outward to press leather-faced shoes against the inner surface of the drum, thus securing the drum and its gear to the shaft. Behind this machinery is the jack shaft with its small differential on the right, 2 laminated rawhide gears meshing with the iron gears on the countershaft, and the internal gear sprockets hanging on the small pinions at either end. A sliding cam bar, mounted nearly in the position of the former shipper fork carriage, is operated by the vertical movement of the tiller handle to engage any one of the 3 clutches. With the tiller depressed, the vehicle is in reverse. Elevating it slightly puts it into low gear, and raising it still higher runs the machine at its highest speed. As the work moved nearer completion, Frank realized that the final tests would have to be conducted on roads made icy by falling snows. He had considerable doubt whether the narrow iron tires would have enough traction to move the phaeton. Soon he devised an expedient for this situation, communicating to Charles on December 22nd that he was having Jack Swain, a local blacksmith, make a couple of clutch rims so we can get over the snow and ice. Our detachable rims referred to will be of 1/8 inch iron, 1 3/4 of an inch wide, and drawn together at one point by 2 screws, one on either side of felloe. It will be studded with cocks in 2 rows. January 18th, 1894 was a day of triumph for Frank Duryea. Writing Charles about his success the next day, he said, "Took out carriage again last night and gave it another test about 9 o'clock. The only difficulty, he mentioned, was a slight irregularity in the engine, caused by the tiny leather pad in the exhaust valve mechanism falling out." Speaking of this trip, Frank recalled in 1956, "When I got this car ready to run one night, I took it out, and I had a young fellow with me. I thought I might need him to help push in case the car didn't work. We ran from the area of the shop where it was built, down on Taylor Street. We started out and ran up Worthington Street Hill, on top of what you might call the Bluff in Springfield. Then we drove along over level roads from there to the home of Mr. Markham, who lived with his son-in-law, Will Bemis, and there we refilled this tank with water. At this point he was asked if it was pretty well emptied by then. Yes, I said in my account of it, that when we got up there the water was boiling furiously. Well, no doubt it was. We refilled it, and then we turned it back and drove down along the Central Street Hill and along Maple Street, crossed into State Street, dropped down to Dwight, went west along Dwight to the vicinity where we had a shed that we could put the car in for the night. During that trip we had run, I think, just about 6 miles, maybe a little bit more. That was the first trip with this vehicle. It was the first trip of anything more than a few hundred yards that the car had ever made." Now Frank could give demonstration rides with the motor carriage, hoping to encourage more investors to back future work. Cautious Mr. Markham finally got his ride, though Frank had to assure him that the engine of the brakeless vehicle would hold them back on any hill they would descend. The carriage on which he had spent so many hours was to see little use after that. Its total mileage is probably less than 100 miles. Little additional work is known to have been performed on the carriage after January 1894. There is, however, a letter Frank sent his brother on January 19th, which tells of contemplated muffler improvements. Another message was dispatched to Charles on March 22nd, mentioning the good performance of the phaeton on Harrison Avenue Hill. This was possibly the last run of the machine, for no further references have been discovered. Frank spent the months of February and March in preparing drawings, some of which accompanied their first patent application, while others were used in the construction of an improved two-cylinder carriage. Work on the new machine started in April. The old phaeton, in the absence of used car lots, was put into storage in the Bemis barn. Later, on the formation of the Duryea Motor Wagon Company in 1895, it was removed to the barn of D.A. Reed, treasurer of the company. There it remained until 1920, when it was obtained by Inglis M. Upercu and presented to the U.S. National Museum. End of Section 2. Section 3 of Smithsonian Institution, United States National Museum, Bulletin 240. Contributions from the Museum of History and Technology, papers 34 through 44 on science and technology, by Museum of History and Technology, United States. This LibriVox recording is in the public domain. Paper 34, Part 3. The 1893 Duryea Automobile in the Museum of History and Technology. Text of article from the Springfield Evening Union, September 16, 1893. No use for horses. Springfield mechanics devise a new mode of travel. Ingenious wagon now being made in this city for which the makers claim great things. A new motor carriage, which, if the preliminary tests prove successful as is expected, will revolutionize the mode of travel on highways, and do away with the horse as a means of transportation, is being made in this city. It is quite probable that within a short time one may be able to see an ordinary carriage, in almost every respect, running along the streets or climbing country hills, without visible means of propulsion. The carriage is being built by J. F. Duryea, the designer, and B. F. Markham, who have been at work on it for over a year. The vehicle was designed by C. E. Duryea, a bicycle manufacturer of Peoria, Illinois, and he communicated his scheme to his brother, who is a practical mechanic in this city. The propelling power is furnished by a 2-horsepower gasoline motor situated near the rear axle, and which, when started, runs continuously to the end of the trip, notwithstanding the number of times the carriage may be stopped. The speed of the motor is uniform, being about 500 revolutions a minute, and is so arranged that it gives a multiplied power for climbing hills, and the lower the rate of speed, the greater power is furnished by the motor. The slowest that the carriage can be driven is 3 miles an hour, and the speed can be increased to 14 or 15 miles an hour. The power is transferred from the driving wheel of the motor, which runs horizontally with the main shaft, by an endless friction belt running on a drum wheel. The belt is controlled by a lever within easy reach of the driver, and is shifted along the drum wheel to increase or decrease the speed. The driving wheel is about 20 inches in diameter, having in its center a depression to which the belt is shifted to stop the carriage. The carriage can be reversed by shifting the belt from the end of the drum, which gives the forward motion to the opposite side, beyond the depression in the driving wheel. The power which has been transferred to the driving shaft from the motor is in turn transferred to the 2 rear wheels of the carriage by a combination gear and sprockets. An endless chain connects the sprockets on the carriage wheels to the sprocket wheels on the driving shaft. All of the motive power is located under the body of an ordinary phaeton, the height of which is not increased by the machinery. The motor is started by a crank, which is easily applied to a shaft in the rear of the carriage, and the gasoline is ignited in the cylinder by electricity. An automatic device stops the flow of gasoline into the cylinder when the motor ceases running. The gasoline is carried in tanks, which hold about 2 gallons, and which will run the carriage for about 8 hours. The wagon is guided by a bicycle bar, and the speed is also controlled by this bar. The method employed in this is as follows. To start the carriage, press the lever down. To reverse it, throw the lever up. And to guide the wagon, turn the lever either to the left or right. The front axle, instead of turning horizontally, plays up and down, in order that the machinery may be on a level with the rear wheels, while the front wheels are set on the axle by a pivotal joint and are connected with the guiding lever by bars with ball bearings. The carriage complete weighs about 220 pounds, and the essential features are already covered by patents while others are pending. It is estimated that the carriages can be sold for about $400, and a stock company will probably be formed to manufacture them. End of Section 3. Section 4 of Smithsonian Institution, United States National Museum, Bulletin 240. Contributions from the Museum of History and Technology. Papers 34 through 44 on Science and Technology by Museum of History and Technology. This LibriVox recording is in the public domain. Paper 35, Part 1. The Borghesi Astronomical Clock in the Museum of History and Technology by Silvio A. Bedini. The history of the 18th century Borghesi astronomical clock is described here from contemporary source material. The evolution of its design by Father Francesco Borghesi and the building of the complex mechanism devised by the clockmaker Bartolomeo Antonio Bertolla is the story of the vision of one man turned into reality by another. The result of their collaboration is the unique astronomical timepiece now in the Museum of History and Technology. The author, Silvio A. Bedini, is a curator of mechanical and civil engineering in the Smithsonian Institution's Museum of History and Technology. All this work I had performed eagerly, so that while in my room I might contemplate leisurely, both during the day and in the night, the true face of the heavens and of the seas unobscured by clouds, even though I had no astronomical equipment. With these words, Father Francesco Borghesi, 1723 to 1802, of Mechel, described the reasons which inspired him to invent a unique astronomical clock which is now in the horological collection of the Museum of History and Technology. This complicated mechanism, which performs a multitude of functions, was designed by Father Francesco Borghesi, a secular priest in Venetia Tridentina. It was constructed in 1764 under his direction by a provincial clockmaker named Bartolomeo Antonio Bertolla, 1702 through 1789, of Mocenigo di Roma. It was the second of two complicated astronomical clocks which Father Borghesi designed and which Bertolla constructed. According to contemporary sources, this clock was presented to the Empress Maria Theresa of Austria soon after its completion. Its history is rather hazy, except for the fact that in 1780 this second Borghesi timepiece was still in the Imperial Palace in Vienna. The clock was again noted in 1927, when it was sold at a public auction in New York. Subsequently, it was acquired for the Smithsonian Institution. Development of astronomical clocks. The history of the great theoretical and mechanical achievement which the Borghesi clock represents has been most adequately covered elsewhere. Consideration of the development of equation and astronomical clocks is required here only for the purpose of relating the Borghesi timepiece with the other significant developments in this branch of horology. The invention of the anchor escapement in about 1670 and the consequent greater accuracy in time-telling led to increased preoccupation with precision. Daily differences in time, as recorded by sundials and clocks, became more noticeable. Finally, in the second half of the 17th century, some attempt was made to construct mechanical clocks combined with sundials as well as astronomical clocks. With the improvement of precision time-telling, it became necessary to reconcile the actual difference between true and mean time. Although a great variety of time equation tables were produced, there was a considerable margin for error in their use. This led to the construction of mechanical clocks in which the equation of time was automatically accomplished. A few were produced late in the 17th and early 18th century at considerable cost, and consequently with little popularity. Equation sundials were also developed, which were elaborately ingenious, but they were not completely practical. Inevitably, they were supplanted by the mechanical equation clock. Probably the first documented mention of an equation clock is in the diary of John Evelyn, who recorded that in 1666 he visited the Royal Society where he witnessed a curious clock, which showed the equation of time being presented by a certain Mercator. More data on the subject appeared in the first 2 decades of the 18th century, when Henry Sully, Joseph Williamson, Daniel Quarry, and Thomas Tompion, who were among the foremost English clockmakers of all time, produced elaborate examples of these timepieces. Another significant maker was Doe Williamson, who became court clockmaker to Emperor Charles VI of Austria. In London, Joseph Williamson produced one of the finest astronomical timepieces of this type that have been known. The interest in the subject next shifted to France, where many fine examples were produced during the first half of the 18th century. Just after the middle of the 18th century, the subject of astronomical clocks suddenly became a major horological preoccupation in another region, namely Austria, where the work in this field was apparently done exclusively by members of the clergy. The earliest was Father Philip Matthaus Hahn, 1739 through 1790, of Württemberg. Father Hahn considered the equation of time as only one part of a plan, to represent astronomical occurrences by means of clockwork. In addition to planetaria and similar mechanisms, Father Hahn produced 2 extraordinary astronomical tall-case clocks, both of which survive in public museums. Another of the clerical clockmakers was Father Aurelianus a Sundinial, 1728 to 1782, an Augustine monk in the monastery of the Imperial Court at Vienna. His 4 complicated astronomical clocks, which exist in museums at present, are comparable to those produced by Father Hahn. The third cleric was Brother David a San Cayetano, 1736 to 1796, in the same Augustine order to which Father Aurelianus belonged. He achieved note as the author of various publications, including Neue Redegebäude, New Construction of Wheels, relating to planet wheels or gear trains containing epicyclic elements. He constructed a clock based on an elaborate astronomical design which was substantially different from the others. The fourth of the ecclesiasts who designed astronomical clocks in this period was Father Klein of Prague, who produced a complicated astronomical timepiece in about 1738. The fact that such important and outstanding examples of astronomical clocks were produced exclusively by ecclesiasts in Austria during the second half of the 18th century is especially significant. It is particularly so when a 5th cleric is added to the group, also an Austrian subject, although Italian by heritage, in the person of Father Francesco Borghesi. Although only Father Borghesi's 2nd astronomical clock is now known, it is apparent that this example in the Museum of History and Technology represents an experiment in astronomical time-telling comparable to any of the timepieces produced by Father Hahn, Father Aurelianus, Brother David a San Cayetano, or Father Klein. This combination of 5 clerical clockmakers who lived in the same region during the same period of time is sufficiently unusual. However, the fact that each of them apparently worked without association with any of the others leads to the conjecture that a common factor must have led them to their individual preoccupation with astronomical horology. What the link may have been is not apparent from the surviving records of the lives and works of these clerics. Certainly it was not an interest in astronomy or clockmaking per se, because other than the astronomical clocks, none of these horological inventors, with the possible exception of Father Hahn, worked in any other aspect of the fields of astronomy or horology. However, after a comprehensive study of Father Borghesi's writings, there is little doubt of the religious basis of his own inspiration. Designer Borghesi. Father Borghesi's story takes place in the picturesque mountainous region of what was then known as Venetia Tridentina, since 1947, Trentino Alto Adige, in northern Italy, along the Tyrolean border of Austria. Because of its strategic position as the passage between Innsbruck and Verona, the possession of the Tridentina was contested again and again in the European wars. But during Father Borghesi's lifetime, the Tridentina was under Austrian domination. Deep within this mountainous district is the romantic valley of the Non, or Anauni, with its great forests and ancient castles. Most maps do not mark it, and the tourist guides ignore it. One of the chief communities is Cles, with its historic Renaissance buildings. The major city of the region is Trent, on the Adige River, with its surviving Roman relics and Romanesque and Renaissance architecture. The little villages scattered throughout the valley of the Non played no part in history, but such names as Michel and Mocenigo di Rumo reflect the interchange of sovereignty. It was in the little village of Michel that Francesco Borghesi was born in 1723. Local records are meager and inadequate, and many of the details of Borghesi's life must be assumed. Inasmuch as the village was in a rural, agricultural district, Borghesi may have come from a family of farmers, vintners, or village tradesmen. Borghesi sought an education by entering the priesthood, and was ordained a secular priest in Salzburg. He was first assigned as curate to the village parish of Rumo in the valley of the Non, a short distance from his birthplace. Later he was transferred to his native Michel. He was inherently a man of simple tastes and of great piety. He tended to the needs of his mountain villagers and attended the births, weddings, and deaths of his parishioners. It was during his assignment in this tiny community that Father Borghesi met and became friendly with the clockmaker Bartolomeo Antonio Bertolla of nearby Mocenigo di Rumo. Clockmaker Bertolla. Bartolomeo Antonio Bertolla was born in Mocenigo di Rumo, a short distance from Michel, in 1702. Nothing is known of his boyhood, other than the fact that he was mechanically inclined. At the age of 17, he was apprenticed to become a clockmaker, with the master, Johann Georg Bootsjäger, of Nugelenbach, a small village on the edge of the Great Vienna Woods. This region was then part of the domain of the Archduke of Austria, of which St. Pölten was the capital. Bertolli began his apprenticeship with Bootsjäger under the auspices of the Corporation of the Blacksmiths of St. Pölten in 1719. His training was supervised by two master locksmiths, Johann Christian Vince and Peter Wisshaffer, who were members of the corporation and were assigned to serve as patrons for the apprentice. It was their obligation to make certain that he received good care and adequate instruction from his master. While he worked in Bootsjäger's shop, Bertolla lived with the master's family in their home. Bertolla's 3 years at Nugelenbach passed quickly, as he sought to absorb all that his master could teach him. Bootsjäger was considered to be a good craftsman in the region, yet today there is not even a mention of his name in the lists of clockmakers. He specialized in the production and repair of great clocks, which included tall case, domestic timepieces, and tower clocks. Bootsjäger treated his apprentice well, and in return Bertolla rewarded him by being diligent and honest. His subsequent work is sufficient indication that he developed into an extremely skilled craftsman, and he became the equal of any clockmaker of his time. The 3 years of apprenticeship were completed, and on December 27, 1722, Bertolla received a certificate from the Corporation of Blacksmiths, which assured whomever it might concern of Bertolla's skill, diligence, and honesty, and permitted him to open his own shop as a clockmaker under the auspices of the corporation. This document, which has been preserved by Bertolla's descendants, is an interesting record of the organization of the trade guilds in the 18th century, and for that reason has been translated from the original German, We, the superiors and other masters of the Honorable Corporation of Municipal Blacksmiths, Armorers, and of Smiths in the imperial city of St. Pölten in Austria, by the river Enns, declare by these presents put in force by this document to anyone who waits to hear, that the Honorable and able Bartolomeo Antonio Bertola of Rumo in Letzenburg, the Tyrol, on the 27th day of the month of December of the year 1719, was consigned as apprentice for 3 years, in the presence of 2 sponsoring masters for the purpose, the Honorable Johann Christian Vince and Peter Wisshofer, both of them master locksmiths, representing the entire Honorable Corporation and others of open shop, to the Honorable Johann Georg Butzjäger, incorporated with us, citizen and master clockmaker for large clocks in the merchant village of Neuglenbach in Wienerwald, and his master of the art would have therefore perfectly and rightfully worked and learned, and that afterwards, on the day and year noted at the bottom, he will be newly declared free and independent before us, representative of an entire and honorable corporation, and with open shop of his above-mentioned master, of the 2 sponsoring masters mentioned, and, since he eagerly requested a truthful certificate of apprenticeship for his honest service as an apprentice, and for his good behavior, and we having great pleasure as well as the duty of favoring the truth and well knowing that the aforesaid Bartolomeo Antonio Bertola has learned honestly the art of clockmaking for great clocks from his aforesaid master, and that he has always behaved with honesty, obedience, faithfulness, and diligence, both toward his master and toward us to our complete satisfaction, and therefore we cannot in any manner refuse his request, rather we wish to grant it with clear conscience. We, therefore, address to everyone and to anyone in whatever state and rank, but particularly to those interested in our branch of this art, our respectful and courteous entreaty and request to consider Bartolomeo Antonio Bertola well recommended for his honest apprenticeship and his good behavior, and to desire to favor him in every way, in such a manner that will assure our gratitude whenever an occasion presents itself. For this purpose, we issue, as we have declared we wish to issue to you, Bartolomeo Antonio Bertola, this certificate of apprenticeship, attaching to it the seal of our corporation, executed in the city of St. Pölten on 27 December 1722. His apprenticeship over, Bertola returned to his native region, where he soon established a reputation for himself as one of the most skillful clockmakers in the Tridentina, and produced timepieces of fine quality in some quantity. No records have survived concerning his personal life, but it is believed that he married probably soon after his return. He had no children of his own. To expand his business, he eventually took into his shop 2 nephews, the sons of a brother and a sister, as apprentices. Bertola's work brought him a sufficient number of clients, and he produced elaborate clocks for his more wealthy patrons. In 1752, it is recorded that he repaired the great clock in the campanile of the Church of the Assumption of the Virgin Mary in Cles, the regional capital of the Valley of the Nan. The clock dated probably from the 16th century, and it seems likely that Bertola replaced the original 2-wheel train with a 3-wheel movement, and that he added the present anchor escapement. It is not possible to determine when Father Borghesi first made Bertola's acquaintance, but it may be assumed that they had become friends in the late 1750s. After he had come to know Bertola, Father Borghesi apparently spent many hours in the clockmaker's shop. He was fascinated by mechanics in any form, and the complications of clockwork particularly intrigued him. Bertola was patient with the young priest, explaining the tools he had and their uses, the clocks he produced or repaired, and the principles which were involved. Father Borghesi listened willingly, and as his understanding of timepieces grew, his curiosity increased. In spite of himself, the priest could not be satisfied with the ordinary aspects of his friend's work and wanted to learn more. From a casual pastime, the study of time became an obsession with him. There was but one recourse. He went back to studying once again. This time it was not theology, however, but the sciences. Every moment he could spare went into the perusal of books on mathematics, astronomy, and associated subjects. He progressed rapidly, driven by his overpowering interest and aided by his quick intellect. Little by little, Borghesi managed to acquire the basic texts that explained this new world to him, probably borrowing them from old seminary friends. As each new book came into his hands, he devoured it in his desire to master its contents. He discussed each new principle or precept that he learned with Bertollo. Together they attempted to apply his new learning to the calculations necessary for a timepiece which would demonstrate the astronomical theories in visual form. Borghesi taught himself slowly, step by step, and the result was a profound understanding of astronomical science. He conceived the project of constructing a great astronomical clock which he felt could be accomplished by combining Bertollo's mechanical skills with his own recent mastery of astronomy and mathematics. End of section 4. Section 5 of Smithsonian Institution, United States National Museum, Bulletin 240. Contributions from the Museum of History and Technology, papers 34 through 44 on science and technology, by Museum of History and Technology. This LibriVox recording is in the public domain. Paper 35, Part 2, The Borghesi Astronomical Clock in the Museum of History and Technology, by Silvio A. Bedini, Part 2. First Borghesi Clock. It is not difficult to visualize the two men, the priest and the clockmaker, as they sat together night after night working out their plans. Father Borghesi would painstakingly outline the astronomical principles he wished to have the clock exhibit, and the mathematical principles which would be involved to operate them. Bertollo concentrated on them, and tried to transcribe the principles into functional mechanical terms, visualizing each operation in terms of wheels and gears. Little by little, the two men coordinated the numerous elements and welded them into an operating entity. They adjourned either to the stark simplicity of the rectory, or, probably more often, to Bertollo's little home workshop, the priest standing over his friend, while the latter worked at his bench in the dark-paneled interior, illuminated only by the several lamps on the workbenches. This first clock, which the two men combined to create, is a monument to the great scientific knowledge of the self-taught priest and the technical ability of the clockmaker, a unity combining astronomical science, mechanics, and artistry. The story of the project is told in a little book, Novissima ac Perpetua Astronomica, which Borghesi later published. Explaining the incentive which inspired him, and the premise from which he began his work, he wrote, "From the foundation of astronomical science long ago, innumerable and repeated observations of both ancient and modern astronomers emerged at last from their hiding places, made light of by the jests of so many outstanding intellects. They have so successfully brought to light the paths of the stars and their motions, which are more complicated to us than the Gordian knots. Now it is possible for even an amateur in astronomy, sufficiently instructed, to predict for any given time not only the mean positions of the planets, but also their true longitude and latitude, and even the true time of their conjunctions, and their ecliptic oppositions with all the attendant circumstances. Yet until now, no hypothesis has been devised which would force an automation to show to us, before our very eyes, the eclipses of the planets in their true and certain times. For though there have been men seeking with all their might to bind by laws their artificial heavens, by I know not how many and how great calculations, and to systemize the complexities of the rotations of celestial bodies, nevertheless, all of them, as if by common agreement, consider themselves to have made great contributions to mechanico-theoretical astronomy. However, they have only attained, even though closely, the mean locations of the secondary mobiles, and those by a certain rather crude calculation. Some attained by more, some by less, but all by some degree of wandering from the truth, either worn out by the intricacies of the motions, or deceived and deceiving by the errors of their calculations. This fact those well know who, setting about to collect information of this kind, even those publicized not long ago, with true astronomical calculation, have been bored to death while digging out by the most elementary and superficial arithmetical torture the worst of fallacies spontaneously erupting from thence. It would seem that true calculations alone can be desired in mechanico-astronomics. Long study had not only convinced me that an automaton was within the realm of possibility, but that there were many mechanical systems by which it could be achieved. I girded myself for a new project, and developed it theoretically, from the ground up, but under such unhappy auspices that not only did all hope fail that anyone would ever appear who might have seemed willing to set his hand to the work, but that the new discovery itself was scoffed at by many as altogether a nightmarish delirium of unbridled imagination. The first months of the project must have seemed like an inspired dream to the two men, and then must have followed a period of hopeless depression. Bartola undoubtedly felt many times that the clock was an aspiration far beyond their combined abilities and means, but the priest would not be thwarted in his ambition and refused to abandon the project. He felt that it was a work that they were destined to produce. Many times he wrote, he chided and begged and shamed his erstwhile partner into resuming the project where it had been last abandoned. Little by little the first clock began to take form. As each new difficulty was encountered, the two men would go back over the notes and sketches to trace the problem to its source. Often a new part of the mechanism would nullify another, which had thus far operated successfully, and a complete rearrangement would be required. Again and again Bartola threw up his hands in despair and begged Father Borghesi to abandon the enterprise. He protested that he was not capable of producing such a complicated mechanism. He had neither the tools nor the skill. The priest wished to produce a clock such as the world had never seen before, such as the greatest scientists and clockmakers of all time had never been able to make. But Bartola felt that he was only a provincial craftsman who could not hope to surpass them all with only his simple tools and training. In his book on the first clock, Novissima ac Perpetua Astronomica, Father Borghesi wrote that when he had finally come within a few weeks of the embryo stage in the development of his clock, he was faced with the problem of bolstering the sagging enthusiasm of Bartola. The clockmaker's original enthusiasm had shown promise of great results, but as the days passed and the problems of the multiplex and generally unfamiliar apparatus to be forged for the workings of the automaton became more complex, his ardor decreased. Finally, Bartola became so discouraged by the scoffers and frustrated by the fact that the work was insufficiently organized that Father Borghesi wrote that it almost became a harder task for me to bolster up by daily opportunity and importunity the failing patience of the artisan, frightened away from the work already begun, that it was for me to extract from the inner recesses of mathematics and astronomy, without light and without a guide, the whole fabric of the machine itself. In spite of Bartola's protests, Father Borghesi prevailed, reviving his friend's interests once more until the two were deep in the project again. Months passed as they worked together on the mechanism, and it seemed as if they lived for no other purpose. Inevitably, Bartola's health began to suffer, undermined as it was by the constant nervous tension, and he eventually became ill from mental strain. He was forced to spend some time in bed, and for many weeks the subject of the clock was not discussed. Bartola's other work, by which he made his living, suffered, and it was several months before he was able to return to his little shop. 1 year passed into another, and the work progressed slowly. The first clock, which easily should have been finished in less than a year, was not completed until after 3 full years had passed. However, when the priest and the clockmaker put the finishing touches on their great clock, the result surpassed the greatest possible expectations, for it was truly a masterpiece. Not only did it illustrate the ecliptic phenomena of the moon, the sun and earth occurring in their proper time, as well as many other things, but it showed these operations as they succeeded in proper order, taking place through the centuries. With mutual feelings of great pride, The two friends surveyed the results of their 3 years of endeavor. Bertollo realized that he had reached a point of maximum achievement in his work. He probably felt now that he could relax again, that his sleep would no longer be troubled by confused nightmares of wheels and gears that did not mesh together. Time was to prove otherwise. Published description of the first clock. Father Borghesi soon came to the conclusion that it would be desirable to have a written description to explain the mechanism of the clock and its many indicators. He thereupon wrote out the story of how the clock was made, the reasons for embarking on the enterprise, the difficulties he had encountered, and the success which had crowned his and Bertollo's mutual labors. Finally, he described the operation of the clock's mechanism and the functions of its array of indicators. The little book was written in Latin, and only a few copies were printed, presumably at the priest's own expense, on a hand press by Giovanni Battista Minoni, printer to the bishop in Trent. The little volume was stated by contemporary writers to have been published in 1763, although no date appears on the title page. The title, translated, is in part the most recent Perpetual Astronomical Calendar Clock, Theoretical, Practical. The work begins with an introduction for the reader in which Father Borghesi stated, "The little work, which as far as I was concerned could easily have been finished in a year, was only completed after about 3 years. Fortunately, however, it was so far beyond the expectations of most that not only am I able to foretell with certainty all the lunar ecliptic phenomena and the solar, or rather terrestrial phenomena, carefully worked out in their true periods, among many other matters exhibited by the machine, but also, within a few hours, I can exhibit, by altogether tangible evidence to the skeptics and the doubting, those very same phenomena occurring within the space of many years, or even centuries, and succeeding one another in proper order with their many attendant circumstances. I was not much concerned about the other eclipses, such as those of Mercury, Venus, and the other stars wandering through the zodiac, or about the other solar eclipses from the transit of Mercury or Venus, since they are altogether undiscernible to the naked eye, and very few compilers or ephemerides wish them to be noted, probably for the same reason. Do not, however, expect, star-loving reader, that here anything at all that you may wish can be drawn forth as from its source. For to demand this would be almost the same as to seek to drain, as from a cup, all the vast knowledge of the many arithmetical sciences from the narrow confines of one book. You will understand how impossible that is when, through prolonged labor, you have grown somewhat more mature in this kind of learning. Wherefore, rather fully, and out of consideration for you, I have decided, setting aside these prolixities, with completely synoptic brevity and with all possible clarity, to expound for you simply the proportion of the movements, the description of the machine, and its usage. As a result, when you have progressed a little in theoretical mechanics, you will not only be able to reduce all these things to their astronomical principles, but you may find the way more smoothly laid out for you, even for perfecting the machine itself. And thus you may be more effectively encouraged to a successful conclusion. Let it be so now for you through the following 10 chapters. After these rather hopeful assurances, Father Borghesi proceeded to provide a detailed description of the clock dial and functions in the 10 short chapters which he had promised, under a separate section entitled Synopsis Totius Operis Mechanici, which is translated in its entirety in the appendix. As Father Borghesi prepared his little volume about his first clock, and described its unusual features and outlined its functions, which were primarily to place in evidence the celestial constellations, it occurred to him that it would now be easier, after the experience he had acquired with his first timepiece, to construct another clock, which would present the motions of the 2 astronomical systems, the Ptolemaic and the Copernican. In this first book he promised the reader that he would undertake the second project. It is fortunate that Father Borghesi undertook this project for the second clock, is the only example of his work that is known to exist today. Extensive research has not shown what happened to the first clock, although several sources state that both timepieces were presented to Empress Maria Theresa sometime between 1764 and 1780. Father Borghesi lost no time in initiating the project of the second clock. The first and most important step was to inform Bertola and enlist his assistance. Bertola was adamant he had had enough of complicated astronomical movements. He was delighted by the prospect of returning to his former simple life, producing simple, domestic, elementary movements for his country clients. Father Borghesi begged and cajoled. The second clock would be a much simpler one to construct, he persisted. After all, they had gained invaluable experience from the production of the first clock. Furthermore, he had already completed its design. Bertola apparently wavered in his resolve, and, unwillingly and against his better judgment, he allowed the priest's inducements to prevail. Once again, the two friends yielded their leisure hours to a study of the priest's books and drawings, as Father Borghesi enthusiastically elaborated his design for the timepiece, and Bertola attempted to transcribe astronomical indications into terms of wheel counts. The second clock was, as Borghesi had promised, much easier of execution. Within a year it was completed and functioned with complete success. This is the clock now in the Museum of History and Technology. It is housed in a tall case of dark red mahogany, veneered on oak, with restrained carving featuring ribbons and foliate motifs. Gilt brass decorations flank the face of the hood, which is surmounted by 3 gilt brass finials in the form of orbs. A wide door in the waist may be opened to attend the weights. The case is 7 feet, 8 inches high, 20.5 inches wide at the waist, and 14 inches in depth. The dial is of gilt brass, measuring 21 inches high and 15 inches in width, with a number of supplementary silver dials visible through its openings. Instead of hands, the dial utilizes 3 concentric rings moving around a central disc, the indications of which are read at 2 bisecting gilt lines inscribed in the glass face. 12 separate functions are performed by the chapter ring assembly alone, and there are 14 openings on the dial. It is estimated that the clock performs 30 separate functions, including striking and chiming. Of the multiple chapter rings, the outermost is 1 1/8 inches wide, the center ring is 3/8 inches wide, and the innermost ring 1 1/4 inches in width. The dial plate engravings. The gilt dial is incised throughout, with figures and inscriptions in engraving of the very finest quality, as is evidenced in the illustrations. The frontispiece is surmounted at its center by the crowned double eagle of the House of Habsburg, indicating the identity of the sovereign in whose reign it was made, Emperor Francis I, or the Empress Maria Theresa of Austria. Below the eagle at either side are flying cherubs, supporting ribbons with inscriptions. Centered at the bottom of the frontispiece, immediately above the chapter rings, is the moving silvered orb representing the sun. Surrounding it is a tableau of the Holy Trinity, with the Virgin Mary being crowned by Christ, holding a cross at the left, and God with a sword in hand at the right, and a dove, representing the Holy Spirit, hovering over the Virgin's head. Father S.X. Winters, S.J., considers it reminiscent of the triptych The Coronation of the Virgin by Fra Lippo Lippi. In the upper spandrels of the dial are 2 more cherubs, bearing ribbons with inscriptions. In the lower left corner is a magnificent engraving of Atlas, upholding the globe of the world, inscribed with the zodiac over his head. The lower right corner features the figures of 2 noblemen apparently examining and discussing an orb upon a table, the significance of which is not clear. The inscriptions. Beginning with the uppermost part of the frontispiece, there are 9 inscriptions in Latin on the dial plate. The topmost is Franciscus I sit plan, Dominator Aeternus. The phrase has reference to Francis I, who was Emperor of the Holy Roman Empire from 1745 to 1765, and husband of Empress Maria Theresa of Austria. The phrase may be translated as May Francis I be the eternal ruler by favor of the planets, or more simply, long live Francis I, Emperor. Although the dial plate of the Borghesi clock is inscribed with his name, the records indicate that the clock was presented to Maria Theresa. Francis I may have already died before the presentation was made. From the left to the right, over the tableau of the Holy Trinity, is the phrase La Sacrosancte Triade Uni Deo et Dea Pare. Praise be to the most Holy Trinity, to the one God, and to the Mother of God. Within the upper left and right spandrels is inscribed Isteic, Signum Grande Apparuit in Coelo, Sancta Die Genetrix Amicita Sole, Illibato Pede Lune, et Serpentis Nigra Premens Conva, bis senis pulcherime coronata sideribus, tempe indiscenita clausa scatoriga signata, cedrus in Libano, cypressis in Monte Sion, mata pure delectionis sancticu spie, chara patris aeterni proles, verbi mata sponsecure precedentis, gratiae et gloriae circumdata varietate. This inscription is a eulogy to the Virgin Mary, assembled from the texts of Holy Scripture. In addition, each lemma contained within asterisks carries out the chronogram 1764, the year the clock was completed. Each lemma is translated and identified from the Duryea Reims version of the Bible. This woman, a great sign appeared in heaven. Apocalypse chapter 12, verse 1. The Holy Mother of God, clothed with the sun. Apocalypse chapter 12, verse 1. And with unharmed foot, crushing the black horns of the moon. Apocalypse chapter 12, verse 1. And the serpent. Genesis chapter 3, verse 15. Most beautifully crowned with twice 6. Apocalypse chapter 12, verse 1. A garden, tempe, enclosed, sealed with a fountain spring of water. Song of Songs, chapter 4, verse 12. Like a cedar in Lebanon and a cypress tree in Mount Zion. Ecclesiasticus, chapter 24, verse 17. Mother of pure love and of holy hope, beloved daughter of the eternal Father, mother of the world, spouse of the Holy Spirit. Ecclesiasticus, chapter 24, verse 24. Surrounded with a diversity of grace and glory. Psalms, chapter 44, verse 10. At the lower left corner below the figure of Atlas upholding the world is the phrase Assiduo prone donanti conta labori. The favorable gods willingly grant all things to the assiduous laborer. The same phrase is quoted by Father Borghesi in the text of his second volume. The last inscription appears at the lower right corner under the figures of the two noblemen. Diligit audaces trepidos fortuna repellet. Fortune favors the daring and rejects the timid. The last two inscriptions are in dactylic hexameter. They appear to be original compositions, inasmuch as no classical prototypes have been identified. Center dial inscriptions. In addition to the inscriptions previously noted on the outer dial plate, there are 3 major inscriptions in the central dial. The outermost states Circulus Horarius Sole, Lune, Fixus, Nodus, Stuici Marino Communis. The hour circle, common to the sun, the moon, the fixed stars, the nodes, and to the sea tide. This inscription is divided into 4 parts by the insertion of 4 divisions for the day into canonical hours: Horae, Nocturnae, night hours; Matutinae, morning hours; Diurnae, daytime hours; and Vespertinae, evening hours. The next section of the central dial is inscribed Intumiscite, Detumiscite, rise and fall of the tides, repeated at intervals of approximately every 6 hours. Within the next section is the following inscription, inscribed continuously around the ring. Lege fluent, re fluent, dormitant hac maris undae, et Phoebe et Phoebus concordia isua moventur aquora, discordi iusu suspensa quiscunt. Translated, this is, by this law, the sea waves ebb and flow and lie dormant. When Phoebus and Diana agree in their commands, the waters are moved. When they disagree, the waters lie silent. Within the central boss of the dial plate, the name of the maker is inscribed. Borghesi Doctore et Bertola Limatore Ananiensibus. Translated, this is by Dr. Borghesi and Bertola, mechanician citizens of Anagni. Indicators in the frontispiece. There are 12 windows in the frontispiece, through each of which appears an indication relating to time. Beginning at the top of the frontispiece of the dial, the first opening occurs on the breast of the imperial eagle. This indicates the dominating planet, represented by its symbol and its house. The opening in the eagle's left claw, labeled Lit Dom, is the dominical letter. The first 7 days in the month of January are each assigned one of the letters A through G in order of appearance. The letter which coincides with the first Sunday within this period is called the dominical letter, and it serves for the following year. In leap year, 2 letters are required, one to February 29th, and the letter next preceding for the remainder of the year. This letter is used in connection with establishing the date of Easter Sunday. The date of Easter regulates the dates of the other movable feasts. The eagle's right claw is labeled capital C, YC, period, capital E, lowercase p, capital E, capital C, and represents the epact, or the age of the moon on January 1st. It serves to find the moon's age by indicating the number of days to be added to each lunar cycle in order to complete a solar year. 12 lunar months are nearly 11 days short of the solar year, so that the new moons in one year fall 11 days earlier than they did the preceding year. However, 30 days are deducted as an intercalary month, since the moon has made a revolution in that time, and the remainder, 3, would be the epact. Below the imperial eagle, 2 winged cherubs support a riband with 3 indications of the Julian period. This period of 7,980 years is the product derived from multiplying together the sums of 28, which represents the cycle of the sun, 19, representing the cycle of the moon, and 15, which represents the Roman indiction. The Julian period is reckoned to have begun from 4713 BC, so that the period will be complete in AD 3267. The first of the 3 openings is marked capital IND period, capital ROM period, or Roman indiction, which is an edict by the Emperor Constantine in AD 312 providing for the assessment of a property tax at the beginning of each 15-year cycle. It continues to be used in ecclesiastical contracts. The second opening, which occurs immediately below the eagle, is marked capital CYC period, capital SOL period, cycle of the sun. The cycle takes a period of 28 years, after which the days of the week once again fall upon the same days of the month as they did during the first year of the former cycle. There is no relationship with the course of the sun itself, but was invented for the purpose of determining the dominical letter, which designates the days of the month on which this Sunday occurs during each year of the cycle. Since cycles of the sun date from 9 years before the Christian era, it is necessary to add the digit 9 to the digits of the current year and then divide the result by 28. The quotient is the number of cycles which has passed, and the remainder will be the year of the cycle answering to the current year. The third opening on the riband is labeled capital NUM period, capital AUR period, the golden number. Meton, an astronomer of Athens, discovered in 432 BC that after a period of 19 years, the new and the full moons returned on the same days of the month as they had before, and this is called the cycle of the moon. The Greeks were so impressed with this calculation that they had it inscribed in letters of gold upon stone, hence the golden number. The First Council of Nicaea in AD 325 determined that Meton's cycle was to be used to regulate the movable feasts of the church. Immediately above the chapter rings is an opening through which the orb of the sun is visible. The Chapter Ring Assembly. In a separate chapter in his second volume, entitled Descriptio Automatis, Summa Totius Operis Mechanici, Description of the Automaton, Summary of the Complete Mechanism, Father Borghesi provided a description of the functions of the various indicators, prefixing it with the short poem shown in Figure 18. He then continues, in the middle of the frontispiece, as at the center of the universe, The terraqueous globe of the week revolves, with a daily motion turning from right to left, bringing with it, from the round window, the coming day, and at the circumference the circle of hours common to the sun, to the moon, to the fixed stars, to the head and tail of the dragon, and to the raging sea. The second circle revolves the synodic periodic measure of the raging sea, the days of the median lunar synodic age, the signs and individual decrees of the signs of the distance of the moon from the middle of the sun within the time of 29 terrestrial revolutions. Hours 12.44.3.13. This circle revolves likewise from right to left around the center of the earth. In this second circle, another little orb revolves, bringing with it the epicycle of the moon, in which the little circle of the moon, whose illuminated middle always faces towards the sun, running from left to right through the signs of the anomaly, within 13 revolutions of the earth, hours 18.39.16. It descends from apogee to perigee, and in just as many others it returns from perigee to apogee to be carried down thus to true, back and front from the longitude and distance from the sun and from the middle of the earth. The third cycle, on which I have tried to indicate astronomically, geometrically, in their places, the degrees of lunar latitude both in the south and in the north, and some fixed stars, those, namely, which can be separated by us from the moon, which goes between, from left to right, turns around the center of the earth, stretching out the head and tail of the dragon, on the inside above the second circle, for noting and measuring the sun, but I should rather say the earth, and the eclipses of the moon, within 346 revolutions of the earth, hours 14.52.23. The fourth circle, in which the heaven of the fixed stars, reduced to the correct ascent of our times, the signs of the zodiac, and the individual degrees of the signs, the months of the year, and the single days of the month can be seen, likewise makes its journey around the earth from left to right in 365 terrestrial revolutions, hours 5.48.56. That is, with a median astronomical year. Above this annual orb, the sun, in its small epicycle, gliding through the 12 signs of the anomaly within the space of 182 terrestrial revolutions, hours 15.6.58, from left to right, falls from apogee to perigee, and within the same time rises from perigee to apogee, and brings with it the index, namely, its central radius, inhering to the axis of the equatorial orb and cutting the 4 greatest circles from the center. When the sun has been moved around, Iris shows from 6 windows the era, that is, the current year. 2 winged youths take their place next to Iris, carrying the Julian period, namely the Roman indiction, the cycle of the sun, and the golden number, on a leaf of paper held between them. The imperial eagle stands out on top, as if added to the frontispiece, carrying on its breast the dominating planet and its talons, the ecclesiastical calends, that is, the Dominical letter and the epact. End of section 5. Section 6 of Smithsonian Institution, United States National Museum, Bulletin 240. Contributions from the Museum of History and Technology. Papers 34 through 44 on Science and Technology by Museum of History and Technology. This LibriVox recording is in the public domain. Paper 35, Part 3. The Borghesi Astronomical Clock in the Museum of History and Technology by Silvio A. Bedini. Attachments for adjustment. 2 attachments in the form of small superimposed dials are situated at the base of the dial plate at either side and immediately below the 4th chapter ring. In his second volume, Father Borghesi stated that they are not moved from inside the clock, but the one at the right, inscribed concitat and retardat, serves for loosening, accelerating, and tightening, retarding, time, that is, the reins of the perpendicular. In other words, the purpose of this attachment is for adjusting the pendulum to make the clock operate fast or slow. The second attachment, which appears on the left, and which is inscribed Claudit, close, and Apparit, open, serves the purpose of preparing the mechanism in a moment as swiftly as you wish for sustaining the astronomical experiments of which you will hear later. When these things have been done, it restores the mechanism to its natural motion at the same speed. This adjustment relates to the final section of Father Borghesi's second book, entitled Chronologo Astronomicus Usus Automatis, Chronological Astronomical Use of the Automaton, which is translated from the Latin in its entirety. With one glance at this automaton, you can quickly answer these questions. What hour the sun shows, the moon, any fixed star, the head and tail of the dragon. Is the sea swelling with periodic heat at high tide, or is it deflated, low tide, or quiescent? How many days is it from nean new moon, or full moon? By how many signs and degrees is the moon distant from the sun, and from its nodes? What sign of the zodiac does the sun occupy? The moon, the head and tail of the dragon. Is the sun or the moon in apogee or perigee, ascending or descending? What is the apparent speed of the sun and of the moon? What is the apparent magnitude of the solar and lunar diameter, and of the horizontal parallax of the umbra and penumbra of the earth? What is the latitude of the moon? Is it north or south? Does the moon hide, occult eclipse, any of the fixed stars from the earth dwellers, and which of these does it obscure? Is there a true new or full moon? Is the sun in eclipse anywhere on earth? What is the magnitude and the duration of this eclipse with respect to the whole earth? Can it be seen in the north or in the south? Is the moon in the eclipse, total or partial? Of what magnitude, etc.? What limb of the moon is obscured? How many years have passed from a given epoch? Is this year a leap year or a common year? First, second, or third after leap year? What is the current month of the year, and what day of the month and of the week? Which of the planets is dominant? What days of the year do the various feasts fall on, and the movable feasts during the ecclesiastical year? And many other similar questions which I pass over here for the sake of brevity. Besides, this device can be so arranged for any time whatsoever, past or future, and for the longitude of any region, and can be so manipulated by hand that within the space of a very short time there can be provided, in their proper order, the various orbits of the luminous bodies, their alternating eclipses, as many as have taken place through the course of many years, or even from the beginning of the world, or those that will be seen as long as the world itself shall last, with all their attendant circumstances, year, month, day, duration, magnitude, etc. All these can be seen with great satisfaction of curiosity and of learning, and hence with great pleasure to the soul. In the meanwhile, the little bells continually play at their proper respective times, so that, all exaggeration aside, 1,000 years pass in the sight of this clock as one day. I am aware of your complaints, O star-loving reader, that my description is too meager and too succinct. Lay the blame for this on those cares, hateful both to me and to you, more pressing, which forbid me and deprive you of a methodical explanation of the work. The clock movement. Father Borghesi specified that the entire mechanism was equal in weight to a 7th part of a centenary Germanici, a Germanic hundredweight. This is probably the Austrian centner, which is equivalent to 123.4615 pounds. Therefore, the clock mechanism weighs approximately 17.6 pounds. The clock operated for 100 days and more at a single winding, according to Father Borghesi, and by means of a pendulum with a leaden bob weighing 60 Viennese pounds, attached to a height of 5 feet. Father Borghesi stated that the weight of the pendulum to be 60 librarum Venetium, but the Viennese libra does not appear among the weights of the Austrian Empire. However, using the average libra, an ancient Roman unit of weight equal to 0.7221 pound, it may be assumed that the driving weight should be approximately 45 pounds. Father Borghesi, however, does not venture to provide any description whatsoever of the movement of his second clock in his book. He gave the following reasons. But beyond this, I entirely omit a description of the further apparatus of the very many wheels, etc., inside the clock which carry on its functions, lest I become too verbose for some persons. To explain more thoroughly the internal labyrinth of the entire mechanism from which the movement of the circles or heavens, etc., are derived, would seem to entangle in too many complicated perplexities. Therefore, that I might not delay longer and perhaps to no purpose, I have thought it better to leave the whole work to the proportionate calculus of the arithmeticians and the technical skill of mechanics. If they have any desire to construct a similar mechanism, they will follow the aforesaid motions of the heavens, etc., not only by one means alone, but by many, more swiftly, through thoughtful study than by any amount of instruction. For whoever is well versed in the theory of calculus, and sets to work at any given project, will discover any desired motion by 1,000 and more ways, by one or another gearing of wheels, which an industrious mechanic will carry out in actuality and without too much difficulty. Nor is there any reason for anyone to be discouraged so long as he is not disgusted by the amount of labor. For there is nothing truer than the old saying, "The favorable gods grant everything to the assiduous laborer." Nay, further, even this little work itself can be improved on and surpassed by new inventions. Otherwise, that other old adage, almost as old as the world, would prove false. What you have found already done, you can easily repeat, nor is it difficult to add to what has already been invented. Relying on this principle, I have already conceived some new things to be added to the present little work. There is a discrepancy between Father Borghesi's written description in his second book on the number of bells and those which currently exist in the clock. At the present time, there are 2 sets of bells attached to the upper part of the movement. While Father Borghesi indicated that there were 2 sets of bells in the clock, he described the first set by stating that there are 3 bells inside the clock. The largest, when struck by a little hammer at each mean new moon, signifies the new moon. The smallest indicates in the same way the full moon, at the time of the mean full moon, by automatic sound. When on the equatorial Earth the sun appears anywhere in eclipse, 2 bells, the largest and the medium, sounding together automatically, announce that eclipse at the time of the mean new moon. I think it is evident that eclipses of the sun occur at new moons and eclipses of the moon at full moon. When the moon is eclipsed, the smallest and the medium bells simultaneously and automatically announce the event to the ear at the time of the mean full moon. Besides, at the proper time and automatically, the largest of these bells announce the current solar hour, and the smallest bell strikes the quarter hours. In the clock today, the first set consists of a smaller bell fixed within a larger one. It is presumably these bells that indicate the eclipses and also strike the hours and quarter hours. A pull cord, attached to the striking mechanism, repeats the current hour and quarter hours at will. The second set consists of 9 meshed bells, struck with individual hammers, operated by means of a pinned cylinder, as in a music box. On the hour, the chimes play one of 2 melodies, which may be changed at will. While not identified, these appear to be Tyrolean folk melodies. The largest of this set of bells is dissimilar to the other chimes, and may be the third bell described by Father Borghesi to signify the new moon. Chronograms. One of the most curious aspects of the second clock produced by Father Borghesi and Bertola, as well as of the second published volume, is the presence of chronograms, which occur repeatedly on the clock dial, and throughout the Novissimum Theorico Practicum Astronomicum Automa, from the title page to the end of the book. Interestingly enough, Father Borghesi did not utilize this device even once in his first little book. Webster defines a chronogram as an inscription, sentence, or phrase in which certain letters express a date or epoch. The method used by Father Borghesi for forming chronograms was a simple one. He used combinations of uppercase and lowercase letters in two sizes, in the inscriptions on the clock dial and in his writings. At first, this curious combination in the inscriptions on the dial plate was a source of considerable speculation. The extremely fine quality of the engraving and artistry was such that these combinations could only be deliberate in nature, and not the accidental whims or accidents of the engraver. Accordingly, they must be chronographic in intention. Such proved to be the case. Borghesi used the larger size of uppercase letters to form the chronogram, and each chronogram was complete within a phrase or line. He accomplished this by using, for this purpose, those letters of the alphabet which form the Roman numerals. The uppercase letters found within words are copied off in the order in which they appear in the inscription or phrase. These are then converted into their numerical equivalents and totaled, taking the uppermost inscription on the clock dial as the first example: Franciscus I, sit plan, Dominator Aeternus. The letters which are intended to form the chronogram are C, I, C, V, I, L, D, M, I, V. 100, 1, 100, 5, 1, 1, 50, 500, 1000, 1, 5. These figures added together total 1764. The second inscription on the clock dial, which forms a chronogram, is Laus Sacrosanctae Triadi Uni Deo et Die Pare. L, V, C, C, I, D, I, V, I, D, D, I. 50, 5, 100, 100, 1, 500, 1, 5, 1, 500, 500, 1 equals 1764. The third inscription required a little more planning because of its greater length. Accordingly, Father Borghesi divided it into 9 parts, each of which is separated from the other by means of asterisks. Each of the 9 parts of the inscription formed a chronogram which, in every instance, totals to the date 1764, the year in which the second clock was completed. The same procedure was followed with the inscriptions in the lower left and the lower right corners of the dial, as well as with the maker's inscription within the central disk. The inscription is Borgesio Doctore et Bertola Limatore Annunciantibus, VIDCLLLIMIIV, 5, 1, 500, 100, 50, 50, 50, 1, 1000, 1, 1, 5 equals 1764. The inscriptions within the chapter ring are not utilized for chronograms, however. It is apparent that Father Borghesi was required to make a most careful selection of the texts for his inscriptions, in order that none of the phrases included any additional letters which formed Roman numerals than would total to the date he desired to indicate, namely 1764. Where it was necessary, he employed an asterisk to separate parts of texts, so that each would produce the same total. Any letter that did not form a Roman numeral, even if capitalized or used in a larger size, did not interfere with the formation of the chronograms. In spite of his ingenuity in designing a text which would include only such of the letters representing the Roman numerals, which would provide the chronograms for 1764, Father Borghesi expressed some difficulties, particularly in place names. He accordingly changed them in order to avoid the inclusion of letters that would have disturbed his totals. Examples are MEGGL instead of MEHCL, which had an extra C, and RVNNO instead of RVMO, which had an extra M. Published description of the second clock. When the clock had been completed and proved to work successfully, Borghesi once more reduced a description of the clock and its function to published form in a second little volume published by Mana Uni. This second work was also in Latin, the title of which is translated as The Most Recent Theoretical Practical Astronomical Clock According to the Equally Most Recent System of the World. As with his first book, Father Borghesi devoted a number of pages to a preface addressed to the reader, which is translated from the Latin. This mechanical instrument was far from being ready for public notice. A great deal of time and work remained to produce a machine of this new system from the very foundations, then by a most accurate calculation to bring the motions of many wheels up to date with the most recent astronomical observations, and finally to fashion it with the craftsman's file, often enough with a weary hand. All this work I had performed eagerly, so that while in my room I might contemplate leisurely, both day and night, the true face of the heavens and the seas, unobscured by clouds, even though I had no astronomical equipment. But then I remembered that in my book on the first clock I had promised a description of a new, at least as far as is known to me, clock. Moreover, friends with astronomical interest, who took part in the oft-repeated astronomical experiments concerning this clock, persuaded me that the intellectual world would enjoy having a greater knowledge and a description of this work. However, it was not only the promises nor the desires of many which moved me to write this work, but I also thought it necessary to set forth, before the description of the clock, an exposition of the astronomical system according to which this clock was constructed, so that the complete work would be evident to all. I was concerned about making this timepiece more acceptable and more understandable to those people who are far distant and unable to see it, so that this present exposition would obtain credulity among all. I could find no better method than to set forth for the reader the theory of the universe, which I figured out after many sleepless nights. In testing this theory day after day, it not only appeared to be complete and true, but each day it appeared more conformable to reality. It captured my mind in such a way that I finally adhered to it. I desired, while I lived, to erect this work as a monument to the theory. To do this I digressed a bit, from the true-to-life pattern to the mechanical order, so that I can transfer all the movements of the heavens, etc., which I enjoyed thinking about more, to the plain surface of the clock's face. In this way the ecliptical spectacles of the stars, etc., would appear at their proper times clearly before the eyes of the viewer. I could also avoid many difficulties which, otherwise perhaps even to the hands of the most skilful craftsmen, could never solve. You ought to know, therefore, that as a result of my nightly meditations, I have rejected, after much consideration, all the explanations of the universe thus far published. All other theories of the makeup of the universe, however admirable, and however many there are, turn the sun and earth around in an ecliptic in an annual movement. Thus Philolaus was the first to move the earth from the center of the universe, and move it through the void. Afterwards, Aristarchus of Samos and then Copernicus moved the earth with the moon. The Egyptians, as well as Pythagoras, Ptolemy, Tycho, Ricciolus, Longomontanus, etc., thought that the sun moved through the degrees of the ecliptic each year, but I attributed this movement to neither earth nor sun, for the movement of both is only apparent. I did not vainly surmise the annual equilibrium in all astronomical observations to be from the daily movement of the same axis moved at the poles of the heavens. Nor in like manner is there a better way to satisfy physical experiments. To you, then, most cultured reader, if you perhaps can make any use or draw pleasure from this most faithful description of my new theory, and the mechanical instrument, refer it first to God on high, from whom everything that is best, and then to those avidly awaiting this little work. Lastly, if you find any statement less fitting, in your humanity do not disdain to excuse it. End of section 6. Section 7 of Smithsonian Institution, United States National Museum. Bulletin 240. Contributions from the Museum of History and Technology. Papers 34 through 44 on Science and Technology by the Museum of History and Technology. This LibriVox recording is in the public domain. Paper 35, Part 4. The Borghesi Astronomical Clock in the Museum of History and Technology by Silvio A. Bedini. Borghesian Theory of the Universe. In Father Borghesi's second volume, there is a separate chapter entitled An Exposition of the Latest Theory of the Universe. This follows the introduction to the reader, and in it Father Borghesi proposed that you might rightly conceive my new system of the world, and mechanically, as it were, construct it. Imagine for yourself, beneath that most happy seat of the blessed and above all other heavens, a kind of spherical convexity, everywhere equidistant from the center of the earth and endowed with absolutely no motion. On the inside, at 2 points diametrically opposite each other, this convexity has 2 most sturdy poles, to speak mechanically, projecting towards the center, which you call the poles of the heavens, and the largest immobile semicircle in some manner is drawn from the center of one pole to the center of the other. This semicircle in the middle, namely at a point equidistant from each pole, is thought to be secured by some sign, for example, by that O, for arranging more perceptibly the seat of the sun, as will be shown later. This much must be conceived first. You must understand that imposed on these poles is the first mobile, primum mobile, everywhere convex, and divided into 12 equal parts, dodecatamoria, by the 6 greatest circles intersecting each other at the centers of the poles. Then it is divided by another equally great circle, everywhere equidistant from the poles, into 2 hemispheres, one hemisphere of 12 parts, proceeding in orders from west, setting, to east, rising, should be assigned the respective signs of the zodiac, that is, one to Aries, the next to Taurus, and so on, etc. The circle which cuts those 12 parts transversely in the middle you call the ecliptic. Then these capital spaces of the prima mobile are subdivided by degrees, minutes, etc., both in longitude and in latitude, so that this heaven represents a kind of great spherical net, extended to capture the longitude and latitude of the stars, and mobile on the aforementioned poles. Note, however, and this is almost the leading point of the system, in that circle of longitude which divides the sign of Gemini from Cancer, and Arctenens, Sagittarius, from Capricorn, you must conceive 2 points, directly opposite each other, and removed about 23½ degrees from the poles. Boreal, the northern, between Gemini and Cancer, austral, the southern, between Sagittarius and Capricorn. These 2 points, by some power, imagine it is magnetic power, equal between them, hold the terraqueous orb suspended in the middle, by acting on the axis of the same orb, imagine it is iron, in such a way that the earth is continually drawn to those 2 points as 2 opposite centers. It is never nearer to one, for as it is about to move towards one, the opposite power is constantly drawing it back. Thus both those points and the axis of the earth are always held in one common line, wherever those points happen to be carried by the rotation of this heaven. Again, it is necessary for you to conceive in this heaven first 2 great circles, bisecting each other at right angles in the centers of these 2 magnets. One of these circles, passing through the first point of Aries and Libra in the ecliptic, is called equinoctial color. The other circle, passing consequently between the first point of Cancer and Capricorn, is called solstitial color. Beneath these are likewise imagined many other great circles, in the centers of the magnets, dividing crosswise in the shape of an X. But if receding from these magnets you describe circles parallel to each other, and ever greater and greater, up to the greatest circle which you will perceive, is called the equator. Equidistant from each magnet, and obliquely splitting the ecliptic and the equinoctial polar, you can then behold a great new woven net in this heaven of the prima mobile. This net most beautifully expands to extract the straight ascent and descent of the stars, etc., from the vast ocean of the heavens, catching the straight ascent in the great circles and in other unequal circles parallel to each other, and obliquely cutting across, most safely catching the descent. Immediately below the prima mobile, place the heaven of the fixed stars, and, that the idea might be clearer, revolving separately on the same poles on which the prima mobile revolves. Through this heaven, the filaments of the little nets, etc., seem to the eyes of you on earth as if they shine. In this heaven you should conceive in their fixed places the fixed stars, a proportionate, inviolable distance from each other, and indeed, if you will, the heavenly images, etc., depicted and all carried along at the same time with their heaven by one motion. Conceive a straight line running from the center of the earth to that sign O noted in the semicircle of the supreme immobile heaven. On this line, greatly below the heaven of the fixed stars, place the center of the solar epicycle, holding an area in common with the ecliptic and subject to absolutely no motions, but at such a distance from the center of the earth that the semi-diameter of the earth has little, if any, proportion with the distance of the solar epicycle from the earth. Around the sun, moving continually in this epicycle, its immobile palace, through the degrees of the anomaly, you can revolve, with motions proportionate to the system, the 5 planets, Mercury and Venus, the nearest barons of the sun, then Mars, Jupiter, and most remote Saturn, with its respective satellites, etc., eccentrically surrounding the earth itself and the moon in their immense ambit and wandering by their proper motions through the zodiac. Nevertheless, not far from the earth, you should imagine fabricated, as from most refined crystal, the heaven of the moon everywhere equidistant from the center of the earth, and revolving separately on the same poles, prolonged even to this place, on which the prima mobile and the heaven of the fixed stars revolve. In the middle of this, that is, in some point equally removed from the poles, you place the center of the lunar epicycle, movable also by the common rotation of the lunar heaven. I refrain from the other movements of the moon in latitude, etc., as also those of the 5 planets, etc., which the theory in no way excludes, lest by a variety of congested motions explained too abundantly, either you might be confused about the fundamental concept of the system, or, while adorning the theory and trying to embellish the least things more widely, you might reject also the things which are capital. Here you already have the whole machine, but still inert and to be animated, for the first time by motions accommodated to the system. Nevertheless, before I assign motion to the individual parts of the world, so that the thing might later appear more clearly to you, I arrange all things thus. First, as if by hand, I turn the prima mobile until the boreal magnetic point comes to the level, or the area, of the semicircle described in the supreme immobile convexity. Then I turn the heaven of the fixed stars until, for example, the heel of Castor, a star of the 3rd magnitude, almost in the ecliptic, and indeed in our time not far distant from the solstitial color, likewise falls nearly at the level of the aforesaid semicircle. Later, I turn the lunar heaven until I bring the center of the lunar epicycle to the same level. Then I turn the earth until some predetermined city, for example, Trent, situated in the northern zone with a latitude of about 46 degrees, is brought to the oft-mentioned level. From things arranged in this way, and from what has gone before, it is evident, with the motions of the luminaries, in epicycles left out, however, lest you be distracted by the explanation, that at Trent, just as in the whole northern hemisphere, it is the summer solstice, and conversely in the southern hemisphere, it is the winter solstice. The reason is because the northern magnetic point, together with the northern half of the earthly axis, is at its highest point towards the sun, immovably residing in a line sent through the level of the highest semicircle, and conversely, the southern magnetic point, with the corresponding half of the axis, is most removed from the same. It further follows that noonday and the noon moon coincide, and the heel of Castor almost reaches the summit, etc. Now, beginning from this hypothetical situation of the whole world as from the root of the motions, I move all things in their circles, so that the earth turns on its axis with a revolving motion, from west to east in each 24 hours of median time. The lunar heaven completes one circle around its poles, likewise from west to east, in the time of 29 terrestrial revolutions, hours 12.44.3.13.1. The sphere of the fixed stars on the same poles revolves once from east to west within 365 revolutions of the earth, hours 6.9.29.1. The prima mobile on the poles, common to the heaven of the fixed stars and the heaven of the moon, is moved once in the same way from east to west, a little faster, however, than the heaven of the fixed stars, yet within 365 revolutions of the earth, hours 5.48.56, that is, within a median astronomical year. Now, behold for yourself a new world, supported on new poles, and provided with new motions and laws. Now, you reader, lover of the stars, turn it and revolve it as long as it pleases you, and compare it astronomically and physically with the Copernican or the Tychonian systems, or whatever one pleases you more, and judge which one seems more constant with nature, when all things are examined. But if you aren't able to reconcile this theory with some astronomical observations or physical experiments, and think it should be eliminated from the group of theories, see that I might know this while life is still my companion, so that I might think with you, if this is possible. Also, so that in gratitude for the detected or perhaps hidden error, I might speak or write, and you won't have to shout in vain in bold ridicule and with no applause after the fleeing shades of the dead and the mute ashes. But if you object that the daily motion of the revolving earth and the annual motion of its whirling axis do not sufficiently agree with certain texts of sacred scripture, and if those things which the Copernicans and the Longomontanists say do not convince you, then reject my whole system as an old wives' tale. Last years. There was a break in the story of Borghesi and Bertollo for the next 5 years. The second clock may have been the last project on which the priest and the clockmaker worked together, for very good reasons. The two clocks must have represented a considerable financial investment in materials and in time, and neither of the men was in sufficiently affluent circumstances to undertake the luxury of such a hobby without some form of recompense. The publication of the 2 little volumes must have also been done at Father Borghesi's expense. The income of the parish priest in a small mountain village could not have been equal to the relatively great costs of the projects that have been completed. It seems probable that the priest attempted to sell his clocks to a wealthy patron, perhaps the Baron of Clays, or he may have attempted to obtain some form of recompense from the continuation of his research. However, no records can be found of such patronage, if it existed. If Borghesi had received financial assistance while the projects were in progress, he would certainly have made adequate mention of the patron's name and assistance in one or the other of the 2 volumes which he published. The next record relating to Borghesi, which has been found, is the description of a letter written by an anonymous mathematician late in 1768 or early 1769. It was 28 pages in length, written in Latin, in the form of a reply to the writer's brother on the subject of the clock invented by Borghesi. It consisted primarily of a criticism launched against Borghesi's first little volume, published in 1763. The anonymous letter is without date, place, or signature. This writer claimed that Father Borghesi had made many errors in his book, presumably in the description of the clock's functions and in the basic theories upon which the priest had predicated his research. No complete copy of the letter's text has been found for study, although it is described at length in Tovazi's Biblioteca Tirolese. Tovazi noted that 4 copies of the letter existed at the time, and that he personally had filed one in the Biblioteca de Claise in Trent. However, every attempt to locate a copy at that present time has been unsuccessful. In the anonymous letter that was brought to the attention of Father Borghesi, it must have introduced a disturbing note into his life, and cost the priest many unhappy moments. He was not, however, dissuaded from his preoccupation with horology. Several years later, in 1773, Father Borghesi was working on yet another astronomical clock, this time presumably without the assistance of Bertollo. This third clock was reported by Tovazi to have been of minimum expense, but of maximum ingenuity. No subsequent information relating to it has come to light, and there is no record that it was actually completed. Again, there is a period of silence in the life of Father Borghesi, which no amount of research has yet been able to pierce. Whatever the circumstances may have been, it is reported by several of the sources noted that both the first and the second clock did in fact become the property of the Empress Maria Theresa in Vienna. The presentation was made sometime during the period between the completion of the second clock in 1764 and the year 1780. There is some discrepancy in the contemporary accounts as to whether Father Borghesi presented 1 or 2 clocks to the Empress, but all the sources, with but one exception, record that both clocks were acquired by the Empress. It is doubtful that Father Borghesi had originally intended to give his clocks to the Empress at the time that they were made, for he would most certainly have made some mention of such an intention in the 2 little volumes which he published about them. If he saw the letter published by the anonymous mathematician in late 1768 or 1769, it is possible that he decided to make the presentation in expiation of his sense of guilt for the amount of time which the creation of the timepieces had consumed. On the other hand, it is just as possible that Father Borghesi may have forwarded copies of his 2 little volumes to the imperial court at Vienna, and that the Empress expressed a desire to acquire the clocks. Father Tovazi states that in 1780, the clock invented by him, Borghesi, was preserved in Vienna, Austria, at the imperial court, from which the inventor was receiving an annual pension of 400 florins. No records in the palace archives relating to the clock have yet been found, nor records of payment of an annuity to Father Borghesi. However, a more exhaustive investigation of the furniture depository of the imperial court may bring forth related records. It was the implication in Father Tovazi's account that the second clock had been presented to the Empress prior to the publication of the anonymous critical letter in 1768 or 1769. He believed that it was the envy of Father Borghesi's ingenuity, fame, and financial benefit that had caused the anonymous mathematician to publish his letter, for Tovazi asked, "Who would have encountered opposition to such a marvel? Envy is not yet dead, and has always reigned." This last mentioned theory about the presentation may be the most likely one. Some evidence may be found in the second clock itself, which bears out this assumption. The multiple chapter ring, with its many inscriptions, is engraved and silvered in a relatively crude manner, presumably by Bartola himself. The main dial plate, however, which is of gilt brass, is engraved with the utmost skill by one of the great masters of the art. The inscription below the imperial Habsburg eagle relates to Francis I, the Emperor of the Holy Roman Empire. It is entirely possible that although Father Borghesi originally had no intention of giving the clock to the Emperor or the Empress at the time that it was made, he later changed his mind. Accordingly, he may have commissioned a master engraver, possibly in Trent or Vienna itself, to produce a dial plate which would be of such a quality as to be worthy of the Emperor himself. If so, this was done shortly after the clock was completed, for the Emperor died in August of the following year. Perhaps by the time that the clock was ready, the Emperor had already died, and Father Borghesi gave the clock instead to Maria Theresa without revising the inscription. The acceptance of the clocks by the Empress, and the annuity which was his reward, would have constituted considerable honor even for one of the foremost clockmakers of the empire. But for a humble parish priest in a little village, such notable imperial recognition was overwhelming. Possibly as a result of it, a change was noted in Father Borghesi in the next few years. His conscience began to bother him, and he began to question whether he had done right in spending so much of his time and thought on his horological research. He became more and more confused in his own mind. Had he spent too much time in mechanical studies to the neglect of his ecclesiastical duties? If this had been the case, he had committed the most grievous sin. Exaggerated though these thoughts may appear, they were undoubtedly of the most critical importance to the middle-aged priest. His mental turbulence and confusion increased daily, and it soon became apparent to others around him. By June 1779, he was completely in the grip of his obsession, and his parishioners began to whisper among themselves that their pastor was being tortured by the devil. They were unable to help him, and he became more and more preoccupied with his problem. The years passed slowly as the pastor became more vague and more tortured by his conscience. There probably was continued contact between Father Borghesi and Bertola for at least some time after the development of his illness. Bertola had retired from active work, but continued to pursue his interests in his clock shop as much as his health and advanced years permitted. A clock which he made at the age of 80 survives, and is described and illustrated in the following section on the clocks of Bartolomeo Antonio Bertola. Finally, on January 15, 1789, Bertola passed away, and Father Borghesi was left alone, deprived of the companionship he had enjoyed with the older man for the past 2 or 3 decades. One of Bertola's nephews continued to work in the master clockmaker's workshop, but there did not appear to be any association between the younger man and Father Borghesi. At last, in 1794, Father Borghesi lost his sanity completely, and he was forced to relinquish his pastoral duties to a curate. For the remaining 8 years of his life, he continued to live in the rectory of the little parish church in Mechel, where most of his life had been spent. His needs undoubtedly attended by the parishioners he could no longer serve. During this period, until his death at the age of 79 on June 12, 1802, Father Borghesi lived on, oblivious of those around him. Seemingly he retired to another world, perhaps to that universe which he had tried to reproduce in his second clock. The clocks of Bartolomeo Antonio Bertola. The ingenuity displayed in the Borghesi clock by its constructor, Bartolomeo Antonio Bertola, requires a consideration of the other examples of his work that have survived. The most important of his clocks are probably the one in the Episcopal Palace at Trent and another made for the Baron of Claes. The one which survives in the Episcopal Palace to the present time is extremely tall and is housed in an elaborately decorated narrow case of black or ebonized wood approximately 9 to 10 feet in height. The upper part of the case is decorated with elaborately carved and gilt rococo motifs. The movement operates for 1 year at a winding, indicates and strikes the hours, and shows the lunar phases. It has an alarm, and will repeat this strike at will, indicating the number of the past hour and the quarters. The gilt brass dial is decorated with silver foliated scrollwork and relief at the corners, inside the chapter ring, and within the broken arch. Featured above the chapter ring is the coat of arms, executed in silver, of the patron for whom the clock was made, Christoforos Sitso Dinoris. Dinoris was Bishop of Trent for 13 years, from 1763 to 1776. The clock which Bertola made for the Baron of Claes is a tall, narrow case clock of ebony or ebonized pearwood, which is approximately 9.5 feet in height. The decoration of the case is considerably more conservative than the one made for Dinoris, but the black wood is decorated with silver trim and carved designs in the wood itself. The dial is decorated with silver scrollwork and spandrels within and around a raised chapter ring. The clock operates for 1 month at each winding, has an alarm, indicates and strikes the hours, and will repeat the quarters. This handsome timepiece is still in the possession of the descendants of the Baron of Clays. According to Pippa, certain characteristics become apparent in a study of the surviving clocks by Bertollo. The tall case clocks are narrow and range in height from 7 3/4 feet to 10.5 feet. The cases had this excessive height in order to obtain the greatest fall for the month and year movements, which Bertollo constructed. For the weight assembly, he substituted a drum, wound with a key, at the point of the driving wheel in place of the customary pulley. The addition of an intermediate wheel augmented the drop of the weight. Bertollo's movements were solidly constructed, from well-hammered brass and iron. He favored the recoil anchor escapement in his clocks, and the Graham deadbeat anchor escapement with his seconds pendulum. The escapement was not always placed in the traditional location in the upper center between the plates. Bertollo occasionally displaced the pendulum to one side, to the lower part of the movement, or placed it entirely between two other small plates. He utilized every type of striking work, including the music box cylinder, common in the clocks of the Black Forest and the Rack and Snail. Bertollo most frequently employed the hour strike and grand sonnerie. He often used a single hammer on two bells of different sounds with the Rack and Snail. The example of this type is the clock he produced at the age of 80. To achieve the necessary axis of rotation for the hammer, which is perpendicular to the plate when it strikes the hours, it moves to an oblique position and displaces one of the two long pins in an elongated opening. Bertollo's dial plates were generally well executed, with a raised or separate chapter ring applied to a brass or copper plate, such as a copper plate repousse, and gilt with Baroque motifs, or upon a smooth brass plate, with spandrels of repousse work, usually of silver, in relief and attached. The engraving of the chapter rings was excellent. The hands were well executed in steel or perforated bronze, and occasionally of repousse copper. Gilt was applied to the hands made of forged steel. In the course of time, Bertollo's home workshop passed from one generation to another within the family. Inevitably, it underwent many modifications until the only original part of the building that remained intact from Bertollo's time was his clock shop. Within the last few years, the workshop room was acquired, complete with contents, from Bertollo's descendants, and installed in the Museo Nazionale della Scienza e della Tecnica in Milan as an exhibit of a typical 18th century clockmaker's shop. The original workshop was dismantled in Mocenigo di Rumo and completely rebuilt in the museum, including the walls, ceiling, and floor. The paneling and woodwork of the walls and ceiling, which have been preserved intact, are hand-cut fir, with columns, trim, and moldings carved by hand. A small painting is featured in the center of the coffered ceiling. The original shop benches and chests of the drawers are set around the reconstructed shop, and Bertollo's tools and equipment laid out as they had been originally. Other clockmakers' tools and equipment in the museum's collection are also displayed. Approximately 40% of the tools are the original items from Bertollo's shop. Parts of clocks and works in progress are on view on the benches as they were in Bertollo's time. Also preserved in the museum are sketches found in Bertollo's manuscripts, some of which are reproduced on the following pages. The shop contains two completed clocks made by Bertollo. One is a weight-driven lantern clock, typical of the 18th century, Italian style, with brass dial, plates and posts, anchor escapement, and striking work. The dial is engraved in the usual style of Bertollo's Baroque design, and the hands are of pierced bronze. Another clock associated with Bertollo and found in the shop was made by his nephew, Alessandro Bertollo, who worked in Venice after his apprenticeship with his uncle had been completed. This clock is a regulator, with a seconds-hand pendulum and sweep hand on an enamel dial. The original case has not survived. One of the most interesting of Bertollo's clocks, and probably the last one which he produced, was found in his workshop. This timepiece indicates the hours, minutes, and quarters by means of a single hand, or an index. The weight-driven clock strikes the hours and quarters on two bells with a single hammer. The chapter ring, which is soldered to the dial plate, is marked for the minutes on the outer rim and for the 4 quarters inside it. Over the center of it is a semicircular opening in the dial plate through which is visible a revolving disc attached behind the dial plate. This is marked with the hours and revolves from right to left, the current hour being indicated by a projection from the minute ring. The brass dial plate is engraved with simple floral designs in the corners and around the broken arch. There is no comparison between this crude and simple decoration and the extremely fine quality of the engraving on the dial plate of the Borghesi clock. For instance, in the center of the dial plate is engraved the following: Questo orologio la dia e li fece nella mia avanzata età d'anni 80. I designed and made this clock at my advanced age of 80 years. Bartolomeo Antonio Bertola. End of section 7. Section 8 of Smithsonian Institution, United States National Museum. Bulletin 240, Contributions from the Museum of History and Technology. Papers 34 through 44 on Science and Technology, Museum of History and Technology. This LibriVox recording is in the public domain. Paper 36, Part 1. The Engineering Contributions of Wendel Bollman, by Robert M. Vogel. The development of structural engineering has always been as dependent upon the availability of materials as upon the expansion of theoretical concepts. Perhaps the greatest single step in the history of civil engineering was the introduction of iron as a primary structural material in the 19th century. It quickly released the bridge and the building from the confines of a technology based upon the limited strength of masonry and wood. Wendel Bollman, self-taught Baltimore civil engineer, was the first to evolve a system of bridging in iron to be consistently used on an American railroad, becoming one of the pioneers who ushered in the modern period of structural engineering. The author, Robert M. Vogel, is curator of civil engineering in the Smithsonian Institution's Museum of History and Technology. Wendel Bollman's name survives today solely in association with the Bollman Truss, and even in this respect is known only to a few older civil and railroad engineers. The Bollman system of trussing, along with those of Whipple and Fink, may be said to have introduced the great age of the metal bridge, and thus directly the modern period of civil engineering. Bollman's bridge truss, of which the first example was built in 1850, has the very significant distinction of being the first bridging system in the world employing iron in all of its principal structural members that was used consistently on a railroad. The importance of this transition from wood to iron as a structural and bridge-building material is generally recognized, but it may be well to mention certain aspects of this change. The tradition of masonry bridge construction never attained the great strength in this country which it held in Europe, despite a number of notable exceptions. There were several reasons for this. From the very beginning of colonization, capital was scarce, a condition that prevailed until well into the 19th century, and which prohibited the use of masonry because of the extremely high costs of labor and transport. An even more important economic consideration was the rapidity with which it was necessary to extend the construction of railways during their pioneer years. Unlike the early English and European railways, which invariably traversed areas of dense population and industrial activity and were thus assured of a significant financial return, almost from the moment that the first rail was down, the Baltimore and Ohio and its contemporaries were launched upon an entirely different commercial prospect. Their principal business consisted not so much in along-the-line transactions as in haulage between principal terminals, separated by great and largely desolate expanses. This meant that income was severely limited until the line was virtually complete from end to end, and it meant that commencement of return upon the initial investment was entirely dependent upon the speed of survey, graduation, tunneling, and bridging. The need for speed, the general attenuation of capital, and the simple fact that all the early railroads traversed thickly forested areas rendered wood the most logical material for bridge and other construction, both temporary and permanent. The use of wood as a bridge material did not, of course, originate with the railroads, or for that matter in this country. The heavily wooded European countries, Switzerland in particular, had a strong tradition of bridge construction in timber from the Renaissance on, and naturally a certain amount of this technique found its way to the New World with the colonials and immigrants. America's highway system was meager, until about the time the railroad age itself was beginning. However, by 1812, there were, along the eastern seaboard, a number of fine timber bridges of truly remarkable structural sophistication and workmanship. It was just previous to the advent of the railroads that the erection of highway bridges in this country began to pass from an art to a science. And an art it had been, in the hands of the group of skilled but unschooled master carpenters and masons who built largely from an intuitive sense of proportion, stress, and the general fitness of things. It passed into an exact science under the guidance of a small number of men trained at first in the scientific and technical schools of Europe, and after about 1820 in the few institutions then established in America that offered technical instruction. The increasing number of trained engineers at first affected highway bridge construction not so much in the materials used, but in the way they were assembled. In a bridge designed by a self-taught constructor, the cheapness of wood made it entirely feasible to proportion the members by enlarging them to the point where there could be no question as to their structural adequacy. The trained engineer, on the other hand, could design from the standpoint of determining the entire load and then proportioning each element according to the increment of stress upon it and to the unit capacity of the material. By the time railroads had started expanding to the west, there had been sufficient experience with the half-dozen practical timber truss systems by then evolved, that there was little difficulty in translating them into bridges capable of supporting the initial light rail traffic. In spite of its inherent shortcomings, wood was so adaptable that it met almost perfectly the needs of the railroads during the early decades of their intense expansion, and, in fact, still finds limited use in the Northwest. Early career. Wendel Bollman was born in Baltimore, of German parents, in 1814. His father was a baker, who in the same year had aided in the city's defense against the British. Wendel's education, until about the age of 11, was more or less conventionally gained in public and private schools in Baltimore. He then entered into informal apprenticeship, first to an apothecary in Shepherdstown, Virginia, now West Virginia, and then to one in Harper's Ferry. In 1826 or 1827 he became ill and returned to Baltimore for cure. From that time on, his education was entirely self-acquired. It is of interest, in light of his later career, to note that on the 4th of July, 1828, he marched with other boys in a procession that was part of the Baltimore and Ohio Railroad's cornerstone-laying ceremony. Shortly afterward, he apprenticed himself to a carpenter for a brief time, but when the work slacked off, he obtained work with the B&O. The right-of-way had been graded for about 5 miles by that time, but no rail was down. The boy was at first given manual work, but soon advanced to rodman, and rapidly rose as he gained facility with the surveying apparatus. In the fall of 1829, he participated in laying the first track. As his mother was anxious that he continue his education in carpentry, he left the railroad in the spring of 1830 to again enter apprenticeship. He finished, became a journeyman, helped build a planter's mansion in Natchez, and returned to Baltimore in 1837 to commence his own carpentry business. The next year, while building a house on Harper's Ferry, he was asked to rejoin the B&O to rebuild parts of its large timber bridge over the Potomac there, which had fallen victim to various defects after about a year's use. Shortly after the Harpers Ferry Bridge reconstruction, Bollman was made foreman of bridges. It is apparent that on the basis of his practical ability, enhanced by the theoretical knowledge gained by intense self-study, he eventually came to assist Chief Engineer Benjamin H. Latrobe in bridge design. He later took this work over entirely, as Latrobe's attentions and talents were demanded in the location and extension of the line between Cumberland and Wheeling. The B&O did not reach its logical destination, Ohio, actually Wheeling, West Virginia, on the east bank of the Ohio River, until 1853. In the years following Bollman's return to the railroad, the design of bridges was an occupation of the engineering staff second in importance only to the location of the line itself. During this time, Bollman continued to rise and assume greater responsibilities, being appointed Master of Road by Latrobe in 1848. In this position, he was responsible for all railroad property that did not move, principally the right-of-way and its structures, including, of course, bridges. The recognition of Bollman's abilities was in the well-established tradition of the B&O, long known as America's first school of engineering, having sponsored many early experiments in motive power, track work, and other fundamental elements of railroad engineering. It furnished the means of expression for such men as Knight, Wright, Whistler, Latrobe, and Winans. Of these pioneer civil and mechanical engineers, some were formally trained, but most were self-taught. Bollman's career on the B&O is of particular interest not only because he was perhaps the most successful of the latter class, but because he was probably also the last. He may be said to be a true representative of the transitional period between intuitive and exact engineering. Actually, his designing was a composite of the two methods. While making consistent use of mathematical analysis, he was at the same time more or less dependent upon empirical methods. For years, B&O employees told stories of his sessions in the tin shop of the railroad's main repair facility at Mount Clair in Baltimore, where he built models of bridges from scraps of metal and then tested them to destruction to locate weaknesses. It seems most likely, however, that the empirical studies were used solely as checks against the mathematical. In the period when Bollman began designing, about 1840, there were fewer than 10 men in the country designing bridges by scientifically correct analytical methods. Whipple and Roebling, the most notable of this group. By 1884, the year of Bollman's death, the age of intuitive design had been dead for a decade or longer. The B&O was in every way a truly pioneer enterprise. It was the first practical railroad in America, the first to use an American locomotive, the first to cross the Alleghenies. The spirit of innovation had been encouraged by the railroad's directors from the outset. It could hardly have been otherwise in light of the project's elemental daring. The first few major bridges beyond the line's starting point on Pratt Street in Baltimore were of rather elaborate masonry, but this may be explained by the projectors' consciousness of the railroad's significance and their desire for permanence. However, the aforementioned economic factors shortly made obvious the necessity of departure from this system, and wood was thereafter employed for most long spans on the line, as far as Harper's Ferry and beyond. Only the most minor culverts and short spans, and those only in locations near suitable quarries, were built of stone. In addition to the economic considerations, which prompted the company to revert to timber for the major bridges, there were several situations in which masonry construction was unsuitable for practical reasons. If stone arches were used in locations where the grade of the line was a relatively short distance above the surface of the stream to be crossed, a number of short arches would have been necessary to avoid a very flat single arch. In arch construction, the smaller the segment of a circle represented by the arch, that is, the flatter the arch, the greater the stress in the arch ring and the resulting horizontal thrust on the abutments. The piers for the numerous arches necessary to permit an optimum amount of rise relative to the span would have presented a dangerous restriction to stream flow in time of flood. By the use of timber trusses, such crossings could be made in one or two spans with at most one pier on the stream, thus avoiding the problem. The principal timber bridges as far west as Cumberland were of Latrobe's design. They were good, solid structures of composite construction, in which a certain amount of cast iron was used in joints and wrought iron for certain tension members. They were, however, more empirical than efficient, and for the most part not only grossly over-designed, but of decidedly difficult fabrication and construction. What is interesting about the Latrobian timber trusses, however, is the effect they appear to have had upon Bollman's subsequent work in the design of his own truss. This effect is evidenced by the marked analogy between the primary structural elements of the two types. The Latrobe truss at Ellisville was only partially a truss, inasmuch as the greater part of the load was not carried from panel to panel, finally to appear at the abutments as a pure vertical reaction, but was carried from each panel, except the four at the center, directly to the bearing points at the piers by heavy diagonal struts, after the fashion of the famous 18th-century Swiss trusses of the Grubenmans. It was a legitimate structural device, and the simplest means of extending the capacity of a spanning system. However, it was defective, in that the strut supplied considerable horizontal thrust to the abutments, requiring heavier masonry than would otherwise have been necessary. It is quite likely that Latrobe did not have absolute confidence in the various pure truss systems already patented by Town, Long, and others, and preferred, for such strategic service, a structure in which the panel members acted more or less independently of one another. It will be seen that, similarly, the individual panel loads in Bollman's truss were carried to the ends of the frame by members acting independently of one another. The Bollman Truss. There had never been any question about the many serious inadequacies of wood as a bridge material. Decay and fire risk, always present, were the principal ones, involving continuous expenditure for replacement of defective members and for fire watches. It was, in fact, understood by the management and engineering staff of the B&O that their timber bridge superstructures, though considered the finest in the country, were more or less expedient, and were eventually to be replaced. In this regard, it is not surprising that Latrobe, a man of considerable foresight, had, at an early date, given serious thought to the possible application of iron here. The world's first major iron bridge, the famed cast-iron arch at Coalbrookdale, England, had been constructed in 1779. Its erection was followed by rather sporadic interest in this use of the material. The first significant use of iron in this country was in a series of small trussed highway arches erected by Squire Whipple of the Erie Canal in the early 1840s, over 60 years later. In these, as in most of the earlier iron structures, an arch of cast iron was the primary support. The thrust of the arches was counteracted by open wrought iron links, with other wrought and cast iron members contributing to the truss action. The Whipple bridges promoted a certain amount of interest in the material. In the B&O's annual report for the fiscal year 1849 appears the first record of Latrobe's interest in this important matter. In the President's message is found the following rather offhand statement. $6,183.19 have been expended toward the renewal of the stone bridges on the Washington branch, carried off by the flood of October 7, 1847. Preparations are made and contracts entered into for the reconstruction of the large bridges at Little Patuxent and at Bladensburg, which will be executed in a few months. It is proposed to erect a superstructure of iron upon stone abutments at each place, with increased span for greater security against future floods. It is interesting to note that it was indeed Bollman's trusses to which the president of the railroad had referred. How much earlier than this date Bollman had evolved his peculiar trussing system is not clear. The certain influence of Latrobe's radiating strut system of trussing has been mentioned. As likely an influence was another basic technique commonly used to increase the capacity of a simple timber beam, that of trussing, that is, placing beneath the beam a rod of iron that was anchored at the ends of the beam and held a certain distance below it at the center by a vertical strut or post. This combination thus became a truss, in that the timber portion was no longer subject to a bending stress, but to a simple one of compression, the rod absorbing the tensile stress of the combination. The effect was to deepen the beam, increasing the distance between its extreme fibers and, by thus reducing the bending moment, reducing the stress in them. It apparently occurred to Bollman that by extending the number of rods in a longitudinal direction, this effect could be practically amplified to such an extent as to be capable of spanning considerable distances. He almost certainly did not at first contemplate an all-iron system, but rather a composite one such as described. It is entirely likely that such trussed beams with multiple systems of tension rods were used by Bollman as bridging, in temporary trestle work along the line as early as 1845. It is impossible to say whether Bollman himself or Latrobe was struck with the logic of further elaborating upon the system, and simultaneously translating the timber compression member into one of cast iron. Cast iron would naturally have been selected for a member that resisted a compressive stress. It was considerably cheaper than wrought iron. But more important, at that time, wrought iron was not available in shapes of sufficient sectional area to resist the appreciable buckling stresses induced in long compression members. The cost of building up members to sufficient size, from the very limited selection of small shapes then rolled, would have been prohibitive. The trussing rods, subjected to tension, were of wrought iron inasmuch as the sectional area had only to be sufficient to resist the primary axial stress. The first all-iron Bollman truss was constructed over the Little Patuxent River at Savage Factory near Laurel, Maryland in 1850. In the chief engineer's report for the year 1850, Latrobe was able to state that the truss had been completed and was giving much satisfaction. He went on at some length to praise the valuable mechanical features embodied therein and expressed great confidence that iron would become as important a material in the field of civil engineering as it was in mechanical engineering. The cost of this first major Bollman bridge was $23,825. Its span was 76 feet. Latrobe's confidence was well placed. The Savage span and another at Bladensburg may be considered successful pilot models, for in spite of a certain undercurrent of mistrust of iron bridges within the engineering profession, due mainly to a number of failures of improperly designed spans, Latrobe felt that there was sufficient justification for the unqualified adoption of iron in all subsequent major bridge structures on the B&O. Almost immediately following completion of the Savage Bridge, Bollman undertook the design of replacements for the large Patapsco River span at Ellisville, now Daniels, Maryland, and the so-called Winchester span of the B&O's largest and most important bridge, that over the Potomac at Harper's Ferry. Harper's Ferry Bridge, a timber structure, had been designed by Latrobe and built in 1836 through 1837 by the noted bridge constructor Louis Vernwag. It was peculiar in having a turnout near the Virginia shore, where a subsidiary road branched off to Winchester. Only the single span on this line, situated between the mid-river switch and the shore, was slated for replacement, as the other 7 spans of the bridge had been virtually reconstructed in the decade or so of their history and were in sound condition at the time. The Winchester span, which was the first Bollman truss to embody sufficient refinement of detail to be considered a prototype, was completed in 1851. Bollman was extremely proud of the work, with perfect justification, it may be said. The 124-foot span was fabricated in the railroad's extensive Mount Clair shops. It was subdivided into 8 panels by 7 struts and 7 pairs of truss rods. An interesting difference between this span and Bollman's succeeding bridges was his use of granite rather than cast iron for the towers. The span consisted of 3 parallel lines of trussing to accommodate a common road in addition to the single-track Winchester line. The distinctive feature of the Bollman system was the previously mentioned series of diagonal truss links in combination with a cast-iron compression cord, which Bollman called the stretcher. The spacing between the cord and the junction of each pair of links was maintained by a vertical post, or strut, also cast. Much of the appeal of this design lay unquestionably in the sense of security derived from the fact that each of the systems acted independently to carry its load to the abutments. The lower cords, actually non-functional in the primary structure, were included merely to preserve the proper longitudinal spacing between the lower ends of the struts. A certain lack of rigidity was inherent in the system due to that very discontinuity which characterized its action. However, this was compensated for by a pair of light, diagonal stay rods crossing each panel. These rods serve the additional function of distributing concentrated loads to adjacent struts, much in the manner of the bridging between floor joists in a building. In the Winchester span, the floor system was of timber, for reasons of economy. This was a very minor weakness, inasmuch as any stick could be quickly replaced, and without disturbing the function of the structure. Bollman received a patent for his truss in January of 1852, and in the same year published a booklet describing his system in general and the Harper's Ferry span in particular. Here he first calls it a suspension and truss bridge, which is indeed an accurate designation for a system which is not strictly a truss because it has no active lower cord. The analogy to a suspension bridge is quite clear, each pair of primary rods being comparable to a suspension cable. Thereafter, Bollman's invention was generally termed a suspension truss. End of Section 8. Section 9 of Smithsonian Institution, United States National Museum. Bulletin 240. Contributions from the Museum of History and Technology. Papers 34 through 44 on Science and Technology. By Museum of History and Technology. This LibriVox recording is in the public domain. Paper 36, Part 2. The Engineering Contributions of Wendel Bollman. By Robert M. Vogel. Influence of the Truss. Bollman's 1852 publication was widely disseminated here and abroad, and studied with respectful interest by the engineering profession. Its drawings of the structure were copied in a number of leading technical journals in England and Germany. Although there is no record that the type was ever reproduced in Europe, there can be little doubt that this successful structural use of iron by the most eminent railroad in the United States, and its endorsement by an engineer of Latrobe's status, gave great impetus to the general adoption of the material. This influence was certainly equal to that of Stephenson's tubular iron bridge of 1850 over the Menai Strait, or Roebling's iron wire suspension bridge of 1855 over Niagara Gorge. The Bollman design had perhaps even greater influence, as the B&O immediately launched the system with great energy and in great numbers to replace its timber spans. On the other hand, Roebling's structure was never duplicated in railroad service, and Stephenson's only once. Evaluation of the truss. By the late 1850s, iron was well established as a bridge material throughout the world. Once the previous fears of iron had been stilled, and the attention of engineers was directed to the interpretation of existing and new spanning methods into metal, the Bollman truss began to suffer somewhat from the comparison. Although its components were simple to fabricate, and its analysis and design was straightforward, it was less economical of material than the more conventional panel trusses, such as the Pratt and Whipple types. Additionally, there was the requisite amount of secondary metal in lower cords and braces necessary for stability and rigidity. A factor difficult to assess is Bollman's handling of his patent, which was renewed in 1866. There is sufficient evidence to conclude that he considered the patent valuable because it was based upon a sound design. Therefore, he probably established a high license fee, which, with the truss's other shortcomings, was sufficient to discourage its use by other railroads. As patron, the B&O had naturally had full rights to its use. An additional defect, acknowledged even by Bollman, arose because of the unequal length of the links in each group except the center one. This caused an unevenness in the thermal expansion and contraction of the framework, with the result that the bridges were difficult to keep in adjustment. This had the practical effect of virtually limiting the system to intermediate span lengths up to about 150 feet. For longer spans, the B&O employed the truss of another of Latrobe's assistants, German-born and technically trained Albert Fink. The Fink truss was evolved contemporaneously with Bollman's, and was structurally quite similar, being a suspension truss with no lower chord. The principal difference was the symmetry of Fink's plan, which was achieved by carrying the individual panel loads from the panel points to increasingly longer panel units, before having them appear at the end bearings. This eliminated the weakness of unequal strains. The design was basically a more rational one, and it came to be widely used in spans of up to 250 feet, generally as a deck-type truss. W. Bollman and Company. Bollman resigned from the Baltimore and Ohio in 1858 to form, with John H. Tegmeyer and John Clark, two of his former B&O assistants, a bridge-building firm in Baltimore known as W. Bollman and Company. This was apparently the first organization in the United States to design, fabricate, and erect iron bridges and structures, pioneering in what 25 years later had become an immense industry. The firm had its foundation at least as early as 1855, when advertisements to supply designs and estimates for Bollman bridges appeared over Tegmeyer's name in several railroad journals. Bollman's separation from the B&O was not a complete one. The railroad continued its program of replacing timber bridges with Bollman trusses and contracted with W. Bollman and Company for design and certain amount of fabrication. There is some likelihood that eventually fabrication was entirely discontinued at Montclair and all parts subsequently purchased from Bollman. The firm prospered, erecting a number of major railroad bridges in Mexico, Cuba, and Chile. Operations ceased from 1861 to 1863 because of difficult wartime conditions in the border city of Baltimore. Following this, Bollman re-entered business as sole proprietor of the Patapsco Bridge and Iron Works. The most noteworthy of Bollman's works in this period was a series of spans at Harper's Ferry. The B&O's timber bridge had been destroyed by Confederate forces in June of 1861, and the crossing was thereafter made upon temporary trestle work. This was a constant source of trouble, with continuing interruptions of the connection from high water, washouts, and military actions. The annoyance and expense of this became so great that the company decided to risk an iron bridge at the crossing. In July and August of 1862, two sections of Bollman truss spans number 4 and number 5 were completed. As this occurred during the time when W. Bollman and Company was inoperative, the work was produced at Montclair to Bollman's design and undoubtedly erected under his supervision. 5 weeks later, on September 24th, these and Bollman's famous Winchester span of 1851 were blown up by the Confederates, and the line's business was again placed at the mercy of trestling. The spirit of the B&O administration indeed seems to have been unshakable when, in the face of such heartbreaking setbacks, it determined to again bridge the river with iron, even at the height of the hostilities. In November, span number 5 was erected, and by April 1863, numbers 3, 4, and 6 also. These were the 4 straight spans in mid-river between the wide, or branch, or Y span, and the span on the Maryland shore over the Chesapeake and Ohio Canal. Although the wood floor system of these spans was burned for strategic reasons by U.S. troops later in 1863, they survived the war. In 1868, the remaining trestle work was replaced with Bollman trusses. This magnificent structure served the railroad until 1894, when the right-of-way was realigned at Harper's Ferry. However, the half used by the common road remained in use until carried away by the disastrous flood of 1936. The piers may still be seen. During the pre-war years, Bollman evolved a structural development of most profound importance, which is usually associated with the Phoenix Iron Works and its founder, Samuel J. Reeves. In the erection of a high trestlework viaduct for the Havana Railroad, Bollman apparently became concerned with the tensile weakness of cast iron when applied in long, unsupported columns. Although a column is normally subjected to compressive stresses, when the slenderness ratio, that is, the length divided by the radius of gyration of the cross-section, becomes great, a secondary bending stress may be produced. If this stress becomes great enough, the value of the tensile stress in one side of the column may actually exceed the principal compressive stress, and a net effect of tension result. As already mentioned, the few available rolled iron shapes were of relatively small area and quite unsuitable for use as columns, unless combined and built up in complex fabrications. The normal practice at the time was to use cast compression members in iron bridges and structures with their sectional area so proportioned to the length that a state of tension could not exist. In the case of long members, this naturally meant that an excessive amount of material was used. Bollman was conscious of the problem, from his experience with the stretchers and struts of his truss, and he must have been aware of the great advantage which would be obtained by a practical method of forming such members in wrought iron, the tensile resistance of which is equivalent to the compressive. He eventually developed the forerunner of what became to be known as the Phoenix form, by having special segmental wrought iron shapes rolled by Morris, Tasker, and Company of Philadelphia, these shapes being combined into a circular section without standing flanges for riveting together. The circular section is theoretically the most efficient to bear compressive loading. A column of any required diameter could be produced by simply increasing the number of segments, the individual size of which never exceeded contemporary rolling mill capacity. The design exhibits the inspired combination of functional perfection and simplicity that seems to characterize the most great inventions. It may have been because he had no facilities for rolling that Bollman communicated his idea to Reeves, although this seems illogical. At any rate, Reeves and his associates patented the system extensively, and the Phoenix column was eventually employed to the virtual exclusion of cast iron and other types of wrought iron columns. By the end of the 19th century, it began to pass from use, as mills became capable of producing larger sections with properties relatively favorable to column use and more adaptable to connection with other members. Final use of the Bollman truss. The Bollman truss found occasional use elsewhere than on the B&O lines, but generally only when erected on contract by Patapsco Bridge and Ironworks. However, the fact that Bollman could profitably erect this bridge in the severely competitive 1870s indicates that the harsh criticism of the system by authorities of such stature as Whipple was not necessarily justified. Bollman's advertisements, in fact, refer to the favorable recommendations of other such renowned engineers as Herman Haupt and M.C. Meigs. An interesting application of the system was in a drawbridge, formed of two Bollman deck spans over an arm of the Mississippi at Quincy, Illinois. The first iron bridge in Mexico was erected by Bollman over the Medellin River about 1864. Another work of this period, which attracted considerable attention, was a pair of bridges that Bollman erected over North Carolina's Cape Fear River in 1867 through 1868. These bridges were notable for their foundation on cast iron cylinders, sunk pneumatically. This was one of the first instances of the use of the process in America, and the depth of 80 feet below the water surface reached by one cylinder was considered remarkable for years afterward. In the last active decade or so of his career, Bollman produced hundreds of minor bridges and other structures. In 1873, he supplied the castings for the splendid iron dome of Baltimore City Hall and erected the ingenious water main truss which carries Lombard Street over Jones Falls in that city. In this structure, the top and bottom chords of the central line of trussing are cast iron water mains, bifurcated at the abutments and joined by cast and wrought iron web members. In the mid-1870s, Bollman saw his truss pass into obsolescence. This was due primarily to the general increasing distrust of cast iron for major structural members due to its brittleness. But advances in structural theory, availability of a greater variety of rolled structural shapes, and the increasing load patterns of the period all contributed. Although no Bollman trusses were built by Bollman or the B&O after 1875, those in use were only removed as required by heavier motive power. The Harper's Ferry span, as noted, remained in full mainline service until 1894. Bollman trusses on feeder lines were continued in use until much later. A number of them on the Valley Railroad of Virginia were not removed until 1923. However, only on the most isolated spurs was the Bollman truss permitted to reach really ripe age. The sole known remaining example stands on such a branch, ironically at Savage, over the Little Patuxent, the site of the first Bollman span. This is not the 1850 bridge, but the one built in 1852 and moved to the present site 30 years later. The fate of the first span is not known. End of Section 9. Section 10 of Smithsonian Institution, United States National Museum, Bulletin 240. Contributions from the Museum of History and Technology. Papers 34 through 44 on Science and Technology by Museum of History and Technology. This LibriVox recording is in the public domain. Paper 37. Screw Thread Cutting by the Master Screw Method since 1480 by Edwin A. Battison. Among the earliest known examples of screw thread cutting machines are the screw cutting lathe of 1483, known only in pictures and drawings, and an instrument of the traverse spindle variety for threading metal, now in the Smithsonian Institution, dating from the late 17th or early 18th century. The author shows clearly their evolution from something quite specialized to the present-day tool. He has traced the patents for these instruments through the early 1930s, and from this research we see the part played by such devices in the development of the machine tool industry. The author, Edwin A. Battison, is Associate Curator of Mechanical and Civil Engineering in the Smithsonian Institution's Museum of History and Technology. Directness and simplicity characterize pioneer machine tools because they were intended to accomplish some quite specialized task, and the need for versatility was not apparent. History does not reveal the earliest forms of any primitive machines, nor does it reveal much about the various early stages in evolution toward more complex types. At best, we have discovered and dated certain developments as existing in particular areas. Whether these forms were new at the time they were first found, or how widely dispersed such forms may have been, is unknown. Surviving evidence is in the form of pictures or drawings, such as the little-known screw-cutting lathe of 1483, shown in das Mittelalterliche Hausbuch. This lathe shows that its builder had a keen perception of the necessary elements, reduced to bare essentials, required to accomplish the object. Present are the coordinate slides often credited to Henry Maudslay. His slides are not, of course, associated with the spindle. Neither is there any natural law which compels them to guide the tool exactly parallel with the axis of revolution. In this sense, the screw-cutting lathe in the Hausbook is superior because it is in harmony with natural law and can generate a true cylinder, whereas Maudslay's lathe can only transfer to the work whatever accuracy is built into it. In principle, this machine shown in the Hausbook is very advanced, as we see when we follow the design through to the present time. The artist whose drawings give us our only knowledge of the machine himself was obviously not very familiar with the details of its function. Reference to Figure 1 shows that the threads on the lead screw and on the work wind in opposite directions. This must be an error in delineation, since the two are closely coupled together without any intervening mechanism, so that the only possible result of the work must be a thread winding in the same direction as on the original screw. The work also is shown threaded for its entire length. This cannot be accomplished with any one location of the cross slide. We are left with the question of whether this slide was used in two locations or whether the artist, possibly working from notes or an earlier rough sketch, failed to show an unthreaded portion on one end or the other of the work. Of at least equal importance with the lead screw and work in their relationship to each other is the tool support, with its screw-adjusted cross slide. Just how this was attached to the frame of the machine so that it placed the tool at a suitable radius is again a questionable point. The very well-developed cutting tool is sharpened to a thin, keen edge, totally unsuited for cutting metal, but ideal for use on a softer, fibrous substance, undoubtedly wood in this instance. Unfortunately, the angle at which the artist chose to show us this cutter is not a view from which it is possible to judge whether or not the tool has been made to conform to the helix angle of the thread to be cut. This cross-slide, in conjunction with the traversing work spindle, gives us a machine having two coordinate slides yielding the same effect as the slide rest usually attributed to Henry Maudslay at the end of the 18th century. Actually, an illustration of coordinate slides independent of the spindle had been published as early as 1569 by Besson, and knowledge of them widely disseminated by his popular work on mechanics. These slides are shown as part of a screw-cutting machine, with a questionably adequate connection, by means of cords, between the master screw and the work. It was the author's pleasure recently to obtain for the Smithsonian Institution and identify a small, nicely made brass instrument which had been in two collections in this country and one collection in Germany as an unidentified locksmith's tool. This proved to be an instrument of the traverse spindle variety for threading metal. Fortunately, all essential details were present, including a cutter. This instrument was identified by the signature Manuel Wetzky, Augsburg. The Wetzkys were a well-known family of gunsmiths and mechanics in Augsburg through several generations. Two bore the given name Emanuel. The earlier was born in 1678 and died in 1728. He was quite celebrated in the field of rifle-making and became chief of artillery to the Landgrave of Hesse-Kassel shortly before his death in the 51st year. Little is known of the later Emanuel Wetzky, except that he was at Augsburg in 1740. Tentative attribution of the instrument has been made to the earlier Emanuel, chiefly on the basis of his recognized position as an outstanding craftsman. In several respects, this little machine differs from its predecessor of the Augsburg, as might be expected when allowance is made for the generations of craftsmen who undoubtedly worked with such tools over the roughly 200 years of time separating them. Another factor to consider when comparing these two machines is that one was used on metal, the other probably only on wood. Therefore, it is not surprising to find on the later machine an outboard or a tailstock support for the work. The spindle of this support has to travel in unison with the work-driving spindle so that it is not an unexpected discovery to find that it is spring-loaded. Figure 5 shows how this spring may be adjusted to accommodate various lengths of the work, by moving the attachment screw to various holes in both the spring and in the frame. Also visible in the same illustration is a rectangular projection at the other end of the spring, which engages a mating hole in the tailstock spindle to prevent its rotation. Figure 6 shows the traversing spindle and nut removed from the machine. Provision has been made for doing this so easily that there is every reason to believe that originally there were various different spindle and nut units which could be interchangeably used in the machine. Additional evidence tending to support this concept exists in the cutting tool, which must have been intended for serious work, as it has been carefully fitted in its unsymmetrical socket. The cutting blade of this tool, which works with a scraping rather than a true cutting action, is too wide to form a properly proportioned thread when used with the existing lead screw. This may well indicate that the tool was made for use with a lead of coarser pitch, now lost. Perhaps the most startling feature of this machine, when compared with the machine of the housebook, is the absence of a cross slide for adjusting the tool. Possibly this can be explained by the blunt scraping edge on the tool. In actual use recently, to cut a sample screw, using a tool similar to the one found in the machine, it was found advantageous to be free of a cross slide, and thus be able to feed the tool into the work by feel, rather than by rule, as would be done with a slide rest. In this way, it was possible to thread steel without tearing, as the cutting pressure could readily be felt and the tool could release itself from too heavy a cut. Size on several screws could be repeated by setting the tool to produce the desired diameter when its supporting arm came to rest against the frame of the machine. The screws used in the machine itself were apparently made in just such a way. They were not cut with a die, as the thread blends very gradually into the body of the screw, without the characteristic marks left by the cutting edges of a die. Threads cut with a single point tool controlled by a cross slide usually end even more abruptly than those cut by a die, while it could be quite simple with a machine of the nature we are considering to bring the thread to a gentle tapering end, as seen in Figure 8, another view of the screw, A in Figure 3, by gradually releasing the pressure necessary to keep the tool cutting as the end of the thread was approached. That machines of this general type having the lead screw on the axis of the work were competitive with other methods and other types of machines over a long period of time may be seen from Figures 9 and 10. The machine, left front in Figure 9, and in more intimate detail in Figure 10, can be seen to differ little from that shown in Das Mittelalterliche Hausbook of 1483. The double work support is of course a great improvement, while the tool support is regressive, since it lacks a feed screw. The development of engineering theory, coupled with the rising needs of industry, particularly the advent of the Industrial Revolution, brought about accelerated development of screw-cutting lathes, through the combination of screw-cutting machines with simple lathes, as seen in Figure 9, and in detail in Figure 11. One important advance shown here is driving the machine by means of a cord or band, so that any means of rotary power could be applied, not just hand or foot power. Of greater interest and technical importance to this study is the provision, seen to better advantage in Figure 11, for readily changing from one master lead screw to another. This has already been achieved in the manual Vetsky machine, as far as versatility is concerned, although not in quite such a convenient way. Figure 12. The headstock of another and more advanced lathe, than shown in Figures 9 and 11, but of the same type, shows keys, D, each of which is a partial nut of different pitch to engage with a thread of mating pitch. The dotted lines in Figure 13 show the engaged and disengaged positions of one of those keys, and Figure 14 shows the spindle with the various leads, C. At D is a grooved collar to be engaged by the narrow key shown in operating position at the left in Figure 12, for the purpose of controlling the endwise movement of the spindle when used for ordinary turning instead of thread cutting. In return for greater convenience and freedom from the expense of the many separate spindles, as typified by the Vetsky machine, a sacrifice has been made in the length of the thread which can be cut without interruption. This reduction in the length, that could conveniently be threaded, was no great drawback on many classes of work. This can be realized from Figure 16, which shows a transverse spindle lathe headstock, typical of the mid-19th century. During the years intervening between the machines of Figures 12 and 16, The general design was greatly improved by removing the lead screws from the center of the spindle. This made possible a shorter, more stiffer spindle and supported both ends of the spindle in one frame or headstock rather than in separate pieces attached to the bed. The screws are now mounted outside of the spindle bearings, one at a time, while the mating nuts were cut, partially into the circumference of a disc, which could be turned to bring any particular nut into working position as required. With this arrangement, a wide variety of leads, either right or left hand, could be provided, and additional leads could be fitted at any future time. Screw-cutting lathes of this design were popular for a very long time with instrument makers and opticians, who had little need to cut screws of great length. The demands of expanding industry for greater versatility in the production of engineering elements late in the 18th century set the stage for the evolution of more complex machines tending to place the threaded spindle lathes in eclipse. Maudsley's lathe of 1797 through 1800 appeared at this time, when industry was receptive to rapid innovation. Unfortunately, the gearing which once existed to connect the headstock spindle with the lead screw has long been lost. At this time, it is quite difficult to say with certainty whether the original gear set offered a variety of ratios, as was true of slightly later Maudsley's lathes, or a fixed ratio. The plausibility of the fixed ratio theory is supported by the very convenient means, seen in Figure 15, for removing the lead screw in preparation for substitution of one of another pitch. All that is required is to back off its supporting center at the tailstock end and withdraw the screw from its split nut and from the driving clutch near the headstock. This split nut also would have to be changed to one of a pitch corresponding to that of the screw. While more expensive than a solid nut, it neatly circumvents the need and saves the time involved to reverse the screw in order to get the tool back to the point of beginning preliminary to taking another cut. David Wilkinson's lathe of 1798, which was developed in Rhode Island at the same time, shows the same method of mounting and driving the master screw. At least in the United States, this method of changing the lead screw instead of using change gears remained popular for many years. Examples of this changeable screw feature are to be found in the lathes constructed for the pump factory of W&B Douglas Company, Middletown, Connecticut, in the 1830s. Middletown, at that time, one of the leading metal working centers and one of the chief industrial states, has been for many years the site of Simeon North Arms Factory, which rivaled Whitney's. In this atmosphere, it is reasonable to expect that machinery constructed by local mechanics, as was the custom in those days, would reflect the most accepted refinements in machine design. Roughly 20 years later, Joseph Nason of New York patented the commercially very important Fox Brassworker's lathe. While this does have a ratio in the pair of gears connecting the work spindle and master screw, it is clear from the patent that various pitches are to be obtained by changing screws, not by changing gears. The patent sums it up as follows. A nut upon the end of the stud is unscrewed when the guide screw is to be removed or changed. The two wheels should have in their number of teeth a common multiple. They are seldom or never removed, and their diameters are made dissimilar only for the purpose of giving to the guide screw a slower rate of motion than that of the mandrel, whereby it may be made of coarser pitch than that of the screw to be cut, and its wear materially lessened. The introduction of gearing between the spindle and the lead screw, for whatever purpose, could not help but introduce variable factors caused by inaccuracies in the gears themselves and in their mounting. These were of little consequence for common work, particularly when coupled to a screw which itself was of questionable accuracy. The increasing refinements demanded in scientific instruments and in machine tools themselves after they had reached a relatively stable form dictated that attention be dedicated to improve accuracy of the threaded components. An attack on this problem which interestingly reverts to the fundamental principle of motion derived from a master screw without the intervention of other mechanisms, is covered by a patent issued to Charles Vader Voord, one-time superintendent of the Waltham Watch Company. The problem is well stated in the patent. This invention relates to the manufacture of leading screws to be used for purposes requiring the highest attainable degree of correctness in the cutting of the screw threads of said screw, as, for example, in machines for ruling lines in glass plates to produce refraction, gratings for the resolution of the lines of the solar spectrum, such machines being required to rule many thousands of lines of an inch of space by a marking device which is reciprocated over the glass plate and is fed by the action of a leading screw after the formation of each line. Great difficulty has been experienced in constructing a leading screw for this and other purposes in which the thread is so nearly correct as to produce no perceptible variation in the microscopic spaces between the ruled lines or gratings. Various causes prevent the formation of a thread on the rod or a blank, which is absolutely uniform and accurate from end to end of the rod. Among other causes are the variations of temperature from time to time, the imperfections of the operating leading screw, the springing of the leading screw and of the rod that is being threaded, and other unavoidable causes, all of which, although apparently trivial and producing only slight variations in the thread at different parts of the rod or blank, are of sufficient moment to be seriously considered when a screw of absolute accuracy is desired. It is interesting to note in Figure 19 that van der Voord's machine, to avoid the problems outlined in his patent, has returned to a starkly simple design. We are not told, however, how he originated this master screw, which is used to produce the accurately threaded workpieces. Later generations, in the search for ever greater accuracy, also return to the fundamental simplicity of a master screw, as we shall see when we consider the refinements in mechanism necessary to the extended development of the automobile and the airplane. As the power and speed of automobiles and aircraft increased, critical parts became more highly stressed. Gears and threaded parts were particularly troublesome details of the mechanism because of the stresses concentrated in them, and in the case of gears, because of the internal and external stresses originating in minute deviations from the ideal of tooth form and spacing. The problems were not entirely new, but had hitherto been solved by increasing the size of the parts, an avenue of limited utility to designers in the field where total weight, as well as the effects of mass and inertia, are so important. By making these parts of heat-treated steel, the strength could be made suitable while the size and mass of the parts were kept within bounds. The necessary processes of heat treating were not always applicable to finished parts, as they sometimes destroyed both finish and accuracy. Grinding, which was well developed for the simple plane, cylindrical and conical surfaces so widely used in mechanisms, had to be extended to threads and gears so that they could be finished after heat treating. Sometimes the gear teeth themselves were ground. For other applications, it was sufficient to improve the accuracy of the gear cutters. Attempts to produce gear hobs, free of the imperfections and distortions introduced by heat treatment, led to another return to the use of the master lead screw. Figure 20 illustrates a machine having this feature, which was patented in 1932 by Carl G. Olson. In speaking of the spindle driving mechanism disclosed in earlier patents, the patent goes on to say, "This driving mechanism includes an integral spindle, 20, one extremity thereof being designed for supporting a hob, 22, and the other extremity thereof being formed so as to present a lead screw, 24. The spindle, 20, is mounted between a bearing, 26, and a bearing, 28, the latter bearing providing a nut in which the lead screw, 24, rotates. From the description thus far given, it will be apparent that the rotation of the lead screw, 24, within the bearing or nut, 28, will cause the hob to be moved axially, the lead of the screw, 24, being equal to the lead of the thread in the hob." Claim 8, which concludes the descriptive portion of the patent, states in part, In a hob grinding machine of the class described, a rotary work-supporting spindle, means for effecting longitudinal movement of the spindle, a tool holder for supporting a grinding wheel in operative position with respect to the work supported by the spindle during the rotary and longitudinal movement thereof. Even before this patent was applied for, another patent was pending for the purpose of modifying the pitch of the lead screw without the use of change gears, in spite of the wide acceptance of such gear mechanisms for over 100 years. Figure 21 shows a plan view of the machine, and Figure 22 a detailed view of the sine bar mechanism actuated by the master screw 6 to modify the effective pitch of the lead screw in accordance with the realities of practice as stated in the preamble of the patent. This invention relates to material working machines, and particularly to machines such as hob grinders and the like, wherein the work is reciprocated through the agency of a lead screw. In the manufacture of hobs, it is common practice to employ the same machine for grinding hobs of varied diameters, and in order to employ such a machine in this manner, the pitch of the lead screw thereof, which actuates the work carrier, must conform to the axial pitch of the hob to be ground. This will be readily apparent when it is understood that the helix angles of hobs vary in accordance with the diameters, and consequently the difference between the normal pitch and the axial pitch correspondingly varies. While the requirement for the normal pitch may be the same for hobs of different diameters, it is necessary to change the axial pitch in accordance with a change in the hob diameter, and this axial pitch of the hob is equal to the pitch of the lead screw which actuates the work carrier in grinding machines heretofore used. Hence, in order to adapt such machines to cover a wide range of leads, it is necessary to provide a large number of interchangeable lead screws, and obviously this represents a large investment, and the interchanging of these screws requires the expenditure of considerable time in setting up the machine for each job. Thread grinding machines were being designed concurrent with the development of hob grinding machines. Many were entirely concerned with features peculiar to the problems of wheel dressing and to automatic characteristics. An invention to embody the use of a master screw and concerned with the precision grinding of worm threads for use in gearing was patented by Frederick A. Ward in this era. That part of the invention pertaining to the use of a master screw, a rotary work holder mounted on said carriage and provided with a driving spindle, an exchangeable master screw and a stationary nut detachably secured to said spindle and head, is shown in Figure 23. Machines embodying the principle of the master lead screw are found in constant use by industry at the present time for specialized application. Whenever technological changes again reopen the topic of thread cutting to a new degree of accuracy, or call for a re-evaluation of popular methods for any other reason, we may expect to see another resurgence of the master screw method, for no other design eliminates so many variables or rests on such firm and fundamental natural principles as the machine of Das Mittelalterliche Hausbuch of 1483, the earliest such machine now known. End of section 10. Section 11 of Smithsonian Institution, United States National Museum, Bulletin 240. Contributions from the Museum of History and Technology, Papers 34 through 44 on Science and Technology by the Museum of History and Technology. This LibriVox recording is in the public domain. Paper 38, The Earliest Electromagnetic Instruments by Robert A. Chipman. Part 1. The history of the early stages of electromagnetic instrumentation is traced here through the men who devised the theories and constructed the instruments. Despite the many uses made of voltaic cells after Volta's announcement of his pile invention in 1800, 2 decades passed before Ørsted discovered the magnetic effects of a voltaic circuit. As a result of this, and within a 5-month period, Three men, apparently independently, announced the invention of the first electromagnetic instrument. This article details the merits of their claims to priority. The author, Robert A. Chipman, is chairman of the Department of Electrical Engineering at the University of Toledo in Toledo, Ohio, and consultant to the Smithsonian Institution. Electrostatic instruments before 1800. It is the fundamental premise of instrument science that a device for detecting or measuring a physical quantity can be based on any phenomenon associated with that physical quantity. Although the instrumentation of electrostatics in the 18th century, for example, relied mainly on the phenomena of attraction and repulsion, and the ubiquitous sparks and other luminosities of frictional electricity, even the physiological sensation of electric shock was exploited semi-quantitatively by Henry Cavendish in his well-known anticipation of Ohm's researches. Likewise, Volta, in 1800, described at length how the application of his pile to suitably placed electrodes on the eyelids, on the tongue, or in the ear caused stimulation of the senses of sight, taste, and hearing. On the other hand, he reported that electrodes in the nose merely produced a more or less painful prickling feeling with no impression of smell. The discharges from the Leyden jars of some of the bigger frictional machines, such as Van Marum's at Leyden, were found by 1785 to magnetize pieces of iron and to melt long pieces of metal wire. The useful instruments that emerged from all of this experience were various deflecting electrometers and electroscopes. The words were not carefully distinguished in use, including the important gold leaf electroscope ascribed to Abraham Bennett in 1787. In 1786, Galvani first observed the twitching of the legs of a dissected frog produced by discharges of a nearby electrostatic machine, thereby revealing still another effect of electricity. He then discovered that certain arrangements of metals, in contact with the frog's nerves, produced the same twitching, implying something electrical in the frog metal situation as a whole. Although Galvani and his nephew Aldini drew from these experiments erroneous conclusions involving animal electricity, which were disputed by Volta in his metal contact theory, it is significant from the instrumentation point of view that the frog's legs were unquestionably, by far, the most sensitive detector of metal contact electrical effects available at the time. Without their intervention, the development of this entire subject area, including the creation of chemical cells, might have been delayed many years. Volta himself realized that the crucial test between his theory and that of Galvani required confirming the existence of metal contact electricity by some electrical but non-physiological detector. He performed this test successfully with an electroscope, using the condensing technique that he had invented more than a decade earlier. Instrumenting voltaic or galvanic electricity, 1800 through 1820. In his famous letter of March 20th, 1800, written in French from Como, Italy, to the President of the Royal Society in London, Volta made the first public announcement of both his pile, the first English translator used the word column, and his crown of cups. The same translator used chain of cups for Volta's Coronae de Tassis. The former consisted of a vertical pile of circular discs, in which the sequence copper, zinc, pasteboard was repeated 10 or 20 or even as many as 60 times, the pasteboard being moistened with salt water. The crown of cups could be most conveniently made with drinking glasses, said Volta, with separated inch-square plates of copper and zinc in salt water in each glass, the copper sheet in one glass being joined by some intermediate conductor and soldered joints to the zinc in the next glass. Volta considered the crown of cups and the pile to be essentially identical, and as evidences of the electrical nature of the latter, said, "If it contains about 20 of these stories or couples of metal, It will be capable not only of emitting signs of electricity by Cavallo's electrometer, assisted by a condenser, beyond 10 degrees or 15 degrees, and of charging this condenser by mere contact so as to make it emit a spark, etc., but of giving to the fingers with which its extremities, bottom and top of the column, have been touched, several small shocks, more or less frequent, according as the touching has been repeated. Each of these shocks has a perfect resemblance to that slight shock experienced from a Leyden flask weakly charged, or a battery still more weakly charged, or a torpedo in an exceedingly languishing state, which imitates still better the effects of my apparatus by the series of repeated shocks which it can continually communicate. The effects provided by Volta's pile and crown of cups are therefore electroscope deflection, sparks, and shocks. Later in the letter, he describes the simulation of sight, taste, and hearing, as noted earlier, but nowhere does he mention chemical phenomena of any kind, or the heating of a wire joining the terminals of either device. Hence, except for the additional physiological responses, he adds nothing to the catalogue of observations on which instruments might be based. His familiarity with the moods of the torpedo, the electric eel, seems to be intimate. The reading of Volta's letter to the Royal Society on June 26, 1800, its publication in the Society's Philosophical Transactions, in French, immediately thereafter, and its publication in English in the Philosophical Magazine for September of 1800, gave scientists throughout Europe an easily constructed and continuously operating electric generator with which innumerable new physical, chemical, and physiological experiments could be made. Editor-engineer William Nicholson read Volta's letter before its publication, and by the end of April, he and Surgeon Anthony Carlisle had built a voltaic pile. Applying a drop of water to improve the connection of a wire lying on a metal plate, they happened to notice gas bubbles forming on the wire, and pursued the observation to the point of identifying the electrical decomposition of water into hydrogen and oxygen. Within 2 or 3 years, innumerable electrochemical reactions had been described, some of which, one might think, could have served as operating principles for electrical instruments. Although the phenomena of gas formation and metal deposition were in fact widely used as crude indicators of the polarity and relative strength of voltaic piles and chemical cells during the period 1800 through 1820, and the gas bubbles were made the basis of a telegraph receiver by S.T. Sommering, the quantitative law of electrolysis were not worked out by Faraday until after 1830, and not until 1834 was he satisfied that the electrolytic decomposition of water was sufficiently well understood to be made the basis for a useful measuring instrument. Describing his water electrolysis device in that year, he wrote, "The instrument offers the only actual measurer, italics his, of voltaic electricity, which we at present possess, for, without being at all affected by variations in time, or intensity, or alterations in the current itself of any kind, or from any cause, or even of intermissions of actions, it takes note with accuracy of the quantity of electricity which has passed through it, and reveals that quantity by inspection. I have therefore named it a volta-electrometer." In passing, Faraday commented that the efforts of Gay-Lussac and Thénard to use chemical decomposition as a measure of the electricity of the voltaic pile in 1811 had been premature, because the principles and precautions involved were not then known. He also noted that the details of metal deposition in electrolysis were still not sufficiently understood to permit its use in an instrument. The heating of the wires in electric circuits must have been observed so early and so often, with both electrostatic and voltaic apparatus, that no one has bothered to claim or trace priorities for this effect. The heating of the wires in electric circuits must have been observed so early and so often, with both electrostatic and voltaic apparatus, that no one has bothered to claim or trace priorities for this effect. The production of incandescence, however, and the even more dramatic combustion or explosion of metal foil strips and fine wires, has a good deal of recorded history. Among the first to burn leaf metal with a voltaic pile was J.B. Tromsdorf of Erfurt, who noted in 1801 the distinctly different colors of the flames produced by the various common metals. In the succeeding few years, Humphrey Davy, at the Royal Institution, frequently, in his public lectures, showed wires glowing from electric current. Early electrical instrumentation, based on the heating effect, took an unusual form. Shortly after 1800, W. H. Wollaston, an English M.D., learned a method for producing malleable platinum. He kept the process secret, and for several years enjoyed an extremely profitable monopoly in the sale of platinum crucibles, wire, and other objects. About 1810, he invented a technique for producing platinum wire as fine as a few millionths of an inch in diameter, that has since been known as Wollaston wire. For several years preceding 1820, no other instrument could compare the strengths of two voltaic cells better than the test of respective maximum lengths of this wire, that they could heat to fusion. One can sympathize with Cummings' comment in 1821 about the difficulty in soldering wires that are barely visible. Electrical instrumentation, 1800 through 1820. The 20 years following the announcement of the voltaic pile invention were years of intense experimental activity with this device. Many new chemical elements were discovered. Beginnings were made on the electrochemical series of the elements. The electric arc and incandescent platinum wires suggested the possibilities of electric lighting, and various electrochemical observations gave promise of other practical applications such as metal refining, electroplating, and quantity production of certain gases. Investigators were keenly aware that all of the available means for measuring and comparing the electrical aspects of their experiments, however vaguely these electrical aspects may have been conceived, were slow, awkward, imprecise, and unreliable. The atmosphere was such that prominent scientists everywhere were ready to pounce immediately on any reported discovery of a new electrical effect to explore its potentialities for instrumental purposes. Into this receptive environment came H.C. Ørsted's announcement of the magnetic effects of a voltaic circuit on July 21, 1820. Ørsted's discovery. Many writers have expressed surprise that with all the use made of voltaic cells after 1800, including the enormous cells that produced the electric arc and vaporized wires, no one for 20 years happened to see a deflection of any of the inevitable nearby compass needles, which were a basic component of the scientific apparatus kept by any experimenter at this time. Yet so it happened. The surprise is still greater when one realizes that many of the contemporary natural philosophers were firmly persuaded, even in the absence of positive evidence, that there must be a connection between electricity and magnetism. Ørsted himself held this latter opinion, and had been seeking electromagnetic relationships more or less deliberately for several years before he made his decisive observations. His familiarity with the subject was such that he fully appreciated the immense importance of his discovery. This accounts for his employing a rather uncommon method of publication. Instead of submitting a letter to a scientific society or a report to the editor of a journal, he had privately printed a 4-page pamphlet describing his results. This he forwarded simultaneously to the learned societies and outstanding scientists all over Europe. Written in Latin, the paper was published in various journals in English, French, German, Italian, and Danish during the next few weeks. In summary, he reported that a compass needle experienced deviations when placed near a wire connecting the terminals of a voltaic battery. He described fully how the direction and magnitude of the needle deflections varied with the relative position of the wire and the polarity of the battery, and stated, From the preceding facts, we may likewise collect that this conflict performs circles. Orsted's comment that the voltaic apparatus used should be strong enough to heat a metallic wire red hot does not excuse the 20-year delay of the discovery. Beginnings of electromagnetic instrumentation. The mere locating of a compass needle above or below a suitably oriented portion of a voltaic circuit created an electrical instrument the moment Orsted's effect became known, and it was to this basic juxtaposition that Ampere quickly gave the name of galvanometer. It cannot be said that the scientists of the day agreed that this instrument detected or measured electric current, however. Volta himself had referred to the current in his original circuits, and Ampere used the word freely and confidently in his electrodynamic researches of 1820 through 1822. But Oersted did not use it first, and many of the German physicists who followed up his work avoided it for several years. As late as 1832, Faraday could make only the rather non-committal statement, "By current, I mean anything progressive, whether it be a fluid of electricity or vibrations or generally progressive forces." Nevertheless, whatever the words or concepts they used, experimenters agreed that Oersted's apparatus provided a method of monitoring the strength of a voltaic circuit and a means of comparing, for example, one voltaic battery or circuit with another. It was perfectly clear from Oersted's pamphlet that if a compass needle was deflected clockwise when the wire of a particular voltaic circuit lay above it in the magnetic meridian, the same needle would also be deflected clockwise if the wire was turned end for end and placed below the compass needle without changing the rest of the circuit. Anyone perceiving this fact might deduce, as a matter of logic, that if the wire of the circuit was first passed above the needle in the magnetic meridian, then folded and returned in a parallel path below the needle, the deflecting effect on the needle would be repeated, and a more sensitive indicator would result, assuming that any additional wire introduced has not affected the circuit excessively. Since 1821, historical accounts of the origins of electromagnetism seem to have limited their credit assignments for the conception and observation of this electromagnetic doubling effect, or multiplying effect if the folding is repeated, to 3 persons. Almost without exception, however, these accounts have given no specific information as to precisely what each of these 3 accomplished, what physical form their respective creations took, what experiments they performed, and what functional understanding they apparently had of the situation. The usual statement is simply that a compass needle was placed in a coil of wire. The main purpose of the present review is to recount some of the details. End of section 11. Section 12 of Smithsonian Institution, United States National Museum. Bulletin 240, Contributions from the Museum of History and Technology. Papers 34 through 44 on Science and Technology by the Museum of History and Technology. This LibriVox recording is in the public domain. Paper 38, The Earliest Electromagnetic Instruments by Robert A. Chipman. Part 2. The following are the 3 candidates whose names are variously associated with the invention of the first constructed electromagnetic instrument, or multiplier, or primitive galvanometer. Johann Salomo Christoph Schweiger, 1779 to 1857. In 1820, had already been editor for several years of the Journal für Chemie und Physik and was professor of chemistry at the University of Halle. Johann Christian Poggendorff, 1796 to 1877. In 1820, had only recently entered the University of Berlin as a student following several years as an apothecary's apprentice, and a brief period as an apothecary. 4 years later, he succeeded Gilbert as editor of the influential Annalen die Physik, a position he held for more than 50 years. James Cumming, 1771 to 1861. In 1820, was professor of chemistry at Cambridge University. Chronology and priority. The earliest established date in the multiplier record is September 16, 1820, when Schweiger read his first paper to the Natural Philosophy Society of Halle. There seems to be no reason to doubt that this report justifies the frequently used label Schweiger's multiplier. In an exuberant support of Schweiger's position, Später, with no mention of coming and no hint of invention details, shows that Poggendorff, in 1821, admitted Schweiger's priority, but suffered some lapse of memory 40 years later when writing sections of his biographical dictionary, leaving a distinct suggestion that the invention was his. Further confusion for later generations resulted from some ambiguous entries in the Allgemeine Deutsche Biographie of 1888. The name multiplier seems not to have originated with Schweiger himself. Später credits it to Meinecke as working editor of Schweiger's journal, but Seebeck seems to have used it much earlier. Conceding priority of conception to Schweiger, Cumming has not been a real competitor on this point, does not alter the fact that all three seem to have reached their results independently of one another, that the first work of each on this subject was published within a period of 5 months, that there were significant differences in their conceptions of the uses and the optimum design of their devices, and that between them they provided an adequate foundation for the subsequent development of the galvanometer to become the primary electrical measuring instrument. In the matter of a publication, Schweiger, as editor of what was popularly called Schweiger's Journal, had an obvious advantage, and presented his experiments beginning on page 1 of the first volume of his journal for 1821, published January 1 of that year. Ørsted's paper had appeared 2 volumes previously. He began by referring to Ørsted's discovery as the most interesting to be presented in 1,000 years of the history of magnetism. He was, in fact, so impressed with the epical nature of Ørsted's achievement that he commemorated it by giving his journal a second title, so that Volume 1 of the new title could begin in the year after Ørsted's publication. Poggendorff, as a relatively junior student, had no such easy access to publicity. He had a staunch admirer in one of his professors, Paul Ehrmann, at the University of Berlin. Ehrmann added a 7-page postscript on Poggendorff's invention to his book, Outline of the Physical Aspects of the Electrochemical Magnetism Discovered by Professor Ørsted, published before April 1821, with an introductory paragraph. Herr Poggendorff, who was one of the most excellent ornaments of the lecture room and laboratory of the university here, carried out a very coherent and well-conceived investigation of electrochemical magnetism, leading step by step to a method of amplifying this activity phenomenon by means of itself. The postscript begins by referring to the condenser, condensator, just brought to my attention by Herr Poggendorff, and explains that he cannot release his treatise without preliminary announcement of the subject of the highest importance. It can be inferred from the text that the name condenser was chosen because of the device's enhancing of magnetic measurements, analogously to the enhancing of electric measurements by Volta's electrostatic condenser. Immediately on reading the book, Schweiger published extracts, mainly of the postscript, with indignant comments on Ehrmann's remissness, or worse, in having failed to mention Schweiger's prior work. However, Ehrmann was not alone in his unawareness, if it was that, of Schweiger's discovery. Rival editor Gilbert of the Annalen der Physik reviewed Ehrmann at much greater length than Schweiger, reprinting most of the postscript with evident enthusiasm, and stating in his preamble that the invention is attributed to a young physicist studying here in Berlin, Herr Poggendorff. Only in a footnote is the reader directed to another footnote in the next article in the volume, where Gilbert finally states that he cannot leave unmentioned the fact that this amplifying apparatus seems to be due to Herr Professor Schweiger. He then quotes rather fully from Schweiger's first 2 papers. Ørsted in 1823 explained the situation thus: "The work of Mr. Poggendorff, having been mentioned in a book on electromagnetism by the celebrated Mr. Ehrmann, published very shortly after its discovery, became known to many scientists before that of Mr. Schweiger. This is the reason for the same apparatus carrying different names. The same confusion is well illustrated by the paper to which Gilbert attached his confessional footnote mentioned above. Written by Professor Raschig of Dresden on April 3, 1821, the paper is entitled Experiments with the Electromagnetic Multiplier, but the device, throughout the paper, is repeatedly referred to in the phrase Poggendorff's condenser, or rather multiplier, an awkward combination that suggests editorial intervention. The work of James Cumming at Cambridge is described in two papers, which he read to the Cambridge Philosophical Society in 1821, which were then duly published in the Transactions of that society. The first, on the connection of galvanism and magnetism, was read April 2, 1821, and the second, on the application of magnetism as a measure of electricity, was first read a few weeks later on May 21st. Though he quotes some unrelated 18th century experiments by Ritter in Germany, an 1807 publication of Orsted's, and electromagnetic experiments with solenoids performed by Arago and Ampere in the late 1820, Cumming makes no mention of Schweiger or Poggendorff, and never uses the word multiplier. It therefore seems probable that his work was done without the knowledge of the German publications or inventions. Original electromagnetic multipliers. Of the three sets of instruments made, respectively by Schweiger, Poggendorff, and Cumming, those of Schweiger are the most elementary, and the least realistic from a practical point of view. He makes little effort to investigate the effect of any design parameters, but presents some odd conductor configurations that involve unimportant variations of the basic principle. The following extracts from his first three papers contain the major references to his conception, construction, and use of his multiplier. Paper read in Halle, September 16, 1820. That a powerful voltaic pile is required for these experiments of Oersted, I have confirmed in my physics lectures using an electric pile that was so strong it would easily produce potassium metal the second and third day after it was built. However, I soon saw that the electromagnetic effect was related, not to the pile, but to the simple circuit, and I was thereby led to perform the experiment with much greater sensitivity. To amplify these electromagnetic phenomena of the simple circuit, it seemed to me necessary to adopt a different arrangement from that initiated by Volta, in order that the electrical phenomena of his simple circuit might be raised to a higher degree. Since a reversal of the effect occurs according to whether the connecting wire lies over or under the needle, and likewise according to whether the wire leads from the positive or negative pole, thence I say it is an easy inference that a doubling of the effect is attainable, which is verified in practice. I present to the Society the simple doubling apparatus, Verdoppelungsapparat, where the compass is placed between the two wires passing around it. A multiplication of the effect is easily obtained when the wire is not just once, but many times wound around. A single turn suffices, however, to demonstrate Oersted's experiments, using small strips of zinc and copper dipped in ammonium chloride solution. Amid innumerable rambling theorizations, such as that hydrogenation affects magnetism as oxidation affects galvanism, or sulfur, phosphorus, and carbon are especially significant in magnetism, since iron in combination with any of these inflammable materials becomes a magnet material. Schweiger announces that he looked for the reactive force of the needle on the connecting wire in the simple Oersted experiment, and he used his amplifying apparatus to look for magnetic effects of an electrostatic machine, but without success in both cases. He suggests that he will continue with many more electromagnetic experiments because with the use of the doubling apparatus, the needle, instead of needing for excitation a cell capable of generating sparks, approaches more closely the sensitivity of a twitching nerve. However, additional special experiments are required to find to what limits the amplification can be increased by the method I have created in the construction of this doubling apparatus using multiple turns of wire. Paper read in Halle, November 4th, 1820. The first half of this paper describes successful observations of the reaction force of a magnetic needle on the connecting wire of a voltaic circuit, achieved by pivoting the connecting wire in the form of brass needles above and below the compass needle. Though the multiplier configuration of needle and wire is in fact present here, Schweiger does not mention it, evidently regarding this as a separate project. He continues, "In my lecture of September 16th, I showed that Ørsted's results depend not on the voltaic cell, but on the connecting circuit. The principle I have used for amplification of the effects for the construction of an electromagnetic battery, as it were, was the winding of wire around the compass, and I now present to the Society a bow pattern of multiple wound wax-insulated wire, Figure 3. There were no illustrations with Schweiger's first paper. While a single wire, using the weak electric circuit here, deflects the magnetic needle only 30 degrees or 40 degrees, if the compass is placed in one of the openings of this pattern, the needle is deflected 90 degrees to the east, or in the other opening, 90 degrees to the west, using the same weak electric circuit. The bow pattern device has novelty interest only, adding nothing to the elucidation of the multiplier phenomenon. The same is true of Schweiger's next proposal, shown in Figure 4. I will now add another apparatus, which is just an extension of the previous one, whereby the needle can take up any angle from 0 to 180 degrees. A short length of circular glass tubing, of inside diameter large enough to contain a compass needle, stands with its axis vertical, and has single or multiple loops of wire wound on it in vertical diametral planes. In the illustration, successive plane coils are inclined at 30 degrees to one another. The electric current flows through the whole wire, and the needle moves under all of these currents, and coming always into another loop can take any desired angle. With much further theorizing about the correlation of magnetism with the cohesion of bodies, Schweiger states again his evaluation of his discovery. Ørsted succeeded in electromagnetic research by using a spark-producing cell, which could make a wire glow. My amplifying electromagnetic device needs only a weak circuit of copper, zinc, and ammonium chloride solution." Further words about the new magnetic phenomena. This was presumably written between November 4th, 1820, and the January 1, 1821 publication date of his journal. These wonderful new electrical effects are most easily rendered perceptible with the help of the previously described wire loops. To focus attention on just one of the windings of Figure 3, we sketch a new drawing, Figure 5. Since it is of major importance that these loops be made of silk-covered wire lying evenly on one another, it is convenient to wind the loops on two small slotted sticks of wood, although it is also possible to hold the wires together with wax or shellac, or tie them together in an orderly manner with silk thread. In Figure 5, AA and CC represent little slotted rods of wood, on which the silk-covered wire is wound. Only 3 windings are shown in the figure, but I generally adopt 3 times that many. Now, T is connected with the copper and D with the zinc, and the compass B, set between the rods AA and CC with the coil perpendicular to the magnetic meridian and the terminals D, T at the east. The instant Z and K are dipped in the ammonium chloride solution, the needle turns around and stays with the North Pole point south. If now the compass is taken out of the coil and put in position B, all effects are reversed and are considerably weaker for obvious reasons. It is of the same significance whether we bring the compass from uppercase B to lowercase b in Figure 5 or from Mesh 1 to Mesh 2 in Figure 3, only that in the latter case, because the compass is enclosed by the two sides, a stronger effect results. If now the coil is rotated, so that the face previously north now faces south, then on connecting the electric circuit there is absolutely no trace of effect on the needle, assuming that the terminal wires are not reversed. It seems unnecessary to note that our magnetic coil can be placed in the direction of the magnetic meridian or at any arbitrary angle with it. Following several pages of further talk about the relation of cohesion to magnetism and about unipolar and bipolar conductors, the only additional item of interest is the observation that discharges of a Leyden jar, Kleitischen Flasche, strong enough to burn strips of leaf gold and to magnetize an iron rod in a coil, produce no compass needle deflections, even with the help of the amplifying apparatus. Schweiger therefore described the basic multiplier idea clearly enough in his first paper, but offered no sketch of the simplest construction until the third paper. In the second paper, meanwhile, he had illustrated two peculiar designs involving the principle in less elementary ways. His indifference to whether the wire loops lie in the magnetic meridian, Figure 3, or perpendicular to it, Figure 5, or at any other arbitrary angle to it, reveals a poor appreciation of the measuring instrument potentialities. His conception seems to be primarily that of a detector. Poggendorff's invention, at first reported by Ehrman and presented to a wider audience by Gilbert, was described as consisting of typically 40 to 50 turns of 1/10 line diameter silk-covered copper wire tied tightly together, with the whole pressed laterally to form an elliptical opening in which a pivoted compass needle could move freely while maintaining clearance of about 2 lines from the wire at all points. "This magnetic condenser can be a great boon to electrochemistry," said Ehrman, "for it avoids all the difficulties of electrical condensers." He noted that using the condenser, Poggendorff had already established the electric series for a great number of bodies, discovered various anomalies about conductivities, and found a way of detecting dissymmetry of the poles of a compass needle. On the other hand, even with the condenser, no magnetic effects have so far been obtainable from a strong tourmaline or from a 12,000 pair Zamboni dry cell. Poggendorff's own account of his work finally appeared as a very long article in the journal known as Oken's Isis. The editorial controversies mentioned earlier may have occasioned this use of a periodical of such minor status in the fields of physics and chemistry. The source of Poggendorff's vision of the multiplier principle was a little different from Schweiger's inspiration. Aiming at some detailed analysis of Ørsted's observation, Poggendorff ran the connecting wire of his cell circuit along a vertical line to just above or below the pivot point of the compass needle, then, after a right-angle bend, horizontally above or below one of the poles of the needle. As he studied the deflections produced for all 4 possible positions of such a wire, with both cell polarities, he came to realize that if a rectangular wire loop in a vertical plane enclosed a compass needle, all parts of the horizontal sides of the loop would produce additive deflections. By a separate experiment, he showed that the vertical sides of the loop would also increase the deflections. He saw at the same time that the effect of additional turns would be cumulative. The multiple surrounding of the needle by a silk-covered wire in a plane perpendicular to the long axis of the needle affords the physicist a very simple and sensitive means of detecting the slightest trace of galvanism, or of magnetism produced by it, so that I have given the names of magnetic condenser to this construction, though I attach no special value to this name. In analyzing the astonishingly increased power which the condenser gives to the magnetic effect of a circuit, the first question that arises is how the effect varies with the number of turns, whether it increases indefinitely or reaches a maximum beyond which additional turns have no effect. The answer to this first question is linked to the solution of another, that is, whether the degrees of deflection are a direct expression of the measure of the magnetic force or not. To instruct myself on this point, I made use of 3 separate circuits, each containing an 8-turn condenser, and put these as close together as possible in the magnetic meridian, with the needle between the windings. Each single circuit gave a deflection of 45 degrees. When 2 were connected, the deflection was 60 degrees, and when finally all three were put in magnetic operation, the deflection grew to only 70 degrees. It appears clearly from this that the angle of deflection is not a simple ratio with the magnetic force acting on the needle. Neither Poggendorff nor Schweiger seem to have ruled out, on logical grounds alone, the possibility of deflections greater than 90 degrees, with the loop plane in the magnetic meridian, though Poggendorff does add a vague note that if the needle deflected too far, it would encounter forces of the opposite sign. Poggendorff experimented with the size of the circuit wires, finding that larger wires led to greater deflections. He noted that the size of the cell plates and the nature of the cell's moist conductors would certainly have a great effect, but that to investigate these in detail would take undue time, and he therefore proposed to keep this part of the apparatus constant, using one pair of zinc and copper plates, 3.6 inches in diameter, separated by cloth soaked in ammonium chloride solution. Poggendorff's principal quantitative study of his magnetic condenser used 13 identical coils, each with 100 turns. In order that the turns should all be at approximately the same distance from the needle, the coils were wound of the finest brass wire that could be silk insulated, the wire diameter being 0.02 lines, or adding coils one at a time across the cell, that is, connecting them in parallel. The deflections were as follows. 100 turns gave a deflection of 45 degrees. 200 turns, 50 degrees. 300 turns, 55 degrees. 400 turns, 59 to 60 degrees. 500 turns, 62. 600 turns, 63. 700 turns, 64. 800 turns, 65. 900 turns, 65.5 degrees. 1,000 turns, 66 degrees. 1,100, 1,200, and 1,300 turns, 66 degrees. Adding some coils with fewer turns and connecting various combinations as a continuum, that is, in series, the deflections using the same cell were 1 turn gave a deflection of 10 degrees, 5 turns gave a deflection of 22 degrees, 10 turns gave a deflection of 27 degrees, 25 turns gave a deflection of 30 degrees, 50 turns gave a deflection of between 35 and 40 degrees, 75 turns gave 40 degrees, 100 turns, 200 turns, 300 turns, 400 turns all gave a deflection of 40 degrees, 500 turns gave a deflection of 41 degrees, 600 turns, 700 turns, 800 turns, 900 turns, and 1,000 turns all gave a deflection of 40 degrees. Making a few coils from wire with 1/8 line diameter, the deflections, again using the same cell, were 5 turns, 20 to 22 degrees in deflection, 25 turns, 40 to 45 degrees in deflection, 50 turns, 45 degrees in deflection, 100 turns, 65 degrees, over 100 turns, 65 degrees. Since the needle used in these experiments was almost as long as the inside clearance of the coils, no simple tangent law can be applied, and it is not possible to discover an equivalent circuit in modern terms. However, the constancy of the deflections for a large number of turns in each case indicates that the cell voltage and resistance were fairly constant, and a rough estimate suggests that the cell resistance was comparable to the resistance of one of the 100-turn coils of fine wire. Such a value means that cell resistance limited the maximum deflections for the parallel connected multipliers, while coil resistance fixed the limit in the series case. For all of these reasons, it was impossible that any useful functional law could be obtained from the data. Poggendorff concluded only that the amplifying power of the condenser does not increase without limit, but has a maximum value dependent on the conditions of plate area and wire size. He added 2 other significant comments derived from various observations: that the basic Oersted phenomenon is independent of the Earth's magnetism, and that the phenomenon is localized. That is, it is not affected by distant parts of the circuit. Only a small fraction of Poggendorff's paper is devoted to elucidating the properties of the condenser. A similar amount is concerned with refuting various proposals, such as those of Berzelius and Ehrman, about distributions of magnetic polarity in a conducting wire to account for Ørsted's results. More than half of the paper describes results obtained by using the condenser to compare conductivities and cell polarities under conditions where no effect had previously been detectable. Notable is the observation of needle deflections in circuits whose connecting wires are interrupted by pieces of graphite, manganese dioxide, various sulfur compounds, etc., materials which had previously been considered as insulators in galvanic circuits. Poggendorff gives these the name of semiconductor, Halbleiter. Cummings' first mention of the multiplier phenomenon in his paper of April 2, 1821, is quite casual, and describes only a one-turn construction. He speaks first of a single-turn ring of thick brass wire, and after noting that the sides of a circuit produce additive effects on a needle, he comments that a flattened rectangular loop produces nearly quadruple the effect of a single wire. The paper is primarily a review of Ørsted's work, with references to electromagnetic observations before Ørsted, on accounts of various related but non-multiplier experiments that Cumming has made. His second paper of May 21st contains a fine plate, Figure 6, illustrating arrangements used in investigating the subject of the paper's title, The Application of Magnetism as a Measure of Electricity. Neither Poggendorff nor any of his commentators ever illustrated his condenser. Although this plate is never referred to in the paper itself, a nearby description gives a few comments. The two wire patterns shown are noted as simply forms of spiral for increasing the electromagnetic intensity. The mounted wire loop, with enclosed compass needle and terminal mercury cups, is clearly identical in principle with the devices of Schweiger and Poggendorff and is called a galvanoscope. The largest structure illustrated does not involve the multiplying effect. It is called a galvanometer, consistent with Ampere's definition of that word. To use it, two leads of a voltaic circuit are inserted into the mercury cups, AC and BD, and the board, EFGH, carrying the cups, is moved vertically until some standard deflection is obtained on the compass needle below. The relative strength of the circuit is then given by the calibrated position of the sliding section. Uncertainties are undoubtedly introduced by the arbitrary positions of the connecting wires from the test circuit to the mercury cups, but Cumming drew some interesting conclusions from various measurements he made. Observing needle deflections for various positions of the wire AB with a constant voltaic circuit, he found that the tangent of the deviation varies inversely as the distance of the connecting wire from the magnetic needle. Here is a combination of the deflection law for a needle in a transverse horizontal field and the magnetic force law for a long straight wire. The latter had been determined experimentally by Biot and Savart in November of 1820 by timing the oscillations of a suspended magnet. Cumming considers his straight wire calibrated galvanometer to be a device for measuring galvanic electricity. On the other hand, his multiple loop galvanoscopes are for discovering galvanic electricity. With the multiplier instrument, he found galvanic effects, that is, the needle deflections, using copper and zinc electrodes with several acids not previously known to create galvanic action. A potassium-mercury amalgam electrode created a powerful cell with zinc as the positive electrode, establishing both the metallic nature of potassium and the fact that it is the most negative of all metals. In a third paper, presented April 28, 1823, Cumming reports use of the galvanoscope in experiments of the thermoelectric phenomena recently discovered by Seebeck. His note that for the more minute effects, a compass was employed in the galvanoscope having its terrestrial magnetism neutralized, seems to be the earliest mention of this version of the astatic principle, a technique whose dramatic effects were especially valuable in low-resistance thermoelectric circuits, where the extra resistance of additional multiplier turns largely offsets their magnetic contribution. In detail, the needle is neutralized by placing a powerful magnet north and south on a line with its center, and another, which is much weaker, east and west, at some distance above it. By means of the first, the needle is placed nearly at right angles to the meridian, and the adjustment is completed by the second. On varying the length of the connecting wire of the circuit, Cumming found the deflections of the multiplier needle to be a nearly reciprocal relation. He speaks of the conducting power of the wire, and seems not far from visualizing Ohm's law, of which no published form appeared until 1826. Ohm's own experiments were made with very similar apparatus. Conclusions. An effort has been made to show that electrical experimenters prior to Ørsted's discovery in 1820 were in desperate need of some electrical instrument for galvanic or voltaic circuits that would combine sensitivity, simplicity, reliability, and quick response. The nearly simultaneous creation by Schweiger, Poggendorff, and Cumming of an arrangement consisting of a coil of wire and a compass needle provided the first primitive versions of a device to fill that need. It appears that Schweiger is clearly entitled to credit for absolute priority in the discovery, but the original sources suggest that both his understanding of the device and the subsequent researches he performed with it were markedly inferior to those of the other independent discoverers. In using the generic label Schweiger's multiplier, there have been historical examples of attributing to Schweiger considerably more sophistication than it justified. Figure 7 shows an instrument designed by Ørsted in 1823, which he says differs in only minor particulars from that of Mr. Schweiger. On comparing Figure 7 with Figures 3, 4, or 5, the remark seems overly generous. The history of the multiplier instruments has had its fair share of erroneous reports and misleading clues. A fine example is the illustration of Figure 8, taken from what is often quoted as the first report in English on Poggendorff's galvano-magnetic condenser. The sketch is the editor's interpretation of a verbal description given him by a visiting Danish chemist, who in turn had received the information in a letter from Ørsted. It incorporates, faithful to the description, a spiral wire, established vertically, with a needle in the axis of the spiral. Yet by misunderstanding of the axial relations and of the ratio of length to diameter for the coil, a completely meaningless arrangement has resulted. The confusion is compounded by the specifying of an unmagnetized needle. Schweiger and Poggendorff, through their editorial positions, were among the best known of all European scientists for several decades. On one basis or another, their reputations are firmly established. Comparison of the accounts of the early multipliers, however, suggests that the Reverend James Cumming, professor of chemistry at the University of Cambridge, was a very perceptive philosopher. This was well understood by G.T. Bettany, who wrote in the Dictionary of National Biography that Cumming's early papers, though extremely unpretentious, were landmarks in electromagnetism and thermoelectricity, and concluded that he had been more ambitious and of less uncertain health. His clearness and grasp and his great aptitude for research might have carried him into the front rank of discoverers. Acknowledgements. I wish to thank Dr. Robert P. Multhoff, Chairman of the Department of Science and Technology in the Smithsonian Institution's Museum of History and Technology, for encouragement in the writing of this paper, and for the provision of opportunity to consult the appropriate sources. To Dr. W. James King of the American Institute of Physics, I am grateful for many provocative discussions on this and related topics. End of section 12. Section 13. of Smithsonian Institution, United States National Museum, Bulletin 240, Contributions from the Museum of History and Technology, papers 34 through 44 on Science and Technology, by the Museum of History and Technology. This LibriVox recording is in the public domain. Paper 39, Fulton's Steam Battery, Blockship and Catamaran, by Howard I. Chappell. Part 1. Robert Fulton's steam battery, a catamaran-type blockship, was built during the War of 1812. Until recently, not enough material has been available to permit a reasonably accurate reconstruction of what is generally acknowledged to be the first steam man-of-war. With the discovery in the Danish Royal Archives at Copenhagen of plans of this vessel, it is now possible to prepare a reconstruction and to build a model. This article summarizes the history of the vessel, describes the plans and the reconstruction, and also evaluates its design with particular attention to the double-hull construction. The author, Howard I. Chappell, is Curator of Transportation in the Smithsonian Institution's Museum of History and Technology. The identity of the first steam man-of-war has been known for many years, and a great deal has been written and published on the history of this American vessel. Until recently, the only available drawing of the ship has been a patent drawing made for Robert Fulton. This does not comply with contemporary descriptions of the steamer, and the drawing or plan is out of proportion with the known dimensions. The lack of plans has heretofore made it impossible to illustrate the vessel with any degree of precision or to build a scale model. The discovery in 1960 of some of the plans of this historic ship in the Danish Royal Archives at Copenhagen now make possible a reasonably accurate reconstruction of the vessel, and also clarifies some of the incomplete and often confusing descriptions by contemporary writers. Of the numerous published accounts of the ship that are available, the most complete is David B. Tyler's Fulton Steam Frigate. A contemporary description of the vessel by the British minister to Washington in 1820-23, Stratford Canning, was published by Arthur J. May. In Naval and Mail Steamers of the United States by Charles B. Stewart, and The Steam Navy of the United States by Frank M. Bennett, the history of the ship and some descriptive facts are given. Stewart, in an appendix, gives in full the report of the Supervisory Committee, set up to administer the building contract. Tyler and Stewart and the committee report are the principal sources from which the following summary of the ship's history is drawn. On December 24, 1813, Robert Fulton invited a group of friends, prominent merchants, professional men, and naval officers, to his home in New York City, and there presented a proposal for a project of great local interest. In that time, the War of 1812 was in its second year, and the economic effect of the British naval blockade was being felt severely. The blockade cut off seaborne trade and posed a constant threat of attack upon New York and other important ports, particularly Baltimore. To defend the ports, it has been proposed to build mobile floating batteries, or heavily built and armed hulks with small sailing rigs. But the high cost of these, and their doubtful value in helping to break the blockade, compared to the value and action of a very heavy large frigate or a 74-gun ship, caused authorities to hesitate to proceed with the construction of any block ships or floating batteries. Fulton's proposal concerned a floating battery, propelled by steam power. He believed that steam propulsion not only would give it effective maneuverability with no loss of gunpowder, but also would allow a successful attack upon the Royal Navy blockading ships during periods of protracted calm, when sailing men of war were nearly helpless. The blockaders then could be attacked and picked off one by the heavily armed steamboat. Among those present at the meeting was Major General Henry Dearborn, a leading citizen and soldier who was later to become noted in American political history. The first step taken during this meeting was the founding of the Coast and Harbor Defense Company, with Dearborn as president, Fulton as engineer, and Thomas Morris as secretary. Next, a committee was established to raise funds from federal, state, and New York City governments, as well as from individual contributors to build the battery. The members of this committee consisted of General Dearborn, Commodore Stephen Decatur, U.S. Navy, General Morgan Lewis, Commodore Jacob Jones, U.S. Navy, Noah Brown, shipbuilder, Samuel L. Mitchell, Henry Rutgers, and Thomas Morris. The committee proved cumbersome and was reduced to General Lewis, Isaac Bronson, Henry Rutgers, Nathan Sanford, Thomas Morris, Oliver Wolcott, and John Jacob Astor. Known as the Coast Defense Society, and with the name of Pyramon given the ship in prospectus, they attempted, unsuccessfully, to raise funds privately. The estimated sums to build a battery, 130 feet long, with a 50-foot beam, capable of a speed of 5 miles per hour and carrying 24 long guns, 18-pounders, was $110,000. Fulton, still the chief engineer, in an effort to interest the federal government, built a model of the proposed vessel and submitted it to some prominent naval officers, Commodore Stephen Decatur, Jacob Jones, James Biddle, Samuel Evans, Oliver Perry, Samuel Warrington, and Jacob Lewis. All gave their support to the society in a written statement, and this recommendation proved helpful to the project in Congress and in the Navy Department. In the process of passing a bill, which went to the Senate Naval Affairs Committee, calling for $250,000 for the construction of the floating battery, the sum was raised to $1,500,000 for the construction of one or more floating batteries, and passed on March 9, 1814. To supervise the start of construction, the Coast Defense Society appointed a committee consisting of Dearborn, Wolcott, Morris, Mitchell, and Rutgers, with Fulton as engineer, and a model and drawing of the proposed vessel was submitted to the Patent Office. The Secretary of the Navy, although supporting the project, delayed action until he had weighed the importance of the batteries in relation to other war needs, for at this time the naval shipbuilding program on the Great Lakes was considered of prime importance. He also raised some technical questions concerning the design of the batteries, which Fulton answered with a full description of the vessel as 138 feet on deck, 120 feet on the keel, 55 feet beam, each hull to have a 20-foot beam, and the race between to be 15 feet wide, draft 8 or 9 feet loaded, and the intended speed was to be 4.5 to 5 miles per hour. The ship was to carry 24 long guns, 32-pounders. The engine was to be 130 horsepower, and the total cost $200,000. In his letters to the Secretary of the Navy, Fulton stated that Adam and Noah Brown would build the hull for $69,800 and that he would build the engine, machinery, and boilers for $78,000, a total of $147,800. He intended to have the boilers, valves, fastenings, and air pumps of brass or copper, which would raise the machinery cost 59% above that of the stationary engines and boilers then in use. On May 23, 1814, the Secretary of the Navy authorized the Coast Defense Society and its committee to act as Navy agents and to enter into the contracts required to build a vessel, and to draw on the Navy storekeepers or Navy Yard commandants for such stores or articles on hand needed for construction. The contracts were prepared, and the committee now was officially empowered to act for the society, with Rutgers, Wolcott, Morris, Dearborn, Mitchell, and Fulton. On June 4th, Dearborn asked the Navy Department for $25,000 advance, for work had started. On the 6th, he informed the Secretary that he had been ordered to assume command of the defenses of Boston, and that Rutgers had been appointed chairman of the construction committee in his place. It is apparent that the Navy Department was pressed for funds, due to the very extensive shipbuilding programs on Lake Erie, Ontario, and Champlain, in addition to the seagoing vessels being built in some of the coastal ports. This was certainly one cause for the Secretary of the Navy's reluctance to carry out the requirements of the bill passed by Congress immediately after its signature, and also This reluctance caused the supervisory committee much embarrassment in its administration of the contract. Another factor which caused difficulty in the administration of the contract was the position of Adam and Noah Brown. The brothers were deeply involved in the shipbuilding program on the lakes, in which they were associated at times with Henry Eckford. The Browns constructed a blockhouse, shops, and quarters at Erie. In addition to Perry's 2 brigs and 5 of his schooners, they also built some of the Lake Ontario vessels, and later, the Saratoga on Lake Champlain. In their New York yard, whose operation continued throughout the war, they built some large letter of marques, the General Armstrong, Prince de Neufchâtel, Zebra, Paul Jones, and some smaller vessels. They also cut down the 2-decked merchant ship China into a single flush-deck letter of marque renamed Yorktown, and they had a contract to build the sloop of war Peacock. It is remarkable that the Browns could undertake and complete so much work between 1813 and 1815 and still be able to build the steam battery in a very short time. With the contracts in order, the Browns began building. The keels of the battery were laid June 20th, 1814. It is apparent that the Browns prepared the original hull plans, undoubtedly before the building authority was obtained. The vessel required only about 4 months to build. She was launched October 29, 1814, at 9 a.m. This was an excellent performance, considering the size of the vessel, the amount of timber required and handled in her massive construction, and the other work being done by the builders. During the ship's construction, sightseers were a nuisance, and finally guards had to be obtained. During the building of the steam battery, work had to be practically stopped on the sloop of war Peacock at one period, after she had been partially planked. There were difficulties in obtaining metalwork for the vessel during her construction, due to the blockade and the demand for such material for other shipbuilding at New York. On November 21, 1814, the ship was towed from the Browns' yard on the East River by Fulton's Car of Neptune and Fulton, each lashed to the sides of the battery and taken to Fulton's works on the North River. There, Fulton supervised in person the completion of the vessel and construction of her machinery. Undoubtedly, only a little of his time was required in inspection of the Browns' work on the battery, for the shipbuilders had been closely associated with Fulton throughout the life of the project and were fully capable as ship designers. The work on the machinery was another matter, however, for men capable of working metal were scarce, and few workmen could read plans. Fulton had some of the work done outside of his own plant, particularly the brass and copper work, mostly by John Yule's foundry. As a result, Fulton was required to move from plant to plant, keeping each job under almost constant observation and personally supervising the workmen. The equipment then available for building a large engine was inadequate in many ways. The large steam cylinder presented a problem. It had to be recast several times, and some of the other parts gave trouble, either in casting or in machining and fitting. Guns for the battery were another problem. Only 3 long guns, 32-pounder, were available at the Navy Yard. The Secretary of the Navy promised some captured guns then at Philadelphia. Because of the blockade, these had come overland to New York. The captured guns thus obtained were probably English, part of the cargo of the British ship John of Lancaster, captured by the frigate President early in the war. Apparently 24 guns were obtained this way. Only 2 were obtained from the Navy Yard. In July, the supervising committee carried out some experimental damage studies in which a 32-pounder was fired at a target, representing a section of the topsides of the battery. Drawings of the result were sent to the Secretary of the Navy. Further problems arose over the delays of the government in making payments. The banks discounted the Treasury notes, so the committee members had to advance $5,000 out of their own pockets. There was fear that British agents might damage the vessel, and although the project was undoubtedly known to the British, no evidence of any act of sabotage was ever found. Captain David Porter was assigned to the command of the battery in November, and it was upon his request that the vessel was later rigged with sails. With the steam battery approaching completion, the Secretary of the Navy became more enthusiastic, and the construction of other batteries of this type was again proposed. Captain Stiles, a Baltimore merchant, offered to build a steam battery, the hull to cost $50,000. The entire cost of the vessel, $150,000, was raised in Baltimore, and the frames of a battery erected. Another battery was projected at Philadelphia, and the Secretary of the Navy wanted one more built at Sackett's Harbor, but naval officers and Fulton objected. A bill put before Congress to authorize another $500,000 to build steam batteries passed the first reading January 9, 1815, went to the House February 22, 1815, but the end of the war prevented any further action on it. On February 24, 1815, Fulton died. He had been to Trenton, New Jersey, to attend a hearing on the steamboat monopoly, and on the way back the ferry on North River was caught in the ice. Fulton and his lawyer, Emmett, had to walk over the ice to get ashore. On the way, Emmett fell through, and Fulton got wet and chilled while helping him. After 2 or 3 days in bed, Fulton went to his foundry to inspect the battery's machinery, causing a relapse, from which he died. This resulted in some delay in completing the machinery, and stopped work on the Mute, an 80-foot, manually propelled torpedo boat that Fulton was having built in the Browns' yard. It was decided to suspend work on the Baltimore battery after an expenditure of $61,500, but the New York battery was to be completed to prove the project was practical. The final payment of $50,000 was made 4 months after it was requested. Charles Stoudinger, Fulton's foreman, or superintendent, was able to complete and install the ship's machinery. On June 10, 1815, the vessel was given a short trial run in the harbor with Stoudinger and the Navy inspector, Captain Smith, on board. This trial revealed the need of some mechanical alterations. Sails were not used, and it was found that she could stem the strong tide and a fresh headwind. The vessel also was visited by the officers of French men of war at anchor in the harbor. On July 4, 1815, she was given another trial. She left Fulton's works at Corlier's Hook at 9 a.m., ran out to Sandy Hook Lighthouse, bore west, and returned, a total of 53 miles under steam, reaching her slip at 5:20 p.m. She was found to steer like a pilot boat. This prolonged trial revealed that the stokehold was not sufficiently ventilated, and more deck openings were required. The windsails used in existing hatches were inadequate. The paddle wheel was too low and had to be raised 18 inches, and there were still some desirable modifications to be made in the machinery. On September 11, 1815, she was again given a trial run. All alterations had been made, including the addition of hatches and raising the paddle wheel, and her battery was on board with all stores, supplies, and equipment. She had 26 long guns, 32-pounders, mounted on pivoted carriages, and now drew 10 feet 4 inches. On this day she left her slip at 8:38 a.m. and went through the Narrows into the lower bay, where she maneuvered around the new frigate Java at anchor there. The battery was then given a thorough trial under steam and sail, and with the ship under way, her guns were fired to see if a concussion would damage the machinery. The vessel was found to be a practical one, capable of meeting the government's requirements in all respects. Her speed was 5.5 knots. However, the stokehold temperature had reached 116 degrees Fahrenheit. She returned to her slip at 7 p.m. On December 28, 1815, the committee, in a written report to the Secretary of the Navy, gave a description of the vessel and praised her performance. At this time, a set of plans was made by Mr. Morgan, of whom no other reference has appeared, and sent to the Navy Department. These cannot now be found. The committee recommended the battery be commissioned and used for training purposes. The suggestion was not followed. The ship remained in her slip during the winter, and in June 1816 she was turned over to the Navy and delivered to Captain Samuel Evans, commandant of the New York Navy Yard. Captain Joseph Bainbridge was assigned to her command. However, she was not commissioned, and soon after her delivery she was housed over and placed in ordinary, that is, laid up. The final settlement showed that the committee, as Navy agents, had paid out $286,162.12, with $872 unpaid, as well as a claim for $3,364 by Adam and Noah Brown, making a total of $290,398.12. The following year, on June 18, 1817, she was unroofed and put into service with a small crew. With President James Monroe on board, she left the Navy Yard about noon for a short trip to the Narrows and then to Staten Island, and returned in the evening. The next day she was again placed in ordinary. 4 years later, in 1821, when her guns and machinery were removed, it was found that she was rapidly becoming rotten. She was then utilized as a receiving ship. At 2:30 p.m. on June 4, 1829, she blew up, killing 24 men and 1 woman, with 19 persons listed as injured. Among those killed was 1 officer, Lieutenant S.M. Brackenridge. 2 lieutenants and a sailing master were hurt, 4 midshipmen were severely injured, and 5 persons were listed as missing. The explosion of 2.5 barrels of condemned gunpowder was sufficient, due to her rotten condition, to destroy the ship completely. A court of inquiry blamed a 60-year-old gunner, who supposedly entered a magazine with a candle to get powder for the evening gun. It was stated to the court that about 300 pounds of powder, in casks and in cartridges, was on board the ship at the time. She was not replaced until the coast defense steamer Fulton was built in 1837-38, though in 1822 the Navy purchased for $16,000 a steam galliot of 100 tons, the Sea Gull, to be used as the dispatch boat for the West Indian Squadron engaged in suppressing piracy during 1823. In 1825 she was laid up at Philadelphia, and in 1840 she was sold for $4,750. It is a curious fact that the battery did not receive an official name, as did the sailing Blockship on the ways at New Orleans, which at the end of the War of 1812 was officially listed as the Chifanta. Nor was the battery given a number, as were the gunboats. In official correspondence and lists, the steam battery is referred to as the Fulton Steam Frigate, or as the Steam Battery, but in later years she was referred to as the Fulton, or Fulton the First. Perhaps the explanation is that as she was the only one of her kind, she was not numbered, and as she was not considered fit for coastal or extended ocean voyages, she was not given a name. End of Part 1. End of Section 13. Section 14 of Smithsonian Institution, United States National Museum, Bulletin 240, Contributions from the Museum of History and Technology, Papers 34 through 44 on Science and Technology, by Museum of History and Technology. This LibriVox recording is in the public domain. Paper 39, Fulton's Steam Battery, Blockship and Catamaran, by Howard I. Chappell. Part 2. Surviving Designs for Floating Batteries. The designs of American blockships that have survived are those of the Chifanta, 145 feet long, 43-foot molded beam, 8-foot 6-inch depth in hold, and about 152 feet 9 inches on deck. She was to carry a battery of 22 long guns, 32-pounders on the main deck, 12 carronades, 42-pounders on forecastle and quarterdecks. She was to have been rigged to rather lofty and very square to'garnsels, and would have been capable of sailing fairly well, though of rather shoal draft, drawing only about 8 feet 6 inches when ready for service. She was sold on the stocks at the end of the war, and her later history is not known. Another and earlier design for a blockship, or floating battery, was prepared by Christian Berg for Captain Charles Stewart in 1806. This was a sailing vessel for the defense of the port of New York, planned to mount 40 guns, 32-pounders, on her 2 lower decks and 14 carronades, 42-pounders, on her spar deck. She was to be 103 feet 6 inches between perpendiculars, a 44-foot molded beam, 10-foot depth of hold, and drawing about 9 feet when ready for service. She was intended to be ship-rigged, but was never built. A few small sloop-rigged block vessels also were built during Jefferson's administration. The sloop of war Saratoga, built on Lake Champlain by the Browns in 1813, was practically a block ship. A plan for a proposed guard ship or a floating battery was made by James Marsh at Charlestown, South Carolina, in 1814. This was an unrigged battery, 200 feet extreme length, 50-foot molded beam, 9-foot depth of hold, to mount 32 guns, 42-pounders, on a flush deck with a covering deck above. Through the courtesy of the trustees of the National Maritime Museum, Greenwich, England, the Riksarkivet, Copenhagen, Denmark, and the Statens Sfihistoriska Museum, Stockholm, Sweden, the author has been able to illustrate in this article the designs of some of the early floating batteries. In the last quarter of the 18th century, the Danes had built sail-propelled floating batteries or blockships which were employed in the defense of Copenhagen. The British built at least one sail-propelled battery, the Spanker, in 1794. This was a scow of very angular form with overhanging gun deck, bomb catch-rigged, and about 120 feet overall, 42-foot 4 inches molded beam, and 8-foot depth of hold. She is said to have been a failure, due to her unseaworthy proportions and form. The overhanging gun deck and sides were objected to in particular. She is called a stationary battery in her plans, which are in the Admiralty collection of drafts, National Maritime Museum, Greenwich. Controversial descriptions. The contemporary descriptions of the Fulton steam battery do not agree. This was in part due to differences between the dimensions given out by Fulton during the negotiations with the federal government and after the ship's construction was authorized. From the context of various statements concerning the projected vessel, such as that of the naval officers, the changes in the intended dimensions of the ship can be seen. For example, the officers state the model and plan shown them would produce a battery carrying 24 guns, 24 and 32-pounders, and a letter from Fulton to Jones shows she was to be 138 feet on deck and 55-foot beam. The final reported dimensions given by the Supervisory Committee are 156 feet length, 56 feet beam, and 20 feet depth. In addition, there are a few foreign accounts which give dimensions and descriptions. The most complete was probably that of Jean-Baptiste Marestier, a French naval constructor who visited the United States soon after the end of the War of 1812, and published a report on American steamboats in 1824. The steam battery is barely mentioned, though a drawing of one of her boilers is given. Marestier made another report on the American Navy, however. Extensive searches have been made for this in Paris over the last 14 years, but this paper has not been found in any of the French archives. References to the original text indicate that the naval report dealt very extensively with the steam battery. Some of his comments on the battery appeared in Procès-verbaux des Sciences de l'Académie des Sciences. Marestier considered the powers of the battery to have been overrated due to fanciful accounts of some layman writers. He was aware of the shortcomings of the double hull in a steam vessel at the then possible speeds, but he apparently thought 2 engines, one in each hull, and each with its boilers, would be better than Fulton's arrangement of boilers in one hull and engine in the other. He noted that the paddle wheel turned 16 to 18 RPM, and that steam pressure sustained a column of mercury 25 to 35 centimeters. The safety valve was set at 50 centimeters. Full consumption was 3 5/8 cords of pine wood per hour. In view of the access Marestier is known to have had to American naval constructors, shipbuilders, and engineers, it is highly probable that he not only obtained the building plan of the ship, but also some of the earlier project plans from the builders and from Fulton's superintendent, Stoutinger. It is therefore a great misfortune that his lengthy report on the battery cannot be produced. A French naval officer who investigated the ship, M. Montgeray, also wrote a description published in Notice sur la vie et les travaux de Robert Fulton. It should be noted in regard to what Montgeray wrote about the battery that in 1821 it had been considered desirable to disarm the ship. The engineer in charge, William Purcell, had reported that as there were not proper scuppers, dirt and water had entered the hull and had collected under the engine and boilers, causing damage to the hull, and also that, with guns removed, the battery would float too high for the paddle wheel to propel the vessel. So it had been decided to remove all machinery, as well as the armament. Montgeray's description, published in 1822, was taken from his report to the Minister of Marine and Colonies. It noted the battery was made of 2 hulls, separated by a channel, or race, 15.5 feet wide, running the full length of the vessel. The 2 hulls were joined by a deck, just above the waterline, as well as by an upper deck, and also connected at their keels by means of 12 oak beams, each 1 foot square. The vessel was 152 feet long, 57 feet beam, and 20 feet deep. Sides were 4 feet 10 inches thick, and the ends of the hull were rounded and alike. There were 2 rudders at each end, one on each hull, alongside the race. The 8 paddle blades, each 14.5 feet by 3 feet, turned in either direction by stopping the engine piston at half-stroke and reversing the flow of steam. Rigged with 2 lateen sails and 2 jibs, the ship sailed either end first. The engine of 120 horsepower was in one hull, and 2 boilers were in the other. Other sources, Forestier and Colden, in Procès Verbaux des Sciences de l'Académie des Sciences, direct connected to the paddle wheel, which was turned at 18 rpm. The boilers were 8 by 22 feet with the fireboxes in inside cylinders, each about 5 feet in diameter and extending about half the length of the boiler from the fire doors. 2 fire tubes, each about 3 feet in diameter, returned the gases from the inside end of the fireboxes to the stacks at the firing end. Except at the fire door end, the firebox was completely surrounded by water. The boiler pressure of about 6 psi was not maintained, varying somewhat with each stroke of the engine. Water level in the boilers was indicated by tricocks. The safety valve was controlled by a counterbalanced lever. A jet of salt water was injected into the exhaust trunk to form a vacuum by condensation. An air pump transferred condensate and seawater into a tank from which it passed overboard. Only about 1/10 of this water was returned to the boilers. Montgeray stated also that only the lower or gun deck was to be armed. No bulwarks were on the spar deck, only iron stanchions to which were fastened a breastwork of wet cotton bales when the steam battery was in action. The battery was designed to carry 30 guns, 32-pounders, with 3 guns in each end and 12 on each side, but no guns in the wake of paddle wheel and machinery. Hatches to give air to the stokehold were located amidships. The battery was to have been supplemented at the ends of each hull by a Columbiad submarine gun, a 100-pounder, Fulton's invention, but these were not fitted. Provision was to be made in the fireboxes for heating shot, and a force pump with a cylinder 33 inches in diameter was employed to throw a stream of cold water, about 60 to 80 gallons per minute, for a distance of about 200 feet. This could be done only when the paddle wheel was not in operation. The paddle wheel was housed, the top fitted with stairs to the spar deck. The gun deck, over the race, was used in part for staterooms, of which the bulkheads were permanent. Hammocks for the complement of 500 men were to be slung on the rest of the gun deck. The ship drew 10 feet 4 inches, with the port sills about 5.5 feet above the load line. Burning wood, the vessel would carry about 4 days' supply of fuel. Burning coal, she carried 12 days' supply. Montgeray said that the vessel would be vulnerable to bomb shells and hot shot, and that, furthermore, she could be boarded. The displacement of the ship at service draft was 1,450 tons, a figure Montgeray obtained from a copy of the original plan given him by Noah Brown. In 1935, Lieutenant Ralph R. Gurley, U.S. Navy, attempted a reconstruction in sketches of the vessel published in his article, The USS Fulton, the First. in the U.S. Naval Institute proceedings. The reconstruction was based on the Patent Office drawing prepared for Fulton and published by Stewart and Bennett and the foregoing French sources. The Patent Office drawing showed the engine was an inclined cylinder, and Lieutenant Gurley shows this in his sketch. In his text on page 323, he says, "The engine was an inclined, single-cylinder affair with a 4-foot base and a 5-foot stroke." Gurley's attempt to reconstruct the steam battery is the only one known to the author. Copenhagen plans. In 1960, Kjeld Rasmussen, naval architect of the Danish Greenland Company, was requested by the author to inspect, in the Danish Royal Archives at Copenhagen, a folio of American ship plans, the index of which had listed some Civil War river monitors. Mr. Rasmussen found the monitor plans had been withdrawn, but discovered that 3 plans of Fulton's steam battery existed, as well as plans of the first Princeton, a screw sloop of war. Copies of the steam battery's plans were obtained at Copenhagen in September of 1960 through the courtesy of the archivist, and were found to consist of the lines copied in 1817, an inboard profile and arrangement, and a sail and rigging plan. From these, the reconstruction for a scale model was drawn and is presented here with reproductions of the original drawings upon which the reconstruction is based. It is apparent that Montgomery's description is generally accurate. The vessel is a catamaran, made of 2 hulls, double-ended and exactly alike. The outboard sides are molded, with round bilges. The inboard sides are straight and flat, as though a hull had been split along the middle line and then planked up flat where split. The hulls are separated by the race, in which the paddle wheel is placed at mid-length. The top sides are made elliptical at the ends, and the midsection shows a marked tumble home over the thick topside planking, but less on the molded lines. The lines plan agreed rather closely to Montgomery's description of the hull. After careful fairing, it was found the lines drawing would produce a vessel 153 feet, 2 inches, overall outside the stems, or about 150 feet over the planked rabbets, with a molded beam of 56 feet and extreme beam of 58 feet. The molded depth was 22 feet 9 inches, and the width of the race was 14 feet 10 inches plank to plank. The room and space of framing shown was 2 feet. The designed draft appears to be 13 feet, and this would bring the port sills 5 feet 6 inches above the load line, and the underside of the gun deck beams about 2 feet 9 inches above the load line. The lines plan is a Danish copy, probably of the building plan by Noah Brown, and may be based on the plan Montgomery obtained from Brown. The spar deck has the iron stanchions. Gurley translated these as chandeliers, which are set inboard 4 feet from the plank shear. This gives room for cotton bales outboard the stanchions to form a barricade. As will be seen by comparing the original Danish drawing with the model drawing, the construction indicates that the iron stanchions should be carried around the ends of the hull in the same manner as along the sides, since the lower ends of the iron stanchions pass through the spar deck and are secured to the inside of the inner ceiling of the gun deck. The rudders are as shown in the Danish drawing, and it is supposed that they were operated ferryboat fashion, one at each end of the vessel. Hence each pair of rudders was toggled together by a cross yoke. This was probably operated by a tiller. Possibly the cross yokes and tillers were of iron, pivoted under the beams of the gun deck close to the ends of the ship. Tiller ropes led from a tackle under the gun deck through trunks to the spar deck, where the wheels were placed. This allowed proper sweep to the tillers and operation of each pair of rudders. The paddle wheel was apparently of iron, with wooden blades, and agrees with Montgomery's description. In the plan for the model, it is shown raised 18 inches above the original design position to agree with trial requirements. It should be observed that the close CL to CL frame spacing created a hull having frames touching one another, at least above the turn of the bilge, so the vessel was almost solid timber, before being planked and sealed from keel to about the load line. The sides are not only heavily planked, but after the frames were sealed with extraordinarily heavy square timbering, a supplementary solid vertical framing was introduced inboard and another ceiling added. The sides scale about 5 feet from outside the plank to the inboard face of the inner ceiling at the level of the gun ports. The holes were tied together athwartship by the deck beams of the gun deck and spar deck, except in the wake of the paddle wheel. Knees were placed along the sides of the race at alternate gun deck beams. In addition, the 12 one-foot square timbers crossing the race at the rabbets of the holes, mentioned by Montgomery, are shown. These must have created extraordinary resistance, even at the low speed of the steamer. The deck details shown are the results of reconstruction of the inboard works. History of the double-hull craft. The use of catamaran hulls, or double hulls, has been periodically popular with ship designers since the time of Charles II of England. The earliest of such vessels known, in the present day, were 4 sloops, or shallops, designed 1673 to 1687 by Sir William Petty, who was an inventor in the field of naval architecture and received some attention from Charles II and from the Royal Society. The first Petty experiment, the Simon and Jude, later called Invention 1, was launched October 28, 1662. She was designed with 2 hulls, cylindrical in cross-section, each 2 feet in diameter and 20 feet long. A platform connected the hulls, giving the boat a beam of a little over 9 feet. She had a 20-foot mast, stepped on one of the crossbeams connecting the hulls with a single gaff sail. In sailing trials, she beat 3 fast boats, the King's Barge, a large pleasure boat, and a man-of-war's boat. This double bottom, also called a sluice boat or cylinder, was later lengthened at the stern to make her 30 feet overall. The King did not support Petty, to the latter's great disappointment, and Petty next built a larger double bottom, Invention 2. This catamaran was lapstrake construction. Not much is known of this boat except that she beat the regular Irish packet boat running between Holyhead and Dublin in a race each way, winning a $20 wager. She was launched in July 1663. What became of her is not recorded. A third and still larger boat, the Experiment, launched December 22, 1664, appears to have been a large sloop. This vessel sailed by way of the Thames in April 1665 and went to Oporto, Portugal. She left Portugal October 20th, 1665, for home, but apparently went down with all hands in a severe storm. For 18 years, Petty did no more with this type. But finally, in July 1684, he laid down a still larger sloop with 2 decks and a mast standing 55 feet above her upper deck. She was named St. Michael the Archangel, and is probably the design of Pepet's Book of Miscellaneous Illustrations in Magdalene College, Cambridge, England. This vessel proved unmanageable and was a complete failure. Though the double canoes of the Pacific Islands were probably known to some in Europe in 1662, there is no evidence that Petty based his designs on such craft. He appears to have produced his designs spontaneously from independent observations and resulting theories. Before Petty concluded his experiments, a number of double-hull craft had been produced by others. However, some double craft, such as double shallops, may have been double-enders, as shown by a double Moss's boat of the 18th century and later. The use of 2 canoes, joined by a platform or by poles, was common in colonial times. In Maryland and Virginia, dugouts so joined were used to transport tobacco down the tidal creeks to vessels loading. Such craft were also used as ferries. M.V. Burrington's Chesapeake Bay log canoes and Paul Wilstack's Potomac landings illustrate canoes used in this manner. A catamaran galley, 2 round bottom hulls, flat on the inboard side, a hole split along the center line and the inboard faces planked up, 113 feet long, and each hull a 7-foot molded beam, 6 foot 6 inches molded depth, and placed 13 feet apart, was proposed by Sir Sidney Smith, Royal Navy, in the 1790s, and built by the British Admiralty. Named Taurus, she is shown by the Admiralty draft to have been a double-ender, with cabins amidships on the platform, an iron rudder at each end, between the hulls, steered with tillers to unship, and with a ramp at one end. The plans are undated, signed by Captain Sir Sidney Smith, and a field carriage gun is shown at the ramp end of the boat. This and the heavy rocker in the keels suggests the Taurus was intended for a landing boat. No sailing rig is indicated, but holes for 12 oars or sweeps on each side are shown. The oarsmen apparently sat on deck, or on low seats, with stretchers and hatches between each pair of tholes. Admiralty Collection of Drafts, the National Maritime Museum, Greenwich, England. Another experimenter with a double-hull type of vessel was a wealthy Scot named Patrick Miller, who was particularly interested in manual propulsion of vessels, employing geared capstans to operate paddle wheels. In a letter dated June 9, 1790, Miller offered Gustav III of Sweden a design for a double-hulled 144 gunship of the line, rating as a 130 gunship, propelled by manually operated capstans connected to a paddle wheel between the hulls. She was rigged to sail with 5 masts and was to be 246 feet long, 63 feet beam, and 17 feet draft. The hulls were 16 feet apart. This project was submitted by the king to Frederick Henrik of Chapman, the great Swedish naval architect, who made an adverse report. Chapman pointed out in great detail that the weight of the armament, the necessary hull structure, the stores, crew, ammunition, spars, sails, rigging, and gear would greatly exceed Miller's design displacement. He also pointed out the prime fault of catamarans under sail: slow turning in stays. He suggested that the speed under sail would be disappointing. He doubted that a double-hull ship of such size could be built strong enough to stand a heavy sea. He remarked that English records showed that a small vessel of the catamaran type had been built between 1680 and 1700, which had sailed well. This may have been one of Petty's boats, and that 36 years ago he had seen 8 miles from London a similar boat that had been newly built by Lord Baltimore and was about 50 feet long. This was a failure, and was discarded after one trial. Therefore, said Chapman, the Miller project was not new, but rather an old idea. Chapman's final remark is perhaps the best illustration of his opinion of the catamaran. Despite all this, two-hull vessels are completely sound when the theory can be properly applied, that is, in vessels of very light weight and of small size, with crews of 1 or 2 men. A model of such a double-hull ship, the Experiment, built at Leith, Scotland in 1786 by J. Laurie, was sent to Sweden by Miller. She was 105 feet long, 31 feet beam, and cost £3,000. This vessel arrived in the summer of 1790, and King Gustav, in a letter dated July 26, ordered Colonel Michael Ankersvard to welcome the vessel at Stockholm. The king presented Miller with a gold snuff-box, and a painting was made of the vessel. The Experiment had 5 paddle wheels in tandem between her hulls, operated by geared capstans on deck. These gave her a speed of 5 knots, but caused the crew to suffer from exhaustion in a short time. The vessel was badly strained in a storm, and was finally abandoned at St. Petersburg, Russia. Miller later turned to the idea of employing steam instead of manual power, and built a 25-foot double-hulled pleasure boat of iron, fitted with a steam engine built by William Symington. Also named Experiment, she was an apparent success, so Miller had a 60-foot boat built of the double-hull design and fitted with an engine built by Symington. She reached a speed of 7 miles per hour on the Forth and Clyde Canal. However, Miller lost interest when he found that the Symington engine was unreliable and that Great Britain showed very little public support for such projects. Fulton was acquainted with Symington's work and probably had heard of Miller's vessels. At any rate, he employed the double-hull principle in his steam ferryboats, the first of which was the Jersey, a 188-ton vessel built by Charles Brown, which began service July 2, 1812. The next year he had a sister ship built, the York. These vessels were based on his patent drawing of 1809. In 1814 he had another vessel of this type built, the Nassau. It was therefore logical that he should apply this design to the steam battery. The double-hull design had worked well in these ferries, and the design would give protection from shot to the paddle wheel. The battery would have the ability to run forward or astern, so as not to be exposed to a raking fire from the enemy while maneuvering in action. The application of this ferryboat principle to the battery reduced the need for extreme maneuverability, the Catamaran's weakest point, even at low speed. The resistance factors in the design are of relatively small importance, for the speed possible under steam in this period was very low. However, the plans show an apparently efficient whole form for the power available, aside from the drag of the beams across the race in the vicinity of the keel. The displacement was adequate. The height of the gun deck above the water at the race made the battery unsuitable for rough water operation. But there is no evidence that Fulton or the sponsors of the vessel considered the battery as a coastwise or seagoing steamer. However, the clearance of the gun deck above the water and the dip of the paddle wheel would have made the additional weight of an upper or spar deck battery prohibitive, even had experience in action prove it desirable. Sail and inboard plans. The sail and rigging plan is likewise a Danish copy, and shows the two mastered lateen rig employed. The hull is shown with bulwarks and gun ports on the spar deck, but no other evidence that the battery was finished in this manner has been found. The rig resembles that of some Hosea Fox's designs. For Jeffersonian gunboats, double enders, designed to sail in either direction but without the jibs. The topmasts do not appear to be more than signal poles, and apparently were not fitted with sails. However, some European lateens did have triangular topsails over a lateen, and it is possible the battery may have carried such sails. Considering the stability and displacement of the battery, the rig is very small and not sufficiently effective. Shrouds were not required. The masts were supported by runners that were shifted when the yards were reversed, and in tacking. Apparently, the jibstays also could be slackened off so that the lateen yards would not have to be dipped under them. The inboard profile is on tracing paper, and the notes are in French. This drawing is of a simplified hull form having flat-bottom hulls with chines. It is possible that this is a tracing of a preliminary drawing obtained by Marstier or Montgarret, but no documentation can be found. Its importance is that it shows in some detail the engine and boilers, as well as the wheel box and another drawing of the paddle wheel, more or less duplicating the wheels shown in the Danish plan. No details of the deck arrangements are shown in any of the plans, except for the domed skylight over the fire room in the boiler hull. Both the lines plan and the inboard drawing show construction midsections and hull connections. These plans show that the engine was not inclined, but rather was vertical, contrary to Fulton's patent drawing. The piston rod and the crosshead obviously passed through its gun deck in a large hatch. Also, it is plain that there must have been large hatches afore and abaft the wheel box to make the stepped wheel box construction desirable. There also must have been a hatch in the gun deck under the domed skylight. It is improbable that the engine and skylight hatches were used for ladderways, passing scuttles, or companionways. The boilers are shown in the inboard profile, about as described and drawn by Marstier, but with 2 stacks on each boiler, 1 to each flue. Marstier's sketch in his report on American steamship shows the flues of each boiler trunked into a single stack. The battery had 2 boilers, and the stacks are at the boiler's fire door end. The steam lines came off the crown of the boilers and probably passed through the ends of the wheel box to the engine. A trunk for the steam lines would undoubtedly have been necessary. The engine is shown to have had counterbalanced side levers, 1 on each side, and a single flywheel on the outboard side. The cylinder is over the condenser, or cistern, connected by the steam line and valve box on the side. The cylinder crosshead is shown in the inboard profile to have reached the underside of the beams of the upper deck. The crosshead was connected by 2 connecting rods to side levers. These levers operated the paddle wheel by connecting rods to cranks on the paddle wheel shaft. There is another pair of connecting rods from the side levers to the crosshead of the air pump. All connecting rods are on one arm of the side levers, the other end having only a counterbalance weight beyond the fulcrum bearing. The flywheel has a shaft fitted with 2 gears, and is driven through idler gears from gears on the paddle wheel shaft. it turns at about twice the speed of the paddle wheel. No other pumps or fittings are shown in the engine hull, although manual pumps were probably fitted to fill and empty the boilers. Piping is not shown. The 4 rudders, toggled in pairs, are shown in both the lines and inboard drawings, but the shape is different in the 2 plans. Operation must have been by a tiller under the gun deck beams. The outer end of the tiller may have been pivoted on the toggle bar and the inboard end fitted, as previously described, with steering cable or chain tackles. This seems to be the only practical interpretation of the evidence. Reconstructing the plans. In the model, it was necessary to reconstruct the deck arrangements without enough contemporary description. The outboard appearance and hull form, rig, and arrangement of armament require no reconstruction, for all that is of importance is shown in the lines and rig drawings, or in the inboard profile. The masts are shown to have been stepped over the race on the gun deck. The iron stanchions are shown in the lines drawing and in the construction section. However, their position at the ends of the battery are apparently incorrectly shown in the original lines plan. The construction section shows these stanchions to have been stepped on the inside face of the inner ceiling, and as the ceiling structure was carried completely around the ship, the stanchions in the ends must have been placed inboard, as along the sides. The bowsprit was above deck, and would probably be secured in the knighthead timbers at the ends of the hull, as well as by the heel bits shown in the Danish lines drawing. With the riding bits shown inboard of the heel bits at each end of the vessel, it is obvious that she would work her ground tackle at both ends, and would therefore require 2 capstans. The wheelbox would prevent effective use of a single one. The capstans might be double-headed, as in some large frigates and ships of the line. As to the remaining deck fixtures, hatches, and fittings, these must be entirely a matter of speculation. Ladderways, passing scuttles, hatches, trunks, galley, heads, and cabins were obviously required in a fighting ship and can only be located on the theory that when completed, the battery was a practical vessel. It had been stated that the officers' cabins were on the race. The logical place for the heads, galley, wardroom, and mess also would be over the race, giving the remaining part of the gun deck for the necessary hatches, ladderways, trunks, etc. in the 2 holes, space required for armament, and to sling the hammocks of a watch below. As the vessel was never fully manned, apparently the space for hammocks is not a serious problem in a reconstruction. If the vessel had been manned as proposed by 500 men, hammocks for over 200 would have been required, which would give very crowded quarters in view of the limited space available. Though no specific requirements were stated in the reports of the trials, it seems reasonable to suppose that additional hatches were cut in the decks to improve the fire room ventilation. In the reconstruction drawings, these hatchways, as well as the other deck openings and deck fittings, such as bilge pumps, companionways, skylights, binnacles, wheels and wheel rope trunks, cable trunks, steam pipe casings, and stack fiddlies, have been located in an effort to meet the imagined requirements of the working of a ship of this unusual form. There are some unanswered questions that arose in the preparation of the reconstruction drawings. As has been shown, the original inboard arrangement plan found in Copenhagen shows 4 smokestacks, while Maristier's sketch of the vessel's boilers shows trunked flues, indicating that 2 stacks were used. It is possible that the boilers were first fitted so that 4 stacks were required. Alterations made as a result of steaming trials may well have included the introduction of trunked flues and the final use of 2 stacks in line fore and aft. This would have required a rearrangement of the fiddly hatches amidships. Another troublesome question was the doubtful arrangement of the 4 companionways on the spar deck. Perhaps only 2 were fitted, 1 on each side of the officers' staterooms, while the ladderways at the crew's end of the ship were simple ladder hatches. The decision to use 4 bilge pumps is based upon the lack of drag in the keel of the hulls, which would prevent accumulation of bilge water at one end of the hull. The use of 4 single-barrel pumps instead of 4 double-barrel pumps may be questioned, for chain pumps requiring 2 barrels would have been practical. Allowance for stores was made by use of platforms in the hold. It is known from statements made to the Court of Inquiry that the magazines were amidships and that a part of these was close to the boilers. Fuel and water would be in the lower hold under the platforms. Hatches and ladderways are arranged to permit fueling the ship. A few prints or drawings of the ship, aside from the patent drawing, had been found. There are 2 prints that show the launch of the vessel. One, a print of 1815, is in possession of the Mariners Museum, Newport News, Virginia, and is reproduced in Alexander Crosby Brown's Twin Ships, Notes on the Chronological History of the Use of Multiple Hold Vessels. A poor copy of this print appears on page 13 of Bennett's Steam Navy of the United States, and another and inaccurate sketch is shown on page 8. These pictures were of no use in the reconstruction as they show no details that are not in the Copenhagen plans. The patent drawing does not show deck details, and in fact does not represent the vessel as built in any respect other than in being a catamaran with paddle wheel amidships between the hulls. The steam battery did not have any particular influence on the design of men of war that followed her. In the first place, steam power was not viewed with favor by naval officers generally. This was without doubt due to prejudice, but engines in 1820 to 1830 were still unreliable when required to run for long periods, as experienced by the early ocean-going steamers. The great weight of the early steam engines and their size in relation to power were important, and also important were practical objections that prevented the design of efficient naval ocean steamers until about 1840. Even then, the paddle wheels made them very vulnerable in action. Until the introduction of the screw propeller, it was not possible to design a really effective ocean-going naval steamer. Hence, until about 1840 to 45, sail remained predominant in naval vessels for ocean service, and steamers were accepted only in coast defense and towing services, or as dispatch vessels. No immediate use of the double hull in naval vessels of the maritime powers resulted from the construction of the steam battery. The flat-bottomed chine belt design employed by Fulton in North River, Raritan, and other early steamboats was utilized in the design for a projected steamer by the British Admiralty in 1815-16. This vessel was about 76 feet overall, 16-foot beam, and 8 foot 10 inches deep in hold. Her design was for a flat bottom, chine-built hull with no fore and aft camber in the bottom, a sharp entrance, and a square tuck stern with slight overhang above the cross seam. Her side frames were straight and vertical amidships, but curved as the bow and stern were approached. She was to be a size paddle wheel steamer, and her hull was diagonally braced. The wheel and engine were to be about amidships, but she was dead flat for about 14 feet. However, the engine and boilers were not installed. The engine was utilized ashore for pumping, and the vessel was completed in the Deptford yard as a sailing ship. Under the name Congo, she was employed in the African Coast Survey. Her plan is in the Admiralty collection of drafts at the National Maritime Museum, Greenwich, England. The double hull continued to be employed in both steam and team ferryboats in the United States and in England and France. A few river and lake steamers were also built with this design of hull. Continued efforts to obtain fast sailing by use of the double hull produced a number of sailing catamarans. Of these, the Herreshoff catamarans of the 1870s showed high speed when reaching in a fresh breeze. Designs for double-hulled steamers appeared during the last half of the 19th century. In 1874, the Castalia, a large double-hull iron cross-channel steamer, was built by the Thames Iron Works Company at Blackwall, England. She was 290 feet long, and each hull had a beam of 17 feet. The paddle wheel was placed between the hulls, and ready for sea she drew 6.5 feet. She ran the 22 miles between Dover and Calais in 1 hour and 50 minutes, a speed much slower than that of the paddle wheel cross-channel steamers having one hull. Another double-hull steamer was built for the service by Hawthorne, Leslie and Company. Newcastle-on-Tyne, Scotland, in 1877. First named Express, she was renamed Calais Douvre when she went into service in May 1878. Her length was 302 feet, her extreme beam 62 feet, and each hull had a beam of 18 feet 3 inches. She drew 6 foot 7.5 inches, ready for sea, and the paddle wheel was between the hulls. On her trials, she made 14 knots and burned coal excessively. Sold to France in 1880, she was taken out of service in 1889. Though popular, she was not faster than the single-hull steamers in this service, and had been a comparatively expensive vessel to build and operate. The many attempts to produce a very fast double-hull steamer and large sailing vessels have led to disappointment for their designers and sponsors. In the history of naval architecture, since Petty's time, there have been a number of periods when the new-old idea of the double hull has become popular. Craft of this type have been commonly well publicized, but on the whole, their basic designs have followed the same principles over and over again and have not produced the sought-for increase in speed and handiness. In very recent years, there has been a revival in interest in sailing double-hull boats that is enthusiastic as to very small craft and somewhat restrained as to large boats. A few projects are under development for double-hull craft, power, and sail, of over 90-foot length, including an oceanographic research vessel. In general, however, the performance of double-hull boats has shown that Chapman's estimate of the type was reasonably correct, and that there are limitations, particularly in maneuverability in the double-hull craft that could have been found by reference to the history of past experiments with the type. End of section 14. Section 15 of Smithsonian Institution, United States National Museum. Bulletin 240, Contributions from the Museum of History and Technology. Papers 34 through 44 on Science and Technology, by the Museum of History and Technology. This LibriVox recording is in the public domain. Paper 39, Fulton's Steam Battery, Blockship and Catamaran, by Howard I. Chappell, Part 3. Naval Steamers, the Demologos, or Fulton the First. At the close of the year 1813, Robert Fulton exhibited to the President of the United States the original drawing from which the engraving on Plate 1 is sketched, being a representation of the proposed war steamer, or floating battery, named by him, the Demologos. This sketch possesses more than ordinary interest, from the circumstance that is, doubtless, the only record of the first war steamer in the world designed and drawn by the immortal Fulton, and represented by him to the executive as capable of carrying a strong battery, with furnaces for red-hot shot, and being propelled by the power of steam at the rate of 4 miles an hour. It was contemplated that this vessel, besides carrying her proposed armament on deck, should also be furnished with submarine guns, 2 suspended from each bow, so as to discharge a 100-pound ball into an enemy's ship at 10 or 12 feet below her waterline. In addition to this, her machinery was calculated for the addition of an engine which would discharge an immense column of water upon the decks, and through the portholes of an enemy, making her the most formidable engine for warfare that human ingenuity has contrived. The estimated cost of the vessel was $320,000, nearly the sum requisite for a frigate of the first class. The project was zealously embraced by the executive, and the national legislature in March 1814 passed a law authorizing the President of the United States to cause to be built, equipped, and employed 1 or more floating batteries for the defense of the waters of the United States. The building of the vessel was committed by the Coast and Harbor Defense Association to a subcommittee of 5 gentlemen who were recognized by the government as their agents for that purpose, and whose interesting history of the steam frigate is copied in Note A of the appendix to this volume. Robert Fulton, whose soul animated the enterprise, was appointed the engineer, And on the 20th day of June, 1814, the keel of this novel steamer was laid at the shipyard of Adam and Noah Brown, her able and active constructors, in the city of New York. And on the 29th of the following October, or in little more than 4 months, she was safely launched in the presence of multitudes of spectators who thronged the surrounding shores and were seen upon the hills which limited the beautiful prospect around the Bay of New York. The river and the bay were filled with steamers and vessels of war, in complement to the occasion. In the midst of these, the enormous floating mass, whose bulk and unwieldy form seemed to render her as unfit for motion as the land batteries which were saluting her. In a communication from Captain David Porter, U.S. Navy, to the Honorable Secretary of the Navy, dated New York, October 29, 1814, he states, "I have the pleasure to inform you that the Fulton I was this morning safely launched. No one has yet ventured to suggest any improvements that could be made in this vessel, and, to use the words of the projector, I would not alter her if it were in my power to do so. She promises fair to meet our most sanguine expectations, and I do not despair in being able to navigate in her from one extreme of our coast to the other. Her buoyancy astonishes everyone. She now draws only 8 feet 3 inches water, and her draft will only be 10 feet with all her guns, machinery, stores, and crew on board. The ease with which she can now be towed with a single steamboat renders it certain that her velocity will be sufficiently great to answer every purpose, and the manner it is intended to secure her machinery from the gunner's shot leaves no apprehension for its safety. I shall use every exertion to prepare her for immediate service. Her guns will soon be mounted, and I am assured by Mr. Fulton that her machinery will be in operation in about 6 weeks." On the 21st of November, the steam frigate was moved from the wharf of Messrs. Brown's in the East River to the works of Robert Fulton on the North River to receive her machinery, which operation was performed by fastening the steamboat Car of Neptune to her larboard and the steamboat Fulton to her starboard side. They towed her through the water from 3½ to 4 miles per hour. The dimensions of the Fulton I were length 160 feet, breadth 56 feet, depth 20 feet, water wheel 16 feet diameter, length of bucket 14 feet, dip 4 feet, engine 48-inch cylinder, and 5 feet stroke, boiler length 22 feet, breadth 12 feet, and depth 8 feet, tonnage 2,475. By June 1815, her engine was put on board, and she was so far completed as to afford an opportunity of trying her machinery. On the 1st of June, at 10 o'clock in the morning, the Fulton I, propelled by her own steam and machinery, left the wharf near the Brooklyn Ferry and proceeded majestically into the river. Though a stiff breeze from the south blew directly ahead, she stemmed the current with perfect ease, as the tide was a strong ebb. She sailed by the forts and saluted them with her 32-pound guns. Her speed was equal to the most sanguine expectations. She exhibited a novel and sublime spectacle to an admiring people. The intention of the commissioners being solely to try her enginery, no use was made of her sails. After navigating the bay, and receiving a visit from the officers of the French ship of war lying at her anchors, the steam frigate came to at Powell's Hook Ferry, about 2 o'clock in the afternoon, without having experienced a single unpleasant occurrence. On the 4th of July of the same year, she made a passage to the ocean and back, and went the distance, which, in going and returning, is 53 miles, in 8 hours and 20 minutes, without the aid of sails. The wind and tide were partly in her favor and partly against her, the balance rather in her favor. In September she made another trial trip to the ocean, and having at this time the weight of her whole armament on board, she went at an average of 5½ miles an hour, with and against the tide. When stemming the tide, which ran at the rate of 3 miles an hour, she advanced at the rate of 2½ miles an hour. This performance was not more than equal to Robert Fulton's expectations, but it exceeded what he had premised to the government, which was that she should be propelled by steam at the rate of from 3 to 4 miles an hour. The English were not uninformed as to the preparations which were making for them, nor inattentive to their progress. It is certain that the steam frigate lost none of her terrors in the reports or imaginations of the enemy. In a treatise on steam vessels, published in Scotland at that time, the author states that she has taken great care to procure full and accurate information of the steam frigate launched in New York, and which he describes in the following words. Length on deck, 300 feet. Breadth, 200 feet. Thickness of her sides, 13 feet of alternate oak plank and corkwood. Carries 44 guns, 4 of which are 100-pounders. Quarter-deck and forecastle guns, 44-pounders. And further to annoy an enemy attempting to board, can discharge 100 gallons of boiling water in a minute. And by mechanism, brandishes 300 cutlasses with the utmost regularity over her gunwales. Works also an equal number of heavy iron pikes of great length, darting them from her sides with prodigious force, and withdrawing them every quarter of a minute. The war having terminated before the Fulton the First was entirely completed, she was taken to the Navy Yard, Brooklyn, and moored on the flats abreast of that station, where she remained, and was used as a receiving ship until the 4th of June, 1829, when she was blown up. The following letters from Commodore Isaac Chauncey, then Commandant of the New York Navy Yard, to the Honorable Secretary of the Navy, informing him of the distressing event, concludes this brief history of the first steam vessel of war ever built. U.S. Navy Yard, New York, June 5, 1829. Sir, it becomes my painful duty to report to you a most unfortunate occurrence which took place yesterday at about 2:30 p.m., and the accidental blowing up of the receiving ship Fulton, which killed 24 men and a woman and wounded 19. There are also 5 missing. Amongst the killed I am sorry to number Lieutenant S.M. Brackenridge, a very fine, promising officer, and amongst the wounded are Lieutenants Charles F. Platt and A.M. Mull, and Sailing Master Clough. The former dangerously, and the 2 last severely. There are also 4 midshipmen severely wounded. How this unfortunate accident occurred, I am not yet able to inform you, nor have I time to state more particularly. I will, as soon as possible, give a detailed account of the affair. I have the honor to be, sir, very respectfully, J. Chauncey. Honorable John Branch, Secretary of the Navy, Washington, U.S. Navy Yard, New York, June 8, 1829. Sir, I had been on board the Fulton all the morning, inspecting the ship and men, particularly the second invalids, which had increased considerably from other ships, and whom I intended to ask the department permission to discharge, as being of little use to the service. I had left the ship but a few moments before the explosion took place, and was in my office at that time. The report did not appear to me louder than a 32-pounder, although the destruction of the ship was complete and entire, owing to her very decayed state. For there was not on board at the time more than 2.5 barrels of damaged powder, which was kept in the magazine for the purpose of firing the morning and evening gun. It appears to me that the explosion could not have taken place from accident, as the magazine was as well or better secured than the magazines of most of our ships, yet it would be difficult to assign a motive to those in the magazine for so horrible an act, as voluntarily to destroy themselves and those on board. If the explosion was not the effect of design, I am at a loss to account for the catastrophe. I have the honor to be, sir, very respectfully, J. Chauncey. Honorable John Branch, Secretary of the Navy, Washington. Appendix. Note A. Steam Frigate. Report of Henry Rutgers, Samuel L. Mitchell, and Thomas Morris, the Commissioners superintending the construction of a steam vessel of war, to the Secretary of the Navy. New York, December 28, 1815. Sir, the war which was terminated by the Treaty of Ghent afforded, during its short continuance, a glorious display of the valor of the United States by land and by sea. It made them much better known to foreign nations, and, what is of much greater importance, it contributed to make them better acquainted with themselves. It excited new enterprises. It educed latent talents. It stimulated to exertions unknown to our people before. A long extent of coast was exposed to an enemy, powerful above every other on the ocean. His commanders threatened to lay waste our country with fire and sword, and actually, in various instances, carried their menaces into execution. It became necessary for our defense to resist by every practicable method such a formidable foe. It was conceived by a most ingenious and enterprising citizen that the power of steam could be employed to propel a floating battery, carrying heavy guns, to the destruction of any hostile force that should hover on the shores or enter the ports of our Atlantic frontier. The perfect and admirable success of his project for moving boats containing travelers and baggage by the same elastic agent opened the way to its employment for carrying warriors and the apparatus for fighting. The plan was submitted to the consideration of the executive of an enlightened government. Congress, influenced by the most liberal and patriotic spirit, appropriated money for the experiment, and the Navy Department, then conducted by the Honorable William Jones, appointed commissioners to superintend the construction of a convenient vessel under the direction of Robert Fulton, the inventor, as engineer, and Messrs. Adam and Noah Brown as naval constructors. The enterprise, from its commencement, and during a considerable part of its preparatory operations, was aided by the zealous cooperation of Major General Dearborn, then holding his headquarters at the city of New York, as the officer commanding the 3rd Military District. The loss of his valuable counsel in conducting a work which he had maturely considered, and which he strongly recommended, was the consequence of his removal to another section of the Union, where his professional talents were specially required. The keels of the steam frigate were laid on the 20th day of June, 1814. The strictest blockade the enemy could enforce interrupted the coasting trade and greatly enhanced the price of timber. The vigilance with which he guarded our coast against intercourse with foreign nations rendered difficult the importation of copper and iron. The same impediment attended the supplies of coal heretofore brought to New York from Richmond and Liverpool. Lead, in like manner, was procured under additional disadvantages. These attempts of the enemy to frustrate the design were vain and impotent. All the obstacles were surmounted. Scarcity of the necessary woods and metals were overcome by strenuous exertions, and all the blockading squadron could achieve was not a disappointment in the undertaking, but merely an increase of the expense. So, in respect to tradesmen and laborers, there was an extraordinary difficulty. Shipwrights had repaired to the lakes for repelling the enemy in such numbers that, comparatively speaking, few were left on the seaboard. A large portion of the men who had been engaged in daily work had enlisted as soldiers, and had marched under the banners of the nation to the defense of its rights. Yet, amidst the scarcity of hands, a sufficient number were procured for the purpose which the commissioners had in charge. An increase of wages was the chief impediment, and this they were enabled practically to overcome. By the exemplary combination of diligence and skill on the part of the engineer and constructors, the business was so accelerated that the vessel was launched on the 29th day of October amidst the plaudits of an unusual number of citizens. Measures were immediately taken to complete her equipment. The boiler, the engine, and the machinery were put on board with all possible expedition. Their weight and size far surpassed anything that had been witnessed before among us. The stores of artillery in the New York, not furnishing the number and kind of cannon which she was destined to carry, it became necessary to transport guns from Philadelphia. A prize taken from the enemy put some fit and excellent pieces at the disposal of the Navy Department. To avoid the danger of capture by the enemy's cruisers, these were carted over miry roads of New Jersey. 20 heavy cannon were thus conveyed by the strength of horses. Carriages of the most approved model were constructed, and everything done to bring her into prompt action as an efficient instrument of war. About this time, an officer, preeminent for bravery and discipline, was commissioned by the government to her command. Prior to this event, it had been intended by the commissioners to finish her conformably to the plan originally submitted to the executive. She is a structure resting upon 2 boats and keels, separated from end to end by a canal 15 feet wide and 66 long. One boat contained the cauldrons of copper to prepare her steam. The vast cylinder of iron, with its piston, levers, and wheels, occupied a part of its fellow. The great water wheel revolved in the space between them. A main gun deck supported her armament, and was protected by a bulwark 4 feet 10 inches thick of solid timber. This was pierced by 30 portholes, to enable as many 32-pounders to fire red-hot balls. Her upper or spar deck was plain, and she was to be propelled by her enginery alone. It was the opinion of Captain Porter and Mr. Fulton that the upper deck ought to be surrounded with a bulwark and stanchions, that 2 stout masts should be erected to support lateen sails, and there should be bowsprees for jibs, and that she should be rigged in a corresponding style. Under authorities so great, and with expectation of being able to raise the blockade of New London by destroying, taking, or routing the enemy's ships, all these additions were adopted and incorporated with the vessel. It must here be observed that during the exhaustion of the Treasury and the temporary depression of public credit, the commissioners were exceedingly embarrassed. Their payments were made in Treasury notes, which they were positively instructed to negotiate at par. On several occasions, even these were so long withheld that the persons who had advanced materials and labor were importunate for payment, and silently discontented. To a certain extent, the commissioners pledged their private credit. Notwithstanding all this, the men at one time actually broke off. The work was retarded, and her completion unavoidably deferred, to the great disappointment of the commissioners, until winter rendered it impossible for her to act. Under all this pressure, they nevertheless persevered in the important object confided to them, but their exertions were further retarded by the premature and unexpected death of the engineer. The world was deprived of his invaluable labors before he had completed this favorite undertaking. They will not inquire wherefore, in the dispensations of divine providence, he was not permitted to realize his grand conception. His discoveries, however, survive for the benefit of mankind, and will extend to unborn generations. At length all matters were ready for a trial of the machinery to urge such a bulky vessel through the water. This essay was made on the 1st day of June, 1815. She proved herself capable of opposing the wind, and stemming the tide, of crossing currents, and of being steered among vessels riding at anchor, though the weather was boisterous and the water rough. Her performance demonstrated that the project was successful. No doubt remained that a floating battery, composed of heavy artillery, could be moved by steam. The commissioners returned from the exercise of the day, satisfied that the vessel would answer the intended purpose, and consoled themselves that their care had been bestowed upon a worthy object. But it was discovered that various alterations were necessary. Guided by the light of experience, they caused some errors to be corrected, and some defects to be supplied. She was prepared for a second voyage with all practicable speed. On the 4th of July she was again put in action. She performed a trip to the ocean, eastward of Sandy Hook, and back again, a distance of 53 miles, in 8 hours and 20 minutes. A part of this time she had the tide against her, and had no assistance whatever from sail. Of the gentlemen who formed the company invited to witness the experiment, not one entertained a doubt of her fitness for the intended purpose. Additional expedients were notwithstanding necessary to be sought for quickening and directing her motion. These were devised and executed with all possible care. Suitable arrangements having been made, a third trial of her powers was attempted on the 11th day of September, with the weight of 26 of her long and ponderous guns, and a considerable quantity of ammunition and stores on board. Her draught of water was short of 11 feet. She changed her course by inverting the motion of the wheel, without the necessity of putting about. She fired salutes as she passed the forts, and she overcame the resistance of the wind and tide in her progress down the bay. She performed beautiful maneuvers around the United States frigate Java, then at anchor near the lighthouse. She moved with remarkable celerity, and she was perfectly obedient to her double helm. It was observed that the explosion of power produced very little concussion. The machinery was not affected by it in the smallest degree. Her progress during the firing was steady and uninterrupted. On the most accurate calculations, derived from heaving the log, her average velocity was 5.5 miles per hour. Notwithstanding the resistance of currents, she was found to make headway at the rate of 2 miles an hour against the ebb of the East River, running 3.5 knots. The day's exercise was satisfactory to the respectable company who attended, beyond their utmost expectations. It was universally agreed that we now possessed a new auxiliary against every maritime invader. The city of New York, exposed as it is, was considered as having the means of rendering itself invulnerable. The Delaware, Chesapeake, Long Island Sound, and every other bay and harbor in the nation may be protected by the same tremendous power. Among the inconveniences observable during the experiment was the heat endured by the men who attended the fires. To enable a correct judgment to be formed on this point, one of the commissioners, Dr. Mitchell, descended and examined by a thermometer the temperature of the hold between the two boilers. The quicksilver, exposed to the radiant heat of the burning fuel, rose to 116 degrees of Fahrenheit scale. Though exposed thus to its intensity, he experienced no indisposition afterwards. The analogy of potteries, forges, glass houses, kitchens, and other places where laborers are habitually exposed to high heats is familiar to persons of business and of reflection. In all such occupations, the men by proper relays perform their services perfectly well. The government, however, will understand that the hold of the present vessel could be rendered cooler by other apertures for the admission of air, and that on building another steam frigate, the comfort of the firemen might be provided for, as in the ordinary steamboats. The commissioners congratulate the government and the nation on the event of this noble project. Honorable alike to its author and its patrons, it constitutes an era in warfare and the arts. The arrival of peace, indeed, has disappointed the expectations of conducting her to battle. That last and conclusive act of showing her superiority in combat has not been in the power of the commissioners to make. If a continuance of tranquillity should be our lot, and this steam vessel of war be not required for the public defense, the nation may rejoice that the fact we have ascertained is of incalculably greater value than the expenditure, and that if the present structure should perish, we have the information never to perish, how, on a future emergency, others may be built. The requisite variations will be dictated by circumstances. Owing to the cessation of hostilities, it has been deemed inexpedient to finish and equip her for immediate and active employ. In a few weeks, everything that is incomplete could receive the proper adjustment. After so much has been done, and with such encouraging results, it becomes the commissioners to recommend that the steam frigate be officered and manned for discipline and practice. A discreet commander, with a selected crew, could acquire experience in the mode of navigating this peculiar vessel. The supplies of fuel, the tending of the fire, the replenishing of the expended water, the management of the mechanism, the heating of shot, the exercise of the guns, and various matters can only become familiar by use. It is highly important that a portion of seamen and marines should be versed in the order and economy of the steam frigate. They will augment, diffuse, and perpetuate knowledge. When, in process of time, another war shall call for more structures of this kind, men regularly trained to her tactics may be dispatched to the several stations where they may be wanted. If, on any such disposition, the government should desire a good and faithful agent, the commissioners recommend Captain Obed Smith to notice, as a person who has ably performed the duties of inspector from the beginning to the end of the concern. Annexed to the report, you will find, sir, several statements explanatory of the subject. A separate report of our colleague, the Honorable Oliver Wolcott, whose removal from New York precluded him from attending to the latter part of the business with his accustomed zeal and fidelity, is herewith presented. A drawing of her form and appearance by Mr. Morgan, as being like to give satisfaction to the department, is also subjoined, as are likewise an inventory of her furniture and effects, and an account of the timber and metals consolidated in her fabric. It is hoped these communications will evince the pains taken by the Commissioners to execute the honorable and responsible trust reposed in them by the Government. Samuel L. Mitchell, Thomas Morris, Henry Rutgers. End of section 15. Section 16 of Smithsonian Institution, United States National Museum, Bulletin 240, Contributions from the Museum of History and Technology, Papers 34 through 44 on Science and Technology by the Museum of History and Technology. This LibriVox recording is in the public domain. Paper 40, History of Phosphorus by Edward Farber. The cold light produced by phosphorus caused it to be considered a miraculous chemical for a long time after its discovery, about 1669. During the intervening 3 centuries, numerous other chemical miracles have been found. Yet phosphorus retains a special aura of universal importance in chemistry. Many investigators have occupied themselves with this element and its diverse chemical compounds. Further enlightenment and insight into the ways of nature can be expected from these efforts. Not only is the story of phosphorus a major drama in the history of chemistry, it also illustrates in a spectacular example the growth of the science through the discovery of connections between apparently unrelated phenomena and the continuous interplay between basic science and the search for practical usage. The author, Edward Farber, is a research professor at American University, Washington, D.C., and has been associated with the Smithsonian Institution as a consultant in chemistry. When phosphorus was discovered nearly 3 centuries ago, it was considered a miraculous thing. The only event that provoked a similar emotion was the discovery of radium more than 2 centuries later. The excitement about the phosphorus igneous, Boyle's icy nocta luca, was slowly replaced by or converted into chemical research. Yet if we would allow room for emotion in research, we could still be excited about the wondrous substance that chemical and biological work continues to reveal as vitally important. It is a fundamental plant nutrient, an essential part in nerve and brain substance, a decisive factor in muscle action and cell growth, and also a component in fast-acting, powerful poisons. The importance of phosphorus was gradually recognized, and the means by which this took place are characteristic and similar to other developments in the history of science. This paper was written in order to summarize these various means which led to the highly complex ways of present research. The element from animals and plants. It was a little late to search for the philosopher's stone in 1669, yet it was in such a search that phosphorus was discovered. Wilhelm Homburg, 1652 to 1715, described it in the following manner. Brand, a man little known, of low birth, with a bizarre and mysterious nature in all he did, found this luminous matter while searching for something else. He was a glassmaker by profession, but he had abandoned it in order to be free for the pursuit of the philosophical stone, with which he was engrossed. Having put it into his mind that the secret of the philosophical stone consisted in the preparation of urine, this man worked in all kinds of manners and for a very long time without finding anything. Finally, in the year 1669, after a strong distillation of urine, he found in the recipient a luminant matter, that has since been called phosphorus. He showed it to some of his friends, among them Mr. Kunkel. Neither the name nor the phenomenon were really new. Organic phosphorescent materials were known to Aristotle, and a lithophosphorus was the subject of a book published in 1640, based on a discovery made by a shoemaker, Vincenzo Casciarolo, on a mountainside near Bologna in 1630. Was the substance new which Brand showed to his friends? Johann Gottfried Leonhardi quotes a book of 1689 in which the author Klettwitsch claims that this phosphorus had already been known to Fernelius, the court physician of King Henry II of France, 1154 through 1189. To the same period belongs the Ordinatio Alcid Becher Saraceni philosophy, in which Ferdinand Hofer found a distillation of urine with clay and carbonaceous material described, and the resulting product named escarbuncle. It would be worth looking for this source, although Becher would still remain an entirely unsuccessful predecessor. It does seem strange that in all the distillations of arbitrary mixtures, the conditions should never before 1669 have been right for the formation and the observation of phosphorus. For Brand's contemporaries, at least, the discovery was new and exciting. The philosopher Gottfried Wilhelm von Leibniz, 1646 to 1716, considered it important enough to devote some of his time, between his work as a librarian in Hanover and Wolfenbüttel, his efforts to reunite the Protestant and the Catholic churches, and his duties as a privy councillor in what we would call the Department of Justice, to a history of phosphorus. This friend of Huygens and Boyle tried to prove that Kunkel was not justified in claiming the discovery for himself. Since then it had been shown that Johann Kunkel, 1630 to 1703, actually worked out the method which neither Brand nor his friend Kraft wanted to disclose. Boyle also developed a method independently, published it, and instructed Gottfried Hankwitz in the technique. Later on, Jean Hillot, 1685 to 1765, gave a meticulous description of the details and a long survey of the literature. To obtain phosphorus, a good proportion of coal, regarded as a type of phlogiston, was added to urine, previously thickened by evaporation and preferably after putrefaction, and the mixture was heated to the highest attainable temperature. It was obvious that phlogiston entered into the composition of the distillation product. The question remained whether this product was generated de novo. In his research of 1743 to 1746, Andreas Sigismund Marggraf, 1709 to 1782, provided the answer. He found the new substance in edible plant seeds, and he concluded that it enters the human system through the plant food, to be excreted later in the urine. He did not convince all the chemists with his reasoning. In 1789, Macquer wrote, "There are some who, even at this time, hold that the phosphorical, or phosphorecia, acid generates itself in the animals, and who consider this to be the animalistic acid." Although Marggraf was more advanced in his arguments than these chemists, yet he was a child of his time. The luminescent and combustible, almost wax-like substance impressed him greatly. My thoughts about the unexpected generation of light and fire out of water, fine earth, and phlogiston I reserve to describe at a later time. These thoughts went so far as to connect the new marvel with alchemical wonder tales. When Marggraf used the essential salt of urine, also called sal microcosmicum, and admixed silver chloride, or horny silver, to it for the distillation of phosphorus, he expected a partial conversion of silver by phlogiston and the added fine vitrifiable earth, but no trace of a more noble metal appeared. Robert Boyle had already found that the burning of phosphorus produced an acid. He identified it by taste, and by its influence on colored plant extracts serving as indicators. Hankwitz described methods for obtaining this acid, and Marggraf showed its chemical peculiarities. they did not necessarily establish phosphorus as a new element. To do that was not as important at the time as to conjecture on analogies with known substances. Underlying all its unique characteristics was the analogy of phosphorus with sulfur. Like sulfur, phosphorus can burn in two different ways, either slowly or more violently, and form two different acids. The analogy can, therefore, be extended to explain the results in both groups in the same way. In the process of burning, the combustible component is removed, and the acid originally combined with the combustible is set free. Whether the analogy should be pursued even further remained doubtful, although some suspicion lingered on for a while that phosphoric acid might actually be a modified sulfuric acid. Analogies and suspicions like these were needed to formulate new questions and stimulate new experiments. They are cited here for their important positive value in the historical development, and not for the purpose of showing how wrong these chemists were from our point of view, a point of view which they helped to create. The widespread interest in the burning of sulfur and of phosphorus naturally caught Lavoisier's attention. In his first volume of Opuscule physique et chimique, 1774, he devoted 20 pages to his experiments on phosphorus. He amplified them a few years later when he attributed the combustion to a combustion of phosphorus with the eminently respirable part of the air. In the Méthode de nomenclature chimique of 1787, the column of undecomposed substances lists sulfur as the radical sulfurique, and phosphorus, correspondingly, as the radical phosphorique. The acids are now shown to be compounds of the undecomposed radicals, the complete reversion of the previous concept of this relationship. A part of the old analogy remained as far as the acids are concerned. Sulfuric acid corresponds to phosphoric, sulfurous acid to phosphorus acid, with less oxygen than in the former. Early uses. In the 18th century, phosphorus was a costly material. It was produced mostly for display and to satisfy curiosity. Guillaume François Rouelle, 1703 to 1770, demonstrated the process in his lectures, and as Mercure reports, he very often succeeded in making it. Robert Boyle had the idea of using phosphorus as a light for underwater divers. A century later, instant lights were sold with molten phosphorus as the igniter, but they proved cumbersome and unreliable. Because white phosphorus is highly poisonous, an active development of the use in matches occurred only after the conversion of the white modification into the red had been studied by Emil Kopp, 1844, by Wilhelm Hittorf, 1824 to 1914, and in its practical application by Anton Schroeter, 1802 to 1875. The most exciting early use, however, was in medicine. It is not surprising that such a use was sought at that time. Any new material immediately became the hope of ailing mankind and of striving inventors. Phosphorus was prescribed in liniments with fatty oils or as solution in alcohol and ether for external and internal application. A certain Dr. Kramer found it efficient against epilepsy and melancholia, 1730. A Professor Hartmann recommended it against cramps. However, in the growing production of phosphorus for matches, the workers experienced the poisonous effects. In the plant of Black and Bell at Stratford, this was prevented by inhaling turpentine. Experiments on dogs were carried out to show that poisoning by phosphorus could be remedied through oil of turpentine. Chemical constitution of phosphoric acids. In a long article on phosphorus, Edmund Wilm wrote in 1876, "For a century, urine was the only source from which phosphorus was obtained. After Gahn in 1769 recognized the presence of phosphoric acid in bones, Scheele indicated the procedure for making phosphorus from them." Actually, Gahn used at first hartshorn, cornu cervi ustum, and Scheele doubted, until he checked it himself, that his esteemed friend was right. A few years later, Scheele corrected Gahn's assumption, and the sal microcosmicum was an ammonium salt. Instead, it is a tertiary neutral salt, consisting of alkali mineralifico, that is, sodium, alkali volatili, and acido phosphori. In the years after 1770, phosphorus was discovered in bones and many other parts of various animals. Treatment with sulfuric acid decomposed these materials into a solid residue and dissolved phosphoric acid. Many salts of this acid were produced in crystalline form. Heat resistance had been considered one of the outstanding characteristics of phosphoric acid. Now, however, in the process of drying and heating certain phosphates, it became clear that three kinds of phosphoric acids could be produced: ortho, pyro, and meta. Berzelius cited these acids as examples of compounds which are isomeric. This word was intended to designate compounds which contain the same number of atoms of the same elements, but combined in different manners, thereby explaining their different chemical properties and crystal forms. It was in 1830 that Berzelius propounded this companion of the concept, isomorphism, which was to collect all cases of equal crystal form in compounds in which equal numbers of atoms of different elements are put together in the same manner. Together, the two concepts of isomerism and isomorphism seem to cover all the known exceptions from the simplest assumption as to specificity and chemical composition. However, only a few years later, Thomas Graham, 1805 to 1869, proved that the three phosphoric acids are not isomeric. He used the proportion of 2p to 5o in the oxide, which Berzelius had thought justified at least until an example of the contrary could be sufficiently established. Refining the techniques of Gay-Lussac, 1816, and several other investigators, Graham characterized the three phosphoric acids as a terphosphate, a biphosphate, and phosphate of water. Actually, this was the wrong terminology for what he meant, and formulated as trihydrate, bihydrate, and monohydrate of phosphorus oxide. In this manner of writing the formulas, each dot over the symbol for the element was to indicate an atom of oxygen. Thus, he wrote H3, 3 dots, P, 4 dots, H2, 2 dots, P, 3 dots, and H, 1 dot, P, 1 dot. Graham had come to this understanding of the phosphoric acids through his previous studies of alkoates, definite compounds of salts and alcohol analogous to the hydrates, 1831. Liebig started from analogies he saw with certain organic acids when he formulated the phosphoric acids with a constant proportion of water, aqueous, and varying proportions of phosphoric acid, P, as follows: 2p3 aqueous phosphoric acid, 3p3 aqueous pyrophosphoric acid, 6p3 aqueous metaphosphoric acid. Salts are formed when a basis, that is, a metal oxide, replaces water. When potassium acid sulfate is neutralized by sodium base, the acid salt divides into Glauber salt and potassium sulfate, which proves the acid salt to be a mixture of the neutral salt with its acid. Sodium acid phosphate behaves quite differently. After neutralization by a potassium base, hydroxide, the salt does not split up. A uniform sodium-potassium phosphate is obtained. Therefore, phosphoric acid is truly 3-basic. This result has later been confirmed, but the analogy by means of which it had been obtained was very weak, in certain parts quite wrong. The acids from the two lower oxides of phosphorus were also considered as 3-basic. Adolphe Wurtz, 1817 to 1884, formulated them in 1846, according to the theory of chemical types. PO, 3 dots, O3, phosphoric acid, H3. PHO, 2 dots, O2, phosphoric acid, H2. PH2O, 1 dot, O, hypophosphorus acid, H. Further proof of these constitutions was sought in the study of the esters formed when the acids react with alcohols. Among the analogies and generalizations by which the research on phosphoric acid was supported, and to the results of which it contributed a full share, was the new theory of acids. Not oxygen, Lavoisier's general acidifier, but reactive hydrogen determines the character of acids. In this brief survey, it seems sufficient just to mention this connection without describing it in detail. The study of phosphoric acids led to important new concepts in theoretical chemistry. The finding of polybasicity was extended to other acids and formed the model that helped to recognize the polyfunctionality in other compounds, like alcohols and amines. The hydrogen theory of acids was fundamental for further advance. In another dimension, it is particularly interesting to see that large-scale applications followed almost immediately and directly from the new theoretical insight. The first and foremost of these applications was in agriculture. End of section 16. Section 17 of Smithsonian Institution, United States National Museum, Bulletin 240, Contributions from the Museum of History and Technology, papers 34 through 44 on Science and Technology, by the Museum of History and Technology. This LibriVox recording is in the public domain. Paper 40, History of Phosphorus, by Edward Farber, Part 2. Phosphates as Plant Nutrients. 100 years after the discovery of cold light, the presence of phosphorus in plants and animals was ascertained, and its form was established as a compound of phosphoric acid. This knowledge had little practical effect until the nature of the acid, in its various forms, was explained through the work of Thomas Graham. From it, there started a considerable technical development. At about that time, 1833, the Duke of Richmond proved that the fertilizing value of bones resided not in the gelatin, nor in the calcium, but in the phosphoric acid. Thus he confirmed what Theodore de Saussure had said in 1804, that we have no reason to believe that plants can exist without phosphorus. Unknowingly at first, the farmer had supplied this element by means of the organic fertilizers he used, manure, excrements, bones, and horns. Now, with the value of phosphorus known, a search began for mineral phosphates to be applied as fertilizers. Jean-Baptiste Boussingault, 1802 to 1887, an agricultural chemist in Lyons, traveled to Peru to see the guano deposits. Garcilaso de la Vega, circa 1540 to circa 1616, noted in his History of Peru, 1604, that guano was used by the Incas as a fertilizer. 200 years later, Alexander von Humboldt revived this knowledge, and Humphrey Davy wrote about the benefits of guano to the soil. Yet the application of this fertilizer developed only slowly, until Justus Liebig sang its praise. Imports into England rose and far exceeded those into France, where, between 1857 and 1867, about 50,000 tons were annually received. The other great advance in the use of phosphatic plant nutrients started with Liebig's recommendation of 1840 to treat bones with sulfuric acid for solubilization. This idea was not entirely new. Since 1832, a production of a superphosphate from bones and sulfuric acid had been in progress at Prague. At Rothamsted in 1842, John Bennett Laws obtained a patent on the manufacture of superphosphate. Other manufacturers in England followed, and were successful, although James Muspratt, 1793 to 1886, at Newton, lost much time and some thousands of pounds on Liebig's idea of a mineral manure. It was difficult enough to establish the efficacy of bones and artificially produced phosphates in promoting the growth of plants under special conditions of soils and climate. Therefore, the question as to the action of phosphates in the growing plant was not even seriously formulated at that time. The beneficial effects were obvious enough to increase the use of phosphates as plant nutrients and to call for new sources of supply. Active developments of phosphate mining and treating started in South Carolina in 1867 and in Florida in 1888. In a reciprocal action, more phosphate application to soils stimulated increasing research on the conditions and reactions, obtaining in the complex and varying compositions called soil. The findings of bacteriologists made it clear that physics and chemistry had to be amplified by biology for a real understanding of fertilizer effects. After 1900, for example, Julius Stocklasa, 1857 to 1936, pointed out that bacterial action in soil solubilizes water-insoluble phosphates and makes them available to the plants. The insight into the importance of phosphorus in organisms, especially since Liebig's time, is reflected in the work of Friedrich Nietzsche, 1844 to 1900. This revaluator of all values, who modestly said of himself, "I am dynamite," once explained the human temperaments as caused by the inorganic salts they contain. The differences in temperament are perhaps caused more by the different distribution and quantities of the inorganic salts than by everything else. Bilious people have too little sodium sulfate. The melancholics are lacking in potassium sulfate and phosphate, too little calcium phosphate in the phlegmatics. Courageous natures have an excess of iron phosphate. See Volume 12 of Nietzsche's works. Edited by Neumann, Kroner, Leipzig, 1886. In this strange association of inorganic salts with human temperaments, the role of iron phosphate as a producer of courage is particularly interesting. What would a modern philosopher conclude if he followed the development of insight into the composition and function of complex phosphate compounds in organisms? From inorganic to organic phosphates. By the middle of the 19th century, the source of phosphorus in natural phosphates and the chemistry of its oxidation products has been established. The main difficulty that had to be overcome was that these oxidation products existed in so many forms, not only several stages of oxidation, but in addition, aggregations and condensations of the phosphoric acids. Once the fundamental chemistry of these acids was elucidated, the attention of chemists and physiologists turned the task of finding the actual state in which phosphorus compounds were present in the organisms. It had been a great advance when it had been shown that plants need phosphates in their soil. This led to the next question concerning the materials in the body of the plant, for which phosphates were being used and into which they were incorporated. Similarly, the knowledge that animals attain their phosphates from the digested plant food called, in the next step of scientific inquiry, for information on the nature of phosphates produced from this source. The method used in this inquiry was to subject anatomically separated parts of the organisms to chemical separations. This means for such separations had to be more gentle than the strong heat and destructive chemicals that had been considered adequate up to then. The interpretation of the new results naturally relied on the general advance of chemistry, the development of new methods for isolating substances of little stability, of new concepts concerning the arrangements of atoms in the molecules, and of new apparatus to measure their rates of change. Figure 1 is a vertical section of the furnace, and Figure 2 is a diagram to illustrate the means for regulating the electromotive force or quantity of current across the furnace. F is the furnace containing the charge to be treated. It has an inlet hopper with slides, by which the charge can be admitted without opening communication between the interior of the furnace and the outer air. B is a screw conveyor, by which the charge is pushed forward into the furnace. C' are the electrodes, consisting of blocks or cylinders, or the like of carbon fixed in metal socket pieces, to which the electric circuit wires from the dynamo are affixed. The current, as aforesaid, may be either continuous or alternating. C2 are rods of metal or carbon, which are used to establish the electric circuit through the furnace, the said rods being inserted into holes in conductors, in contact with the socket pieces, and in the furnace as shown. G is the outlet for the gas or vapor, H the slag tap hole, and X the opening for manipulating the charge, the said openings being closed by clay or otherwise when the furnace is at work. I use coke or other form of carbon in the charge between the electrodes, the said coke being in contact with the said electrodes, so that complete incandescence is ensured. A means for varying the electromotive force or quantity of current across the furnace with varying resistance of the charge is illustrated by the diagram in Figure 2. C'(C2) indicates the electrodes in the furnace, as in Figure 1, and D is the dynamo, T its terminals. E represents the exciting circuit. R are resistances, and RS is the resistance switch, which is operated to put in more or less resistance at R, as the resistance of the charge in the furnace lessens or increases. This switch may be automatically operated, and a suitable arrangement for the purpose is a current regulator, such as is described in the specifications of English Letters Patent Number 14,504 of September 14, 1889, granted to William Henry Douglas and Thomas U. Parker. In the system of chemistry, as it developed in the first half of the 19th century, the new development can be characterized as the turn from inorganic to organic phosphates, from the substance of minerals and strong chemical interactions to the components in which phosphate groups remain combined with carbon-containing substances. Phosphatides and phosphogens. The important phosphorus compounds in organisms are much more complex than the simple salts, to which Nietzsche attributed such influence on man's character. Long before he wrote, it was known that phosphoric acid combines not only with inorganic bases to form salts, but with alcohols to form esters. In the middle of the 19th century, Théophile Just Pellows, 1807 to 1867, extended this knowledge to an ester of glycerol. This proved to be significant in several respects. Glycerol had been shown by Michael Chevreul, 1786 to 1889, as the substance in fats that is released in the process of soap boiling, when the fatty acids are converted into their salts. That it has the nature of an alcohol had been demonstrated by Marcellin Berthelot. Instead of one alcoholic hydroxyl group, OH, like ethanol, the alcohol of fermentation, or two hydroxyl groups, like ethylene glycol, glycerol contains three such groups. It was the only natural alcohol known at that time. That this alcohol would combine with phosphoric acid could be predicted, but that the ester as obtained by Pellows still contained free acidic functions and formed a water-soluble barium salt was a new experience. Shortly after this experience had been gained, it became valuable for understanding the chemical nature of a new substance extracted from a natural organ. This substance was named lecithin by its discoverer, Nicholas Theodore Gobley, 1811 to 1876, because he obtained it from egg yolk, in Greek, lekydos. He used ether and alcohol for this extraction. Had he used water and mineral acid instead, he would not have found lecithin, but only its components. As Gobley and slightly later Oscar Liebreich, 1839 to 1908, subjected lecithin to treatment with boiling water and acid, they separated it into three parts. One of them was the glycerophosphoric acid of Pellows. The second was the well-known stearic acid of Chevreul. But the third was somewhat mysterious. This third substance was the same as one previously noticed when nerves had been subjected to an extraction by boiling water and acid, and therefore called nerve substance, or neurine. Adolf Friedrich Strecker, 1822 to 1871, established the identity of this neurine with a product he had extracted from bile, and which went under the name of choline. Adolf Wurtz, 1817 to 1884, succeeded in synthesizing this substance from ethylene oxide, CH2.O.CH2, and trimethylamine, NCH3,3. Thus, all three parts were identified, and Strecker put them together to construct a chemical formula for lecithin. glycerophosphoric acid combined with a fatty acid and with choline, a hydrate of norine. This formula was not quite correct. Richard Willstatter showed that an internal neutralization takes place between the amino group and the free acidic residue. This is expressed in his lecithin formula of 1918. When the aim was to distill elementary phosphorus out of an organic material, it did not matter whether this was fresh or putrefied. For obtaining lecithin out of egg yolk or similar materials, it was essential to use it in fresh condition. Otherwise, enzymes would have decomposed it. Through more recent work, 4 enzymes have been separated, which act specifically in decomposing lecithin. Enzyme A removes one fatty acid and leaves a complex residue called lysolecithin intact. Enzyme B attacks this residue and splits off the remaining fatty acid group from it. Enzyme C liberates only the choline from lecithin, and enzyme D opens lecithin at the ester bond between glycerol and phosphoric acid. This is shown in the following diagram. Enzyme A, the substrate, lecithin, products, lysolecithin and fatty acids. Enzyme B, substrate, lysolecithin, products, glycerophosphocholine and fatty acids. Enzyme C, substrate lecithin, products, phosphatidic acid and choline. Enzyme D, substrate lecithin, products, phosphorylcholine and diglyceride. Several fatty acids can be present in lecithin from various sources, palmitic and oleacic, besides the stearic acid, which at first had been thought the only one involved. In another group of extracts from brain or nerve tissue, aminoethanol, H2, NCH2, CH2, OH, is found instead of the choline of lecithin. The variations include the alcohol, to which the fatty acids and choline phosphate are attached. For example, glycerol can be replaced by the so-called meat sugar, inositol, which has 6 hydroxyl groups in its hexagon-shaped molecule, C6, H6, OH6. The generally similar behavior of these phosphate and fat-containing substances was emphasized by Ludwig Thüttigem, 1829 to 1901. He coined the name phosphatides for this group of substances from seeds and nerves. His work on the phosphates in brain substance aroused particular interest. When William Crookes drew his highly imaginative picture of an evolution of the chemical elements, he put it into phosphorus for the brain, salt for the sea, clay for the solid earth. But phosphatides occur in many places of organisms, in bacteria, in leaves and roots of plants, in fat and tissue of animals, and where phosphatides are found, there are also enzymes that specifically act on them. They are called phosphatases, to imply that they split the phosphatides. In addition, enzymes are present which transfer phosphate groups from one compound to another. They are more abundant in seeds of high fat content than in more starch-containing seeds. But even potatoes and orange juice have phosphatases. Thus, from phosphatides, phosphoric acid is generated, and they could also be called phosphogens. Since 1926, however, the name phosphogens has been reserved for a group of organic substances that release their phosphoric acid very readily. The link between phosphorus and carbon is provided by oxygen in the phosphatides, by nitrogen in the phosphogens. In vertebrates, the basis for the phosphoric acid is creatine, whereas invertebrates have arginine instead. Nuclein and nucleic acids. All parts of an organism are essential for life. Only with this in mind does it make sense to say that the most important part of the cell is its nucleus. From the nuclei of cells in pus and in salmon sperm, Johann Friedrich Miescher, 1811 to 1887, obtained a peculiar kind of substance, which he named nuclein, 1868. Its phosphate content was easily discovered, but to find the exact proportions and the nature of the other components required special methods of separation from phosphatides and other proteins. It was difficult to develop such methods at a time when little was known about the properties, and particularly the stability of a nucleon. For preparing nucleon from yeast cells, Felix Hopf-Seyler, 1825 to 1895, described the following details. Yeast is dispersed in water to extract soluble materials, like salts or sugars. After a few hours, the insoluble material is separated, washed once more with water, and then extracted with a very dilute solution of sodium hydroxide. The slightly alkaline solution, freed from insoluble residues, is slowly added to a weak hydrochloric acid. A precipitate forms, which is separated by filtration, washed with dilute acid, then with cold alcohol, and finally extracted by boiling alcohol. The dried residue is the nucleon. It contains 6% phosphorus. A little more washing with water, a slightly longer treatment with acid or alcohol gives products of lower phosphorus content. Many experimental variations were necessary to establish the procedure that leads to purification without alteration of the natural substance. This was also true for the methods of chemical degradation, carried out in order to find the components of nucleons in their highest state of natural complexity. It was learned, for example, that the special kind of carbohydrate present in nucleons was very susceptible to change under the conditions of hydrolysis by acids. Phoebus Aaron Theodore Levine, 1869 to 1940, therefore used the digestion by a living organism. With E.S. London, he introduced a solution of nucleic acid into, for example, the gastrointestinal segment of a dog through a gastric fistula and withdrew the product of digestion through an intestinal fistula. Fortunately, the products obtained in such degradations were not new in themselves. The carbohydrate in this nucleic acid proved to be identical with D-ribose, which Emil Fischer had artificially made from arabinose and named ribose to indicate this relationship, 1891. The nitrogenous products of the degradation were identical with substances previously prepared in the long study of uric acid. In the course of this study, Emil Fischer established uric acid and a number of its derivatives as having the elementary skeleton of what he called pure uric acid, abbreviated to purine. Out of Adolf Bayer's work on barbituric acid came the knowledge of pyrimidine and its derivatives. From these findings, together with what Oswald Schmiedeberg, 1838 to 1921, had established concerning the presence of 4 phosphate groups in the molecule, 1899, Robert Fulton, 1884 to 1955, constructed the following scheme of a nucleic acid. Fulton's formula of 1918 is phosphoric acid, carbohydrate, guanine, phosphoric acid, carbohydrate, cytosine, phosphoric acid, carbohydrate, thymine, phosphoric acid, carbohydrate, adenine. Of the 4 basic components on the right, thymine occurs in the nucleic acid from the thymus gland. Yeast contains uracil instead. The difference between these 2 bases is 1 methyl group. Thymine is a 5-methyl uracil. In all of these basic substances, the structure of urea is involved, and they form pairs of oxidized and reduced states. The exact position of phosphoric acid was established after long work and verified by synthesis. A compound of adenine, ribose, and phosphoric acid was found in yeast, blood, and in skeletal muscle of mammals. From 100 grams of such muscle, 0.35 to 0.40 grams of this compound were isolated. If the muscle is at rest, the compound contains 3 molecules of phosphoric acid, linked through oxygen atoms. It was named adenosine triphosphate, or adenyl triphosphoric acid, usually abbreviated by the symbol ATP. It releases 1 phosphoric acid group very easily, and goes over in the diphosphate, ADP, but it can also lose 2 P groups as pyrophosphoric acid, and leave the monophosphate, AMP. This change of ATP was considered to be the main source of energy by muscle contraction by Otto Mehrhoff. The corresponding derivatives of guanine, cytosine, and uracil were also found, and they are active in the temporary transfer of phosphoric acid groups in biological processes. Thus, the study of organic phosphates progressed from the comparatively simple esters connected with fatty substances of organisms to the proteins and the nuclear substances of the cell. The proportional amount of phosphorus in the former was larger than in the latter. The actual importance and function in the life of organisms, however, is not measured by the quantity, but determined by the special nature of the compounds. The study of this function is the newest phase in the history of phosphorus, and represents the culmination of the previous efforts. This newest phase developed out of an accidental discovery concerning one of the oldest organic chemical industries, the production of alcohol by the fermentative action of yeast on sugar. A transition of carbohydrates through phosphate compounds to the end products of the fermentation process was found, and it gradually proved to be a kind of model for a host of biological processes. Specific phosphates were thus found to be indispensable for life. In reverse, the wrong kind of phosphates can destroy life. As a result, an important part of the new phase in phosphorus history consisted in the study and use of antibiotic phosphorus compounds. End of section 17.